Part 2, Chapter 1 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary CLERKE. Chapter 1, Foundation of Astronomical Physics, Part 2. Convincing evidence as to the true nature of the solar lines was, however, at length, in the autumn of 1859, brought forward at Heidelberg. Kirchhoff's experimentum crucis in the matter was a very simple one. He threw bright sunshine across a space occupied by vapor of sodium, and perceived with astonishment that the dark Fraunhofer line D, instead of being effaced by flame, giving a luminous ray of the same refrangibility, was deepened and thickened by the superposition. He tried the same experiment, substituting for sunbeams light from a Drummond lamp, and with similar result. A dark furrow, corresponding in every respect to the solar D line, was instantly seen to interrupt the otherwise unbroken radiance of its spectrum. The inference was irresistible, that the effect thus produced artificially was brought about naturally in the same way, and that sodium formed an ingredient in the glowing atmosphere of the sun. This first discovery was quickly followed up by the identification of numerous bright rays in the spectra of other metallic bodies with others of the hitherto mysterious Fraunhofer lines. Kirchhoff was thus led to the conclusion that besides sodium, iron, magnesium, calcium, and chromium are certainly solar constituents, and that copper, zinc, barium, and nickel are also present, though in smaller quantities. As to cobalt, he hesitated to pronounce, but its existence in the sun has since been established. These memorable results were founded upon a general principle first enunciated by Kirchhoff in a communication to the Berlin Academy, December 15, 1859, and afterwards more fully developed by him. It may be expressed as follows. Substances of every kind are opaque to the precise rays which they emit at the same temperature. That is to say, they stop the kinds of light or heat which they are then actually in a condition to radiate. But it does not follow that cool bodies absorb the rays which they would give out if sufficiently heated. Hydrogen at ordinary temperatures, for instance, is almost perfectly transparent. But if raised to the glowing point, as by the passage of electricity, it then becomes capable of arresting and at the same time of displaying in its own spectrum light of 4 distinct colors. This principle is fundamental to solar chemistry. It gives the key to the hieroglyphics of the Fraunhofer lines. The identical characters which are written bright in terrestrial spectra are written dark in the unrolled sheaf of sun rays. The meaning remains unchanged. It must, however, be remembered that they are only relatively dark. The substances stopping those particular tints in the neighbourhood of the sun are at the same time vividly glowing with the very same. Remove the dazzling solar background, by contrast with which they show as obscure, and they will be seen, and at critical moments actually have been seen, in all their native splendour. It is because the atmosphere of the sun is cooler than the globe it envelops that the different kinds of vapour constituting that atmosphere take more than they give, absorb more light than they are capable of emitting. Raise them to the same temperature as the sun itself, and their powers of emission and absorption being brought exactly to the same level, the thousands of dusky rays in the solar spectrum will be at once obliterated. The establishment of the terrestrial science of spectrum analysis was due, as we have seen, equally to Kirchhoff and Bunsen, but its celestial application to Kirchhoff alone. He effected this object of the aspirations, more or less dim, of many other thinkers and workers by the union of two separate, though closely related, lines of research: the study of the different kinds of light emitted by various bodies, and the study of the different kinds of light absorbed by them. The latter branch appears to have been first entered upon by Dr. Thomas Young in 1803. It was pursued by the younger Herschel, by William Allen Miller, Brewster, and Gladstone. Brewster, indeed, made in 1833 a formal attempt to found what might be called an inverse system of analysis with the prism based upon absorption, and his efforts were repeated just a quarter of a century later by Gladstone, but no general point of view was attained, nor, it may be added, was it by this path attainable. Kirchhoff's map of the solar spectrum, drawn to scale with exquisite accuracy, and printed in 3 shades of ink to convey the graduated obscurity of the lines, was published in the Transactions of the Berlin Academy for 1861 and 1862. Representations of the principal lines belonging to various elementary bodies formed, as it were, a series of marginal notes accompanying the great solar scroll, enabling the veriest tyro in the new science to decipher its meaning at a glance. Where the dark solar and bright metallic rays agreed in position, it might safely be inferred that the metal emitting them was a solar constituent, and such coincidences were numerous. In the case of iron alone, no less than 60 occurred in one half of the spectral area, rendering the chances absolutely overwhelming against mere casual conjunction. The preparation of this elaborate picture proved so trying to the eyes that Kirchhoff was compelled, by failing vision, to resign the latter half of the task to his pupil Hoffmann. The complete map measured nearly 8 feet in length. The conclusions reached by Kirchhoff were no sooner announced than they took their place, with scarcely a dissenting voice, among the established truths of science. The broad result, that the dark lines in the spectrum of the sun afford an index to its chemical composition, no less reliable than any of the tests used in the laboratory, was equally captivating to the imagination of the vulgar, and authentic in the judgment of the learned. And, like all genuine advances in the knowledge of nature, it stimulated curiosity far more than it gratified it. Now, the history of how discoveries were missed is often quite as instructive as the history of how they were made. It may then be worth while to expend a few words on the thoughts and trials by which, in the present case, the actual event was heralded. 3 times it seemed on the verge of being anticipated. The experiment which in Kirchhoff's hands proved decisive, of passing sunlight through glowing vapours and examining the superposed spectra, was performed by Professor W.A. Miller of King's College in 1845. Nay, more, it was performed with express reference to the question, then already, as has been noted, in debate, of the possible production of Fraunhofer's lines by absorption in a solar atmosphere. Yet it led to nothing. Again, at Paris in 1849, with a view to testing the asserted coincidence between the solar D line and the bright yellow beam in the spectrum of the electric arc, really due to the unsuspected presence of sodium, Léon Foucault threw a ray of sunshine across the arc and observed its spectrum. He was surprised to see that the D line was rendered more intensely dark by the combination of lights. To assure himself still further, he substituted a reflected image of one of the white-hot carbon points for the sunbeam, with an identical result. The same ray was missing. It needed but another step to have generalized this result, and thus laid hold of a natural truth of the highest importance. But that step was not taken. Foucault, keen and brilliant though he was, rested satisfied with the information that the voltaic arc had the power of stopping the kind of light emitted by it. He asked no further question, and was consequently the bearer of no further intelligence on the subject. The truth conveyed by this remarkable experiment was, however, divined by one eminent man. Professor Stokes of Cambridge stated to Sir William Thomson, now Lord Kelvin, shortly after it had been made, his conviction that an absorbing atmosphere of sodium surrounded the sun. And so forcibly was his hearer impressed with the weight of the argument based upon the absolute agreement of the D line in the solar spectrum with the yellow ray of burning sodium, then freshly certified by W. H. Miller, combined with Foucault's reversal of that ray, that he regularly inculcated in his public lectures on natural philosophy at Glasgow 5 or 6 years before Kirchhoff's discovery, not only the fact of the presence of sodium in the solar neighbourhood, but also the principle of the study of solar and stellar chemistry in the spectra of flames. Yet it does not appear to have occurred to either of these two distinguished professors, themselves among the foremost of their time in the successful search for new truths, to verify practically a sagacious conjecture in which was contained the possibility of a scientific revolution. It is just to add that Kirchhoff was unacquainted when he undertook his investigation either with the experiment of Foucault or the speculation of Stokes. For C.J. Ångström, on the other hand, perhaps somewhat too much has been claimed in the way of anticipation. His optical researches appeared at Uppsala in 1853, and in their English garb 2 years later. They were undoubtedly pregnant with suggestion, yet made no epoch in discovery. The old perplexities continued to prevail after, as before their publication. To Ångström, indeed, belongs the great merit of having revived Euler's principle of the equivalence of emission and absorption. But he revived it in its original crude form, and without the qualifying proviso which alone gave it value as a clue to new truths. According to his statement, a body absorbs all the series of vibrations it is, under any circumstances, capable of emitting, as well as those connected with them by simple harmonic relations. This is far too wide. To render it either true or useful, it had to be reduced to the cautious terms employed by Kirchhoff. Radiation strictly and necessarily corresponds with absorption only when the temperature is the same. In point of fact, Ångström was still, in 1853, divided between absorption and interference as the mode of origin of the Fraunhofer dark rays. Very important, however, was his demonstration of the compound nature of the spark spectrum, which he showed to be made up of the spectrum of the metallic electrodes superposed upon that of the gas or gases across which the discharge passed. It may here be useful, since without some clear ideas on the subject no proper understanding of recent astronomical progress is possible, to take a cursory view of the elementary principles of spectrum analysis. To many of our readers they are doubtless already familiar, but it is better to appear trite to some than obscure even to a few. The spectrum, then, of a body is simply the light proceeding from it, spread out by refraction into a brilliant variegated band, passing from brownish red through crimson, orange, yellow, green, and azure into dusky violet. The reason of this spreading out or dispersion is that the various colours have different wavelengths, and consequently meet with different degrees of retardation in traversing the denser medium of the prism. The shortest and quickest vibrations, producing the sensation we call violet, are thrown farthest away from their original path. In other words, suffer the widest deviation. The longest and slowest, the red, travel much nearer to it. Thus the sheaf of rays, which would otherwise combine into a patch of white light, are separated through the divergence of their tracks after refraction by a prism, so as to form a tinted riband. This visible spectrum is prolonged invisibly at both ends by a long range of vibrations, either too rapid or too sluggish to affect the eye as light, but recognizable through their chemical and heating effects. Now, all incandescent solid or liquid substances, and even gases ignited under great pressure, give what is called a continuous spectrum. That is to say, the light derived from them is of every conceivable hue. Sorted out with the prism, its tints merge imperceptibly one into the other, uninterrupted by any dark spaces. No colours, in short, are missing. But gases and vapours rendered luminous by heat emit rays of only a few tints, which accordingly form an interrupted spectrum, usually designated as one of lines or bands. And since these rays are perfectly definite and characteristic, not being the same for any two substances, it is easy to tell what kind of matter is concerned in producing them. We may suppose that the inconceivably minute particles which by their rapid thrilling agitate the ethereal medium so as to produce light are free to give out their peculiar tone of vibration only when floating apart from each other in gaseous form. But when crowded together into a condensed mass, the clear ring of the distinctive note is drowned, so to speak, in a universal molecular clang. Thus, prismatic analysis has no power to identify individual kinds of matter, except when they present themselves as glowing vapours. A spectrum is said to be reversed when lines previously seen bright on a dark background appear dark on a bright background. In this form it is equally characteristic of chemical composition, with the direct spectrum being due to absorption, as the latter is to emission. And absorption and emission are, by Kirchhoff's law, strictly correlative. This is easily understood by the analogy of sound, for just as a tuning fork responds to sound waves of its own pitch, but remains indifferent to those of any other, so those particles of matter whose nature it is, when set swinging by heat, to vibrate a certain number of times in a second, thus giving rise to light of a particular shade of colour, appropriate those same vibrations, and those only when transmitted past them, or, phrasing it otherwise, are opaque to them and transparent to all others. It should further be explained that the shape of the bright or dark spaces in the spectrum has nothing whatever to do with the nature of the phenomena. The lines and bands so frequently spoken of are seen as such for no other reason than because the light forming them is admitted through a narrow straight opening. Change that opening into a fine crescent or a sinuous curve, and the lines will at once appear as crescents or curves. Resuming in a sentence what has been already explained, we find that the prismatic analysis of the heavenly bodies was founded upon three classes of facts. First, the unmistakable character of the light given by each different kind of glowing vapour. Secondly, the identity of the light absorbed with the light emitted by each. Thirdly, the coincidence observed between rays missing from the solar spectrum and rays absorbed by various terrestrial substances. Thus, a realm of knowledge pronounced by Morinus in the 17th century, and no less dogmatically by Auguste Comte in the 19th, hopelessly out of reach of the human intellect, was thrown freely open, and the chemistry of the sun and stars took at once a leading place among the experimental sciences. The immediate increase of knowledge was not the chief result of Kirchhoff's labours. Still more important was the change in the scope and methods of astronomy, which, set on foot in 1852 by the detection of a common period affecting at once the spots on the sun and the magnetism of the earth, was extended and accelerated by the discovery of spectrum analysis. The nature of that change is concisely indicated by the heading of the present chapter. We would now ask our readers to endeavour to realize somewhat distinctly what is implied by the foundation of astronomical physics. Just 3 centuries ago, Kepler drew a forecast of what he called a physical astronomy, a science treating of the efficient causes of planetary motion and holding the key to the inner astronomy. What Kepler dreamed of and groped after, Newton realized. He showed the beautiful and symmetrical revolutions of the solar system to be governed by a uniformly acting cause, and that cause no other than the familiar force of gravity, which gives stability to all our terrestrial surroundings. The world under our feet was thus for the first time brought into physical connection with the worlds peopling space, and a very tangible relationship was demonstrated as existing between what used to be called the corruptible matter of the earth and the incorruptible matter of the heavens. This process of unification of the cosmos, this levelling of the celestial with the sublunary, was carried no farther until the fact unexpectedly emerged from a vast and complicated mass of observations that the magnetism of the earth is subject to subtle influences, emanating certainly from some and presumably from all of the heavenly bodies. The inference being thus rendered at least plausible that a force not less universal than gravity itself, but with whose modes of action we are as yet unacquainted, pervades the universe, and forms, it might be said, an intangible bond of sympathy between its parts. Now, for the investigation of this influence, two roads are open. It may be pursued by observation, either of the bodies from which it proceeds, or of the effects which it produces. That is to say, either by the astronomer or by the physicist, or better still, by both concurrently. Their acquisitions are mutually profitable, nor can either be considered as independent of the other. Any important accession to knowledge respecting the sun, for example, may be expected to cast a reflected light on the still obscure subject of terrestrial magnetism, while discoveries in magnetism, or its alter ego, electricity, must profoundly affect solar inquiries. The establishment of the new method of spectrum analysis drew far closer this alliance between celestial and terrestrial science. Indeed, they have come to merge so intimately one into the other that it is no easier to trace their respective boundaries than it is to draw a clear dividing line between the animal and vegetable kingdoms. Yet up to the middle of the last century, astronomy, while maintaining her strict union with mathematics, looked with indifference on the rest of the sciences. It was enough that she possessed the telescope and the calculus. Now the materials for her inductions are supplied by the chemist, the electrician, the inquirer into the most recondite mysteries of light and the molecular constitution of matter. She is concerned with what the geologist, the meteorologist, even the biologist has to say. She can afford to close her ears to no new truth of the physical order. Her position of lofty isolation has been exchanged for one of community and mutual aid. The astronomer has become, in the highest sense of the term, a physicist, while the physicist is bound to be something of an astronomer. This, then, is what is designed to be conveyed by the foundation of astronomical or cosmical physics. It means the establishment of a science of nature whose conclusions are not only presumed by analogy, but are ascertained by observation to be valid wherever light can travel and gravity is obeyed. A science by which the nature of the stars can be studied upon the earth, and the nature of the earth can be made better known by study of the stars. A science, in a word, which is, or aims at being, one and universal, even as nature, the visible reflection of the invisible highest unity, is one and universal. It is not too much to say that a new birth of knowledge has ensued. The astronomy so signally promoted by Bessel, the astronomy placed by Comte at the head of the hierarchy of the physical sciences, was the science of the movements of the heavenly bodies. And there were those who began to regard it as a science which, from its very perfection, had ceased to be interesting, whose tale of discoveries was told, and whose farther advance must be in the line of minute technical improvements, not of novel and stirring disclosures. But the science of the nature of the heavenly bodies is one only in the beginning of its career. It is full of the audacities, the inconsistencies, the imperfections, the possibilities of youth. It promises everything. It has already performed much. It will doubtless perform much more. The means at its disposal are vast and are being daily augmented. What has so far been secured by them, it must now be our task to extricate from more doubtful surroundings and place in due order before our readers. End of Part 2, Chapter 1, Part 2. Part 2, Chapter 2 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clarke. Chapter 2, Solar Observations and Theories, Part 1. The zeal with which solar studies have been pursued during the last half-century has already gone far to redeem the neglect of the two preceding ones. Since Schwab's discovery was published in 1851, observers have multiplied, new facts have been rapidly accumulated, and the previous comparative quiescence of thought on the great subject of the constitution of the sun has been replaced by a bewildering variety of speculations, conjectures, and more or less justifiable inferences. It is satisfactory to find this novel impulse not only shared, but to a large extent guided by our countrymen. William Rudder Dawes, one of many clergymen eminent in astronomy, observed in 1852, with the help of a solar eyepiece of his own devising, some curious details of spot structure. The umbra, heretofore taken for the darkest part of the spot, was seen to be suffused with a mottled nebulous illumination, in marked contrast with the striated appearance of the penumbra, while through this cloudy stratum a black opening permitted the eye to divine farther unfathomable depths beyond. The whole, thus disclosed, evidently the true nucleus, was found to be present in all considerable as well as in many small maculae. Again, the whirling motions of some of these objects were noticed by him. The remarkable form of one, sketched at Wateringbury in Kent, January 17, 1852, gave him the means of detecting and measuring a rotatory movement of the whole spot round the black nucleus at the rate of 100 degrees in 6 days. It appeared, he said, as if some prodigious ascending force of a whirlwind character, in bursting through the cloudy stratum and the two higher and luminous strata, had given to the whole a movement resembling its own. An interpretation founded, as is easily seen, on the Herschelian theory, then still in full credit. An instance of the same kind was observed by Mr. W. R. Burt in 1860, and cyclonic movements are now a recognized feature of sunspots. They are, however, as Father Secchi concluded from his long experience, but temporary and casual. Scarcely 3% of all spots visible exhibit the spiral structure, which should invariably result if a conflict of opposing or the friction of unequal currents were essential and not merely incidental to their origin. A whirlpool phase not unfrequently accompanies their formation, and may be renewed at periods of recrudescence or dissolution, but it is both partial and inconstant, sometimes affecting only one side of a spot, sometimes slackening gradually its movement in one direction to resume it after a brief pause in the opposite. Persistent and uniform motions, such as the analogy of terrestrial storms would absolutely require, are not to be found, so that the cyclonic theory of sunspots, suggested by Herschel in 1847 and urged from a different point of view by Faye in 1872, may be said to have completely broken down. The drift of spots over the sun's surface was first systematically investigated by Carrington, a self-constituted astronomer gifted with the courage and the instinct of thoughtful labour. Born at Chelsea in May 1826, Richard Christopher Carrington entered Trinity College, Cambridge, in 1844. He was intended for the Church, but Professor Challis's lectures diverted him to astronomy, and he resolved, as soon as he had taken his degree, to prepare with all possible diligence to follow his new vocation. His father, who was a brewer on a large scale at Brentford, offered no opposition. Ample means were at his disposal. Nevertheless, he chose to serve an apprenticeship of 3 years as observer in the University of Durham, as though his sole object had been to earn a livelihood. He quitted the post only when he found that its restricted opportunities offered no farther prospect of self-improvement. He now built an observatory of his own at Redhill in Surrey, with the design of completing Bessel's and Argelander's survey of the northern heavens by adding to it the circumpolar stars omitted from their view. This project, successfully carried out between 1854 and 1857, had another and still larger one superposed upon it before it had even begun to be executed. In 1852, while the Redhill Observatory was in course of erection, the discovery of the coincidence between the sun-spot and magnetic periods was announced. Carrington was profoundly interested, and devoted his enforced leisure to the examination of records, both written and depicted, of past solar observations. Struck with their fragmentary and inconsistent character, he resolved to appropriate, as he said, by close and methodical research, the 11-year period next ensuing. He calculated rightly that he should have the field pretty nearly to himself, for many reasons conspired to make public observatories slow in taking up new subjects, and amateurs with freedom to choose and means to treat them effectually were scarcer then than they are now. The execution of this laborious task was commenced November 9, 1853. It was intended to be merely a paragon, a second subject upon which daylight energies might be spent, while the hours of night were reserved for cataloguing those stars that are bereft of the baths of ocean. Its results, however, proved of the highest interest, although the vicissitudes of life barred the completion in its full integrity of the original design. By the death in 1858 of the elder Carrington, the charge of the brewery devolved upon his son, and eventually absorbed so much of his care that it was found advisable to bring the solar observations to a premature close on March 24, 1861. His scientific life may be said to have closed with them. Attacked 4 years later with severe and, in its results, permanent illness, he disposed of the Brentwood business and withdrew to Churt, near Farnham in Surrey. There, in a lonely spot on the top of a detached conical hill known as the Devil's Jump, he built a second observatory and erected an instrument which he was no longer able to use with pristine effectiveness. And there, November 27, 1875, he died of the rupture of a blood vessel on the brain before he had completed his 50th year. His observations of sunspots were of a geometrical character. They concerned positions and movements, leaving out of sight physical peculiarities. Indeed, the prudence with which he limited his task to what came strictly within the range of his powers to accomplish was one of Carrington's most valuable qualities. The method of his observations, moreover, was chosen with the same practical sagacity as their objects. As early as 1847, Sir John Herschel had recommended the daily self-registration of sunspots, and he enforced the suggestion with more immediate prospect of success in 1854. The art of celestial photography, however, was even then in a purely tentative stage, and Carrington wisely resolved to waste no time on dubious experiments, but employ the means of registration and measurement actually at his command. These were very simple, yet very effective. To the helioscope employed by Father Scheiner 2 centuries and a quarter earlier, a species of micrometer was added. The image of the sun was projected upon a screen by means of a firmly clamped telescope, in the focus of which were placed 2 cross wires, forming angles of 45 degrees with the meridian. The 6 instants were then carefully noted, at which these were met by the edges of the disk as it traversed the screen, and by the nucleus of the spot to be measured. A short process of calculation then gave the exact position of the spot as referred to the sun's centre. From a series of 5,290 observations made in this way, together with a great number of accurate drawings, Carrington derived conclusions of great importance on each of the 3 points which he had proposed to himself to investigate. These were the law of the sun's rotation, the existence and direction of systematic currents, and the distribution of spots on the solar surface. Grave discrepancies were early perceived to exist between determinations of the sun's rotation by different observers. Galileo, with comfortable generality, estimated the period at about a lunar month. Scheiner at 27 days. Cassini in 1678 made it 25.58. Delambre in 1775 no more than 25 days. Later inquiries brought these divergences within no more tolerable limits. Langier's result of 25.34 days, obtained in 1841, enjoyed the highest credit, yet it differed widely in one direction from that of Böhm, 1852, giving 25.52 days, and in the other from that of Ctesias, 1846, giving 25.09 days. Now, the cause of these variations was really obvious from the first, although for a long time strangely overlooked. Scheiner pointed out in 1630 that different spots gave different periods, adding the significant remark that one at a distance from the solar equator revolved more slowly than those nearer to it. But the hint was wasted. For upwards of 2 centuries, ideas on the subject were either retrograde or stationary. What were called the proper motions of spots were, however, recognized by Schroeter, and utterly baffled Langier, who despaired of obtaining any concordant result as to the sun's rotation except by taking the mean of a number of discordant ones. At last, in 1855, a valuable course of observations made at Capo di Monte, Naples, in 1845-6 enabled C.H.F. Peters to set in the clearest light the insecurity of determinations based on the assumption of fixity in objects plainly affected by movements uncertain both in amount and direction. Such was the state of affairs when Carrington entered upon his task. Everything was in confusion. The most that could be said was that the confusion had come to be distinctly admitted and referred to its true source. What he discovered was this, that the sun, or at least the outer shell of the sun visible to us, has no single period of rotation, but drifts round, carrying the spots with it at a rate continually accelerated from the poles to the equator. In other words, the time of axial revolution is shortest at the equator and lengthens with increase of latitude. Carrington devised a mathematical formula by which the rate or law of this lengthening was conveniently expressed, but it was a purely empirical one. It was a concise statement, but implied no physical interpretation. It summarized, but did not explain, the facts. An assumed mean period for the solar rotation of 25.38 days, 25 days, 9 hours, very nearly, was thus found to be actually conformed to only in 2 parallels of solar latitude, 14 degrees north and south, while the equatorial period was slightly less than 25, and that of latitude 50 degrees rose to 27 days and a half. These curious results gave quite a new direction to ideas on solar physics. The other 2 elements of the sun's rotation were also ascertained by Carrington with hitherto unattained precision. He fixed the inclination of its axis to the ecliptic at 82 degrees 45 minutes, the longitude of the ascending node at 73 degrees 40 minutes, for the epoch 1850 A.D. These data, which have scarcely yet been improved upon, suffice to determine the position in space of the sun's equator. Its north pole is directed towards a star in the coils of the Dragon, midway between Vega and the pole star. Its plane intersects that of the earth's orbit in such a way that our planet finds itself in the same level on or about the 3rd of June and the 5th of December, when any spots visible on the disk cross it in apparently straight lines. At other times the paths pursued by them seem curved downward to an observer in the northern hemisphere between June and December, upward between December and June. A singular peculiarity in the distribution of sunspots emerged from Carrington's studies at the time of the minimum of 1856. 2 broad belts of the solar surface, as we have seen, are frequented by them, of which the limits may be put at 6 degrees and 35 degrees of north and south latitude. Individual equatorial spots are not uncommon, but nearer to the poles than 35 degrees they are a rare exception. Carrington observed, as an extreme instance, in July 1858, one in south latitude 44 degrees, and Peters in June 1846 watched during several days a spot in 50 degrees 24 minutes north latitude. But beyond this no true macula has ever been seen, for Lahir's reported observation of one in latitude 70 degrees is now believed to have had its place on the solar globe erroneously assigned, and the veiled spots described by Trouvelot in 1875 as occurring within 10 degrees of the pole can only be regarded as, at the most, the same kind of disturbance in an undeveloped form. But the novelty of Carrington's observations consisted in the detection of certain changes in distribution concurrent with the progress of the 11-year period. As the minimum approached, the spot zones contracted towards the equator, and there finally vanished. Then, as if by a fresh impulse, spots suddenly reappeared in high latitude, and spread downwards with the development of the new phase of activity. Scarcely had this remark been made public when Wolf found a confirmation of its general truth in Böhm's observations during the years 1833 to 36, and a perfectly similar behaviour was noted both by Spörer and Secchi at the minimum epoch of 1867. The ensuing period gave corresponding indications, and it may now be looked upon as established that the spot zones close in towards the equator with the advance of each cycle, their activity culminating, as a rule, in a mean latitude of about 16 degrees, and expiring when it is reduced to 6 degrees. Before this happens, however, a completely new disturbance will have manifested itself some 35 degrees north and south of the equator, and will have begun to travel over the same course as its predecessor. Each series of sunspots is thus, to some extent, overlapped by the succeeding one, so that while the average interval from one maximum to the next is 11 years, the period of each distinct wave of agitation is 12 or 14. Curious evidence of the retarded character of the maximum of 1883 to 4 was to be found in the unusually low latitude of the spot zones when it occurred, their movement downward having gone on regularly while the crisis was postponed. Its final symptoms were hence displaced locally as well as in time. The law of zones was duly obeyed at the minima of 1890 and 1901, and Spörer found evidence of conformity to it so far back as 1619. His researches, however, also showed that it was in abeyance during some 70 years previously to 1716, during which period sunspots remained persistently scarce, and auroral displays were feeble and infrequent even in high northern latitudes. An unaccountable suspension of solar activity is, in fact, indicated. Gustav Spörer, born at Berlin in 1822, began to observe sunspots with the view of assigning the law of solar rotation in December 1860. His assiduity and success with limited means attracted attention, and a government endowment was procured for his little solar observatory at Anklam in Pomerania, the Crown Prince, afterwards Emperor Frederick, adding a 5-inch refractor to its modest equipment. Unaware of Carrington's discovery, not made known until January 1859, he arrived at and published in June 1861 a similar conclusion as to the equatorial quickening of the sun's movement on its axis. Appointed observer in the new astrophysical establishment at Potsdam in 1874, he continued his sunspot determinations there for 20 years and died July 7, 1895. The time had now evidently come for a fundamental revision of current notions respecting the nature of the sun. Herschel's theory of a cool, dark, habitable globe, surrounded by and protected against the radiations of a luminous and heat-giving envelope, was shattered by the first dicta of spectrum analysis. Traces of it may be found for a few years subsequent to 1859, but they are obviously survivals from an earlier order of ideas doomed to speedy extinction. It needs only a moment's consideration of the meaning at last found for the Fraunhofer lines to see the incompatibility of the new facts with the old conceptions. They implied not only the presence near the sun as glowing vapours of bodies highly refractory to heat, but that these glowing vapours formed the relatively cool envelope of a still hotter internal mass. Kirchhoff accordingly included in his great memoir on the solar spectrum, read before the Berlin Academy of Sciences, July 11, 1861, an exposition of the views on the subject to which his memorable investigations had led him. They may be briefly summarized as follows. Since the body of the sun gives a continuous spectrum, it must be either solid or liquid, while the interruptions in its light prove it to be surrounded by a complex atmosphere of metallic vapours somewhat cooler than itself. Spots are simply clouds due to local depressions of temperature, differing in no respect from terrestrial clouds, except as regards the kinds of matter composing them. These sun clouds take their origin in the zones of encounter between polar and equatorial currents in the solar atmosphere. This explanation was liable to all the objections urged against the cumulus theory on the one hand and the trade wind theory on the other. Setting aside its propounder, it was consistently upheld perhaps by no man eminent in science except Spörer, and his advocacy of it proved ineffective to secure its general adoption. Monsieur Faye of the Paris Academy of Sciences was the first to propose a coherent scheme of the solar constitution covering the whole range of new discovery. The fundamental ideas on the subject now in vogue here made their first connected appearance. Much indeed remained to be modified and corrected, but the transition was finally made from the old to the new order of thought. The essence of the change may be conveyed in a single sentence. The sun was thenceforth regarded not as a mere heated body, or still more remotely from the truth as a cool body unaccountably spun round with a cocoon of fire, but as a vast heat-radiating machine. The terrestrial analogy was abandoned in one more particular besides that of temperature. The solar system of circulation, instead of being adapted like that of the earth to the distribution of heat received from without, was seen to be directed towards the transportation towards the surface of the heat contained within. Polar and equatorial currents tending to a purely superficial equalization of temperature were replaced by vertical currents bringing up successive portions of the intensely heated interior mass, to contribute their share in turn to the radiation into space, which might be called the proper function of a sun. Faye's views, which were communicated to the Academy of Sciences January 16, 1865, were avowedly based on the anomalous mode of solar rotation discovered by Carrington. This may be regarded either as an acceleration increasing from the poles to the equator, or as a retardation increasing from the equator to the poles, according to the rate of revolution we choose to assume for the unseen nucleus. Faye preferred to consider it a retardation produced by ascending currents continually left behind as the sphere widened in which the matter composing them was forced to travel. He further supposed that the depth from which these vertical currents rose, and consequently the amount of retardation effected by their ascent to the surface, became progressively greater as the poles were approached, owing to the considerable flattening of the spheroidal surface from which they started. But the adoption of this expedient has been shown to involve inadmissible consequences. The extreme internal mobility betrayed by Carrington's and Spörer's observations led to the inference that the matter composing the sun was mainly or wholly gaseous. This had already been suggested by Father Secchi a year earlier, and by Sir John Herschel in April 1864. But it first obtained general currency through Faye's more elaborate presentation. A physical basis was afforded for the view by Cagnard de la Tour's experiments in 1822, proving that under conditions of great heat and pressure, the vaporous state was compatible with a very considerable density. The position was strengthened when Andrews showed in 1869 that above a fixed limit of temperature, varying for different bodies, true liquefaction is impossible, even though the pressure be so tremendous as to retain the gas within the same space that enclosed the liquid. The opinion that the mass of the sun is gaseous now commands a very general assent, although the gaseity admitted is of such a nature as to afford the consistence rather of honey or pitch than of the aeriform fluids with which we are familiar. On another important point, the course of subsequent thought was powerfully influenced by Faye's conclusions in 1865. Arago somewhat hastily inferred from experiments with the polariscope the wholly gaseous nature of the visible disk of the sun. Kirchhoff, on the contrary, believed erroneously, as we now know, that the brilliant continuous spectrum derived from it proved it to be a white-hot solid or liquid. Herschel and Secchi indicated a cloud-like structure as that which would best harmonize the whole of the evidence at command. The novelty introduced by Faye consisted in regarding the photosphere no longer as a defined surface in the mathematical sense, but as a limit to which, in the general fluid mass, ascending currents carry the physical or chemical phenomena of incandescence. Uprushing floods of mixed vapours with strong affinities, say of calcium or sodium and oxygen, at last attain a region cool enough to permit their combination. A fine dust of solid or liquid compound particles, of lime or soda, for example, there collects into the photospheric clouds, and descending by its own weight in torrents of incandescent rain, is dissociated by the fierce heat below, and replaced by ascending and combining currents of similar constitution. This first attempt to assign the part played in cosmical physics by chemical affinities was marked by the importation into the theory of the sun of the now familiar phrase dissociation. It is indeed tolerably certain that no such combinations as those contemplated by Faye occur at the photospheric level, since the temperature there must be enormously higher than would be needed to reduce all metallic earths and oxides. But molecular changes of some kind, dependent perhaps in part upon electrical conditions, in part upon the effects of radiation into space, most likely replaced them. The conjecture was emitted by Dr. Johnstone Stoney in 1867 that the photospheric clouds are composed of carbon particles precipitated from their mounting vapour just where the temperature is lowered by expansion and radiation to the boiling point of that substance. But this view, though countenanced by Ångström and advocated by Hastings of Baltimore and other authorities, is open to grave objections. In Faye's theory, sunspots were regarded as simply breaks in the photospheric clouds, where the rising currents had strength to tear them asunder. It followed that they were regions of increased heat, regions, in fact, where the temperature was too high to permit the occurrence of the precipitations to which the photosphere is due. Their obscurity was attributed, as in Dr. Brester's more recent Théorie du Soleil, to deficiency of emissive power. Yet here the verdict of the spectroscope is adverse and irreversible. After every deduction, however, has been made, we still find that several ideas of permanent value were embodied in this comprehensive sketch of the solar constitution. The principal of these were, first, that the sun is a mainly gaseous body; secondly, that its stores of heat are rendered available at the surface by means of vertical convection currents, by the bodily transport, that is to say, of intensely hot matter upward and of comparatively cool matter downward. Thirdly, that the photosphere is a surface of condensation, forming the limit set by the cold of space to this circulating process, and that a similar formation must attend, at a certain stage, the cooling of every cosmical body. To Warren de la Rue belongs the honour of having obtained the earliest results of substantial value in celestial photography. What had been done previously was interesting in the way of promise, but much could not be claimed for it as actual performance. Some pioneering experiments were made by Dr. J. W. Draper of New York in 1840, resulting in the production of a few moon pictures 1 inch in diameter, but slight encouragement was derived from them, either to himself or others. Bond of Cambridge, U.S., however, secured in 1850 with the Harvard 15-inch refractor that daguerreotype of the moon with which the career of extraterrestrial photography may be said to have formally opened. It was shown in London at the Great Exhibition of 1851 and determined the direction of de la Rue's efforts. Yet it did little more than prove the art to be a possible one. Warren de la Rue was born in Guernsey in 1815 and died in London April 19, 1889. Educated at the École Sainte-Barbe in Paris, he made a large fortune as a paper manufacturer in England, and thus amply and early provided the material supplies for his scientific campaign. Towards the end of 1853 he took some successful lunar photographs. They were remarkable as the first examples of the application to astronomical light painting of the collodion process invented by Archer in 1851, and also of the use of reflectors. De la Rue's was one of 13 inches constructed by himself for that kind of work. The absence of a driving apparatus was, however, very sensibly felt. The difficulty of moving the instrument by hand so as accurately to follow the moon's apparent motion being such as to cause the discontinuance of the experiments until 1857, when the want was supplied. De la Rue's new observatory, built in that year at Cranford, was expressly dedicated to celestial photography, and there he applied to the heavenly bodies the stereoscopic method of obtaining relief, and turned his attention to the delicate business of photographing the sun. A solar daguerreotype was taken at Paris, April 2, 1845, by Foucault and Fizeau, acting on a suggestion from Arago, but the attempt, though far from being unsuccessful, does not at that time seem to have been repeated. Its great difficulty consisted in the enormous light power of the object to be represented, rendering an inconceivably short period of exposure indispensable, under pain of getting completely burnt-up plates. In 1857, de la Rue was commissioned by the Royal Society to construct an instrument specially adapted to the purpose for the Kew Observatory. The resulting photoheliograph may be described as a small telescope of 3½ inches aperture and 50 focus, with a plate holder at the eye end, guarded in front by a spring slide, the rapid movement of which across the field of view secured for the sensitive plate a virtually instantaneous exposure. By its means the first solar light pictures of real value were taken, and the autographic record of the solar condition recommended by Sir John Herschel was commenced and continued at Kew during 14 years, 1858 to 72. The work of photographing the sun is now carried on in every quarter of the globe, from Mauritius to Massachusetts, and the days are few indeed on which the self-betrayal of the camera can be evaded by our chief luminary. In the year 1883, the incorporation of Indian with Greenwich pictures afforded a record of the state of the solar surface on 340 days, and 364 were similarly provided for in 1897 and 1899. The conclusions arrived at by photographic means at Kew were communicated to the Royal Society in a series of papers drawn up jointly by de la Rue, Balfour Stewart, and Benjamin Lowry in 1865 and subsequent years. They influenced materially the progress of thought on the subject they were concerned with. End of Chapter 2, Part 1. Part 2, Chapter 2 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary CLERKE. Chapter 2, Solar Observations and Theories, Part 2. By its rotation, the Sun itself offers opportunities for bringing the stereoscope to bear upon it. Two pictures taken at an interval of 26 minutes show just the amount of difference needed to give, by their combination, the maximum effect of solidity. De la Rue thus obtained in 1861 a stereoscopic view of a sunspot and surrounding faculae, representing the various parts in their true mutual relations. I have ascertained in this way, he wrote, that the faculae occupy the highest portions of the sun's photosphere, the spots appearing like holes in the penumbrae, which appeared lower than the regions surrounding them. In one case, parts of the faculae were discovered to be sailing over a spot apparently at some considerable height above it. Thus, Wilson's inference as to the depressed nature of spots received, after the lapse of not far from a century, proof of the most simple, direct, and convincing kind. A careful application of Wilson's own geometrical test gave results only a trifle less decisive. Of 694 spots observed, 78% showed, as they traversed the disk, the expected effects of perspective, and their absence in the remaining 22% might be explained by internal commotions producing irregularities of structure. The absolute depth of spot cavities, at least of their sloping sides, was determined by Father Secchi through measurement of the parallax of profundity, that is, of apparent displacements attendant on the sun's rotation due to depression below the sun's surface. He found that in every case it fell short of 4,000 miles and averaged not more than 1,321, corresponding on the terrestrial scale to an excavation in the earth's crust of 1 1/5 miles. Of late, however, the reality of even this moderate amount of depression has been denied. Mr. Hallett's persevering observations, extending over a third of a century, the results of which were presented to the Royal Astronomical Society in December 1894, availed to shatter the consensus of opinion which had so long been maintained on the subject of spot structure. It has become impossible any longer to hold that it is uniformly cavernous, and what seem like actually protruding umbrae are occasionally vouched for on unimpeachable authority. We can only infer that the forms of sunspots are really more various than had been supposed, that they are peculiarly subject to disturbance, and that the level of the nuclei may rise and fall during the phases of commotion like lavas within volcanic craters. The opinion of the Kew observers as to the nature of such disturbances was strongly swayed by another curious result of the statistical method of inquiry. They found that of 1,137 instances of spots accompanied by faculae, 584 had those faculae chiefly or entirely on the left. 508 showed a nearly equal distribution, while 45 only had fasculous appendages mainly on the right side. Now, the rotation of the sun as we see it is performed from left to right, so that the marked tendency of the faculae was a lagging one. This was easily accounted for by supposing the matter composing them to have been flung upwards from a considerable depth, whence it would reach the surface with the lesser absolute velocity belonging to a smaller circle of revolution, and would consequently fall behind the cavities or spots formed by its abstraction. An attempt, it is true, made by M. Wilsing at Potsdam in 1888 to determine the solar rotation from photographs of faculae had an outcome inconsistent with this view of their origin. They unexpectedly gave a uniform period. No trace of the retardation poleward from the equator shown by the spots could be detected in their movements. But the experiment was obviously inconclusive, and M. Stratonoff's repetition of it with ampler materials gave a full assurance that faculae rotate like spots spots in periods lengthening as latitude augments. The ideas of M. Faye were on two fundamental points contradicted by the Kew investigators. He held spots to be regions of uprush and of heightened temperature. They believed their obscurity to be due to a downrush of comparatively cool vapours. Now M. Chacornac, observing at Villeurbanne, March 6, 1865, saw floods of photospheric matter visibly precipitating themselves into the abyss opened by a great spot, and carrying with them small neighbouring maculae. Similar instances were repeatedly noted by Father Secchi, who considered the existence of a kind of suction in spots to be quite beyond question. The tendency in their vicinity, to put it otherwise, is centripetal, not centrifugal, and this alone seems to negative the supposition of a central uprush. A fresh witness was by this time at hand, the application of the spectroscope to the direct examination of the sun's surface dates from March 4, 1866, when Sir Norman Lockyer, to give him his present title, undertook an inquiry into the cause of the darkening in spots. It was made possible by the simple device of throwing upon the slit of the spectroscope an image of the sun, any part of which could be subjected to special scrutiny, instead of, as had hitherto been done, admitting rays from every portion of its surface indiscriminately. The answer to the inquiry was prompt and unmistakable, and was again in this case adverse to the French theorist's view. The obscurations in question were found to be produced by no deficiency of emissive power, but by an increase of absorptive action. The background of variegated light remains unchanged, but more of it is stopped by the interposition of a dense mass of relatively cool vapours. The spectrum of a sunspot is crossed by the same set of multitudinous dark lines, with some minor differences visible in the ordinary solar spectrum. We must then conclude that the same vapours, speaking generally, which are dispersed over the unbroken solar surface, are accumulated in the umbral cavity, the compression incident to such accumulation being betrayed by the thickening of certain lines of absorption. But there is also a general absorption, extending almost continuously from one end of the spot spectrum to the other. Using, however, a spectroscope of exceptionally high dispersive power, Professor Young of Princeton, New Jersey, succeeded in 1883 in resolving the supposed continuous obscurity of spot spectra into a countless multitude of fine dark lines set very close together. Their structure was seen still more perfectly about 5 years later by M. Dunet, director of the Upsala Observatory, who traced, besides some shadowy vestiges of the crowded doublets and triplets forming the array, from the spots on to the general solar surface. They ceased to be separable in the blue part of the spectrum, and the ultraviolet radiations of spots show nothing distinctive. As to the movements of the constipated vapours forming spots, the spectroscope is also competent to supply information. The principle of the method by which it is procured will be explained farther on. Suffice it here to say that the transport at any considerable velocity to or from the eye of the gaseous material giving bright or dark lines can be measured by the displacement of such lines from their previously known normal positions. In this way, movements have been detected in or above spots of enormous rapidity, ranging up to 320 miles per second, but the result so far has been to negative the ascription to them of any systematic direction. Uprushes and downrushes are doubtless, as Father Corti remarks, correlated phenomena in the production of a sunspot, but neither seem to predominate as part of its regular internal economy. The same kind of spectroscopic evidence tells heavily against a theory of sunspots started by Faye in 1872. He had been foremost in pointing out that the observations of Carrington and Spörer absolutely forbade the supposition that any phenomenon at all resembling our trade winds exists in the sun. They showed indeed that beyond the parallels of 20 degrees there is a general tendency in spots to a slow poleward displacement, while within that zone they incline to approach the equator, but their proper movements gave no evidence of uniformly flowing currents in latitude. The systematic drift of the photosphere is strictly a drift in longitude. Its direction is everywhere parallel to the equator. This fact being once clearly recognized, the solar tornado hypothesis at once fell to pieces. But M. Faye perceived another source of vorticose motion in the unequal rotating velocities of contiguous portions of the photosphere. The pores with which the whole surface of the sun is studded he took to be the smaller eddies resulting from these inequalities, the spots to be such eddies developed into whirlpools. It only needs to thrust a stick into a stream to produce the kind of effect designated, and it happens that the differences of angular movement adverted to attain a maximum just about the latitudes where spots are most frequent and conspicuous. There are, however, grave difficulties in identifying the two kinds of phenomena. One, already mentioned, is the total absence of the regular swirling motion in a direction contrary to that of the hands of a watch north of the solar equator, in the opposite sense south of it, which should impress itself upon every lineament of a sunspot if the cause assigned were a primary producing and not merely, as it possibly may be, a secondary determining one. The other, pointed out by Young, is that the cause is inadequate to the effect. The difference of movement, or relative drift, supposed to occasion such prodigious disturbances, amounts at the utmost for two portions of the photosphere 123 miles apart to about 5 yards a minute. Thus the friction of contiguous sections must be quite insignificant. A view better justified by observation was urged by Secchi in and after the year 1872, and was presented in an improved form by Professor Young in his excellent little book on the Sun, published in 1882. Spots are manifestly associated with violent eruptive action, giving rise to the faculae and prominences which usually garnish their borders. It is accordingly contended that upon the withdrawal of matter from below by the flinging up of a prominence must ensue a sinking in of the surface into which the partially cooled erupted vapours rush and settle, producing just the kind of darkening by increased absorption told of by the spectroscope. Round the edges of the cavity, the rupture of the photospheric shell will form lines of weakness, provocative of further eruptions, which will in their turn deepen and enlarge the cavity. The phenomenon thus tends to perpetuate itself until equilibrium is at last restored by internal processes. A sunspot might then be described as an inverted terrestrial volcano, in which the outbursts of heated matter take place on the borders instead of at the center of the crater, while the cooled products gather in the center instead of at the borders. But on the earth, the solid crust forcibly represses the steam gathering beneath until it has accumulated strength for an explosion, while there is no such restraining power that we know of in the sun. Zöllner, indeed, adapted his theory of the solar constitution to the special purpose of procuring it, yet with very partial success, since almost every new fact has proved adverse to his assumptions. Volcanic action is essentially spasmodic. It implies habitual constraint, varied by temporary outbreaks, inconceivable in a gaseous globe such as we believe the sun to be. If the volcanic hypothesis represented the truth, no spot could possibly appear without a precedent eruption. The real order of the phenomenon, however, is exceedingly difficult to ascertain, nor is it perhaps invariable. Although in most cases the opening shows first, that may be simply because it is more easily seen. According to Father Sidgreaves, the disturbance has then already passed the incipient stage. He considers it indeed highly probable that the preparatory sign of a new spot is always a small, bright patch of facula. This sequence, if established, would be fatal to Lockyer's theory of sunspots, communicated to the Royal Society May 6, 1886, and further developed some months later in his work on the chemistry of the sun. Spots are represented in it as incidental to a vast system of solar atmospheric circulation, starting with the polar out and up flows indicated by observations during some total eclipses, and eventuating in the plunge downward from great heights upon the photosphere of prodigious masses of condensed materials. From these falls result primarily spots, secondarily through the answering uprushes, in which chemical and mechanical forces cooperate, their girdles of flame prominences. The evidence is, however, slight that such a circulatory flow as would be needed to maintain this supposed cycle of occurrences really prevails in the sun's atmosphere, and a similar objection applies to an anticyclonic theory, so to designate it, elaborated by Egon von Appolzer in 1893. August Schmidt's optical rationale of solar phenomena was, on the other hand, a complete novelty both in principle and development. Attractive to speculators from its recondite nature and far-reaching scope, it by no means commended itself to practical observers, intolerant of finding the all but palpable realities of their daily experience dealt with as illusory products of circular refraction. A singular circumstance has now to be recounted. On the 1st of September, 1859, while Carrington was engaged in his daily work of measuring the positions of sunspots, he was startled by the sudden appearance of two patches of peculiarly intense light within the area of the largest group visible. His first idea was that a ray of unmitigated sunshine had penetrated the screen employed to reduce the brilliancy of the image. But having quickly convinced himself to the contrary, he ran to summon an additional witness of an unmistakably remarkable occurrence. On his return, he was disappointed to find the strange luminous outburst already on the wane. Shortly afterwards, the last trace vanished. Its entire duration was 5 minutes, from 11.18 to 11.23 a.m. Greenwich time, and during those 5 minutes it had traversed a space estimated at 35,000 miles. No perceptible change took place in the details of the group of spots visited by this transitory conflagration, which, it was accordingly inferred, took place at a considerable height above it. Carrington's account was precisely confirmed by an observation made at Highgate. Mr. R. Hodgson described the appearance seen by him as that of a very brilliant star of light, much brighter than the sun's surface, most dazzling to the protected eye, illuminating the upper edges of the adjacent spots and streaks, not unlike, in effect, the edging of the clouds at sunset. This unique phenomenon seemed as if specially designed to accentuate the inference of a sympathetic relation between the earth and the sun. From the 28th of August to the 4th of September, 1859, a magnetic storm of unparalleled intensity, extent, and duration was in progress over the entire globe. Telegraphic communication was everywhere interrupted, except indeed that it was in some cases found practicable to work the lines without batteries, by the agency of the earth currents alone. Sparks issued from the wires, gorgeous aurorae draped the skies in solemn crimson over both hemispheres and even within the tropics. The magnetic needle lost all trace of continuity in its movements and darted to and fro as if stricken with inexplicable panic. The coincidence was drawn even closer. At the very instant of the solar outburst, witnessed by Carrington and Hodgson, the photographic apparatus at Kew registered a marked disturbance of all the three magnetic elements, while shortly after the ensuing midnight the electric agitation culminated, thrilling the earth with subtle vibrations and lighting up the atmosphere from pole to pole with the coruscating splendors which perhaps dimly recall the times when our ancient planet itself shone as a star. Here, then, at least, the sun was, in Professor Balfour Stewart's phrase, taken in the act of stirring up terrestrial commotions, nor have instances since been wanting of an indubitable connection between outbreaks of individual spots and magnetic disturbances. 4 such were registered in 1882, and symptoms of the same kind, including the beautiful rose aurora, marked the progress across the sun of the enormous spot group of February 1892, the largest ever recorded at Greenwich. This extraordinary formation, which covered about 1/300th of the sun's disk, survived through 5 complete rotations. It was remarkable for a persistent drift in latitude, its place altering progressively from 17 degrees to 30 degrees south of the solar equator. Again, the central passage of an enormous spot on September 9, 1898, synchronized with a sharp magnetic disturbance and brilliant aurora, and the coincidence was substantially repeated in March 1899, when it was emphasized by the prevalent cosmic calm. The theory of the connection is indeed far from clear. Lord Kelvin in 1892 pronounced against the possibility of any direct magnetic action by the sun upon the earth on the ground of its involving an extravagant output of energy. But the fact is unquestionable that, in Professor Bigelow's words, abnormal agitations affect the sun and the earth as a whole and at the same time. The nearer approach to the event of September 1, 1859, was photographically observed by Professor George E. Hale at Chicago, July 15, 1892. An active spot in the southern hemisphere was the scene of this curiously sudden manifestation. During an interval of 12 minutes between 2 successive exposures, a bridge of dazzling light was found to have spanned the boundary line dividing the twin nuclei of the spot, and these, after another 27 minutes, were themselves almost obliterated by an overflow of far-spreading brilliancy. Yet 2 hours later, no trace of the outburst remained, the spot and its attendant faculae remaining just as they had been previously to its occurrence. Unlike that seen by Carrington, it was accompanied by no exceptional magnetic phenomena, although a storm set in next day. Possibly a terrestrial analogue to the former might be discovered in the auroral beam, which traversed the heavens during a vivid display of polar lights, November 17, 1882, and shared, there is every reason to believe, their electrical origin and character. Meantime, M. Rudolf Wolf, transferred to the direction of the Zurich Observatory, where he died December 6, 1893, had relaxed none of his zeal in the investigation of sun-spot periodicity. A laborious revision of the entire subject, with the aid of fresh materials, led him in 1859 to the conclusion that while the mean period differed little from that arrived at in 1852 of 11.11 years, very considerable fluctuations on either side of that mean were rather the rule than the exception. Indeed, the phrase sunspot period must be understood as fitting very loosely the great fact it is taken to represent, so loosely that the interval between 2 maxima may rise to 16½ or sink below 7½ years. In 1861, Wolf showed, and the remark was fully confirmed at Kew, that the shortest periods brought the most acute crises, and vice versa, as if for each wave of disturbance a strictly equal amount of energy were available, which might spend itself lavishly and rapidly, or slowly and parsimoniously, but could in no case be exceeded. The further inclusion of recurring solar commotions within a cycle of 55½ years was simultaneously pointed out, and Hermann Fritz showed soon afterwards that the aurora borealis is subject to an identical double periodicity. The same inquirer has more recently detected both for aurorae and sunspots a secular period of 222 years, and the Kew observations indicate for the latter oscillations accomplished within 26 and 24 days, depending most likely upon the rotation of the sun. This is certainly reflected in magnetic and perhaps in auroral periodicity. The more closely, in fact, spot fluctuations are looked into, the more complex they proved. Maxima of one order are superposed upon or in part neutralized by maxima of another order. Originating causes are masked by modifying causes. The larger waves of the commotion are indented with minor undulations, and these again crisped with tiny ripples, while the whole rises and falls with the swell of the great secular wave, scarcely perceptible in its progress because so vast in scale. The idea that solar maculation depends in some way upon the position of the planets occurred to Galileo in 1612. It has been industriously sifted by a whole bevy of modern solar physicists. Wolf in 1859 found reason to believe that the 11-year curve is determined by the action of Jupiter, modified by that of Saturn, and diversified by influences proceeding from the Earth and Venus. Its tempting approach to agreement with Jupiter's period of revolution round the sun indeed irresistibly suggested a causal connection, yet it does not seem that the most skilful coaxing of figures can bring about a fundamental harmony. Carrington pointed out in 1863 that while during 8 successive periods from 1770 downwards there were approximate coincidences between Jupiter's aphelion passages and sunspot maxima, the relation had been almost exactly reversed in the 2 periods preceding that date, and Wolf himself finally concluded that the Jovian origin must be abandoned. M. Dupontchel's prediction, nevertheless, of an abnormal retardation of the maximum due in 1881 through certain peculiarities in the positions of Uranus and Neptune about the time it fell due, was partially verified by the event, since after an abortive phase of agitation in April 1882, the final outburst was postponed to January 1894. The interval was thus 13.5 instead of 11.1 years, and it is noticeable that the delay affected chiefly the southern hemisphere. Alternations of activity in the solar hemispheres were indeed a marked feature of the maximum of 1884, which in Mr. Fay's view derived thence its indecisive character, while sharp, strong crises arise with the simultaneous advance of agitation north and south of the solar equator. The curve of magnetic disturbance followed with its usual strict fidelity the anomalous fluctuations of the sunspot curve. The ensuing minimum occurred early in 1889 and was succeeded in 1894 by a maximum slightly less feeble than its predecessor. It cannot be said that much progress has been made towards the disclosure of the cause or causes of the sun-spot cycle. No external influence adequate to the effect has at any rate yet been pointed out. Most thinkers on this difficult subject provide a quasi-explanation of the periodicity in question through certain assumed vicissitudes affecting internal processes. Sir Norman Lockyer and E. von Oppolzer reached the same end by establishing self-compensatory fluctuations in the solar atmospheric circulation. Dr. Schuster resorts to changes in the electrical conductivity of space near the sun. In all these theories, however, the course of transition is arbitrarily arranged to suit a period, which imposes itself as a fact, peremptorily claiming admittance, while obstinately defying explanation. The question so much discussed as to the influence of sunspots on weather does not admit of a satisfactory answer. The facts of meteorology are too complex for easy or certain classification. Effects owning dependence on one cause often wear the livery of another. The meaning of observed particulars may be inverted by situation, and yet it is only by the collection and collocation of particulars that we can hope to reach any general law. There is, however, a good deal of evidence to support the opinion, the grounds for which were primarily derived from the labours of Dr. Meldrum at Mauritius, that increased rainfall and atmospheric agitation attend spot maxima, while Herschel's conjecture of a more copious emission of light and heat about the same epochs has recently obtained some countenance from Savelyev measures showing a gain in the strength of the sun's radiation pari passu with increase in the number of spots visible on its surface. The examination of what we may call the texture of the sun's surface derived new interest from a remarkable announcement made by Mr. James Nasmyth in 1862. He had made, as he supposed, the discovery that the entire luminous stratum of the sun is composed of a multitude of elongated shining objects on a darker background, shaped much like willow leaves, of vast size, crossing each other in all possible directions, and possessed of unceasing relative motions. A lively controversy ensued. In England and abroad, the most powerful telescopes were directed to a scrutiny encompassed with varied difficulties. Mr. Dawes was especially emphatic in declaring that Nasmyth's willow leaves were nothing more than the nodules of Sir William Herschel seen under a misleading aspect of uniformity, and there is little doubt that he was right. It is nevertheless admitted that something of the kind may be seen in the penumbrae and bridges of spots, presenting an appearance compared by Dawes himself in 1852 to that of a piece of coarse straw thatching left untrimmed at the edges. The term granulated, suggested by Dawes in 1864, best describes the mottled aspect of the solar disk as shown by modern telescopes and cameras. The grains, or rather the floccules, with which it is thickly strewn, have been resolved by Langley, under exceptionally favourable conditions, into granules not above 100 miles in diameter, and from these relatively minute elements, composing jointly about 1/5 of the visible photosphere, he estimates that 3/4 of the entire light of the sun are derived. Janssen agrees so far as to say that if the whole surface were as bright as its brightest parts, its luminous emission would be 10 to 20 times greater than it actually is. The rapid changes in the forms of these solar cloud summits are beautifully shown in the marvellous photographs taken by Janssen at Meudon, with exposures reduced at times to 1/100,000th of a second. By their means also the curious phenomenon known as the réseau photosphérique has been made evident. This consists in the diffusion over the entire disk of fleeting blurred patches separated by a reticulation of sharply outlined and regularly arranged granules. The imperfect definition in the smudged areas may be due to agitations in the solar or terrestrial atmosphere, unless it be, as Dr. Schemmer thinks possible, merely a photographic effect. Monsieur Janssen considers that the photospheric cloudlets change their shape and character with the progress of the sunspot period, but this is as yet uncertain. The grains, or more brilliant parts of the photosphere, are now generally held to represent the upper termination of ascending and condensing currents. while the darker interstices, Herschel's pores, mark the positions of descending cooler ones. In the penumbrae of spots, the glowing streams rushing up from the tremendous sub-solar furnace are bent sideways by the powerful indraft, so as to change their vertical for a nearly horizontal motion, and are thus taken as it were in flank by the eye, instead of being seen end on in mamelon form. This gives a plausible explanation of the channeled structure of penumbrae, which suggested the comparison to a rude thatch. Accepting this theory as in the main correct, we perceive that the very same circulatory process, which in its spasms of activity gives rise to spots, produces in its regular course the singular marbled appearance, for the recording of which we are no longer at the mercy of the fugitive or delusive impressions of the human retina. And precisely this circulatory process it is which gives to our great luminary its permanence as a sun or warming and illuminating body. End of chapter 2, part 2.
Part 1 of chapter 3 of A Popular History of Astronomy during the 19th century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melanie T. A Popular History of Astronomy during the 19th century by Agnes Mary CLERKE. Chapter 3. Recent solar eclipses. By observations made during a series of 5 remarkable eclipses, comprised within a period of 11 years, knowledge of the solar surroundings was advanced nearly to its present stage. Each of these events brought with it a fresh disclosure of a definite and unmistakable character. We will now briefly review this orderly sequence of discovery. Photography was first systematically applied to solve the problems presented by the eclipsed sun, July 18, 1860. It is true that a daguerreotype taken by Boulais with the Königsberg heliometer during the eclipse of 1851 is still valuable as a record of the corona of that year, and some subsequent attempts were made to register partial phases of solar occultation, notably by Professor Bartlett at West Point in 1854. But the ground remained practically unbroken until 1860. In that year the track of totality crossed Spain and Tiver accordingly. Warren de la Rue transported his photoheliograph and Father Secchi his 6-inch cast-shoe refractor. The question then primarily at issue was that relating to the nature of the red protuberances, although, as already stated, the evidence collected in 1851 gave a reasonable certainty of their connection with the sun. Objectors were not silenced, and when the side of incredulity was supported by so considerable an authority as Monsieur Fay, it was impossible to treat it with contempt. 2 crucial tests were available. If it could be shown that the fantastic shapes suspended above the edge of the dark moon were seen under an identical aspect from 2 distant stations, that fact alone would annihilate the theory of optical illusion or mirage, while the certainty that they were progressively concealed by the advancing moon on one side and uncovered on the other would effectually detach them from dependence on our satellite and establish them as solar appendages. Now both these tests were eminently capable of being applied by photography, but the difficulty arose that nothing was known as to the chemical power of the rosy prominence light, while everything depended on its right estimation. A shot had to be fired, as it were, in the dark. It was a matter of some surprise and of no small congratulation that, In both cases, the shot took effect. De la Rue occupied a station at River Bellosa, in the upper Ebro Valley. Secchi set up his instrument at Desierto de las Palmas, about 250 miles to the southeast, overlooking the Mediterranean. From the totally eclipsed sun, with its strange garland of flames, each observer derived several perfectly successful impressions, which were found, on comparison, to agree in the most minute details. This at once settled the fundamental question as to the substantial reality of these objects, while their solar character was demonstrated by the passage of the moon in front of them, indisputably attested by pictures taken at successive stages of the eclipse. That forms seeming to defy all laws of equilibrium were, nevertheless, not wholly evanescent, appeared from their identity at an interval of 7 minutes, during which the lunar shadow was in transit from one station to the other, and the singular energy of their actinic rays was shown by the record on the sensitive plates of some prominences invisible to the telescope. Moreover, photographic evidence strongly confirmed the inference, previously drawn by Grant and others, and now with fuller assurance by Secchi, that an uninterrupted stratum of prominence matter encompasses the sun on all sides, forming a reservoir from which gigantic jets issue, and into which they subside. Thus, first fruits of accurate knowledge regarding the solar surroundings were gathered, while the value of the brief moments of eclipse gained indefinite increase, by supplementing transient visual impressions with the faithful and lasting records of the camera. In the year 1868 the history of eclipse spectroscopy virtually began, as that of eclipse photography in 1860. That is to say, the respective methods then first gave definite results. On the 18th of August 1868, the Indian and Malayan peninsulas were traversed by a lunar shadow producing total obscuration during 5 minutes and 38 seconds. 2 English and 2 French expeditions were dispatched to the distant regions favoured by an event so propitious to the advance of knowledge, chiefly to obtain the verdict of the prism as to the composition of the prominences. Nor were they dispatched in vain. An identical discovery was made by nearly all the observers. At Jamkhandi, in the Western Ghauts, where Lieutenant, now Colonel, Herschel was posted, unremitting bad weather threatened to baffle his eager expectations. But during the lapse of the critical 5½ minutes the clouds broke, and across the driving rack a long finger-like projection jutted out over the margin of the dark lunar globe. In another moment the spectroscope was pointed towards it. 3 bright lines, red, orange, and blue, flashed out, and the problem was solved. The problem was solved in the general sense that the composition out of glowing vapours of the objects infelicitously termed protuberances or prominences was no longer doubtful, although further inquiry was needed for the determination of the particular species to which those vapours belonged. Similar but more complete observations were made with less atmospheric hindrance by Tennant and Janssen at Guntur, by Pogson at Masulipatam, and by Rayet at Warton on the coast of the Malay Peninsula, the last observer counting as many as 9 bright lines. Among them it was not difficult to recognise the characteristic light of hydrogen, and it was generally, though over hastily, assumed that the orange ray matched the luminous emissions of sodium, but fuller opportunities were at hand. The eclipse of 1868 is chiefly memorable for having taught astronomers to do without eclipses, so far at least as one particular branch of solar inquiry is concerned. Inspired by the beauty and brilliancy of the various tinted prominence lines revealed to him by the spectroscope, Janssen exclaimed to those about him, Je verrai ces longues-là en dehors des eclipses. On the following morning he carried into execution the plan which formed itself in his brain while the phenomenon which suggested it was still before his eyes. It rests upon an easily intelligible principle. The glare of our own atmosphere alone hides the appendages of the sun from our daily view. To a spectator on an airless planet, the central globe would appear attended by all its splendor retinue of crimson prominences, silvery corona, and far-spreading zodiacal light projected on the star-spangled black background of an absolutely unilluminated sky. Now, the spectroscope offers the means of indefinitely weakening atmospheric glare by diffusing a constant amount of it over an area widened ad libitum. But monochromatic or bright line light is, by its nature, incapable of being so diffused. It can, of course, be deviated by refraction to any extent desired, but it always remains equally concentrated in whatever direction it may be thrown. Hence, when it is mixed up with continuous light, as in the case of the solar flames shining through our atmosphere, it derives a relative gain in intensity from every addition to the dispersive power of the spectroscope with which the heterogeneous mass of beams is analysed. Employ prisms enough, and eventually the undiminished rays of persistent colour will stand out from the continually fading rainbow-tinted band, by which they were at first effectually veiled. This Janssen saw by a flash of intuition while the eclipse was in progress, and this he realised at 10 a.m. the next morning, August 19th, 1868, the date of the beginning of spectroscopic work at the margin of the unobscured sun. During the whole of that day, and many subsequent ones, he enjoyed, as he said, the advantage of a prolonged eclipse. The intense interest with which he surveyed the region suddenly laid bare to his scrutiny was heightened by evidences of rapid and violent change. On the 18th of August, during the eclipse, a vast spiral structure, at least 89,000 miles high, was perceived planted in a surprising splendour on the rim of the interposed moon. If was formed, as General Tennant judged from its appearance in his photographs, by the encounter of two mounting torrents of flame, and was distinguished as the Great Horn. Next day it was in ruins, hardly a trace remained to show where it had been. Janssen's spectroscope furnished him besides with the strongest confirmation of what had already been reported by telescope and the camera as to the continuous nature of the Scarlet Sierra lying at the base of the prominences. Everywhere at the sun's edge the same bright lines appeared. It was not until the 19th of September that Janssen thought fit to send news of his discovery to Europe. It seemed little likely to be anticipated, yet a few minutes before his dispatch was handed to the Secretary of the Paris Academy of Sciences, a communication similar in purport had been received from Sir Norman Lockyer. There was no need to discuss the narrow and wearisome question of priority. Each of the competitors deserves and has obtained full credit for his invention. With noteworthy and confident prescience, Lockyer, in 1866, before anything was yet known regarding the constitution of the red flames, ordered a strongly dispersive spectroscope for the express purpose of viewing, apart from eclipses, the bright line spectrum which he expected them to give. Various delays, however, supervened, and the instrument was not in his hands until October 16, 1868. On the 20th he picked up the vivid rays, of which the presence and approximately the positions had in the interim become known. But there was little doubt that, even without the previous knowledge, they would have been found, and that the eclipse of August 18th only accelerated a discovery already assured. Sir William Huggins, meanwhile, had been tending towards the same goal during 2.5 years in his observatory at Tulse Hill. The principle of the spectroscopic visibility of prominence lines at the edge of an uneclipsed sun was quite explicitly stated by him in February 1868, and he devised various apparatus for bringing them into actual view, but not until he knew where to look did he succeed in seeing them. Astronomers, thus liberated by the acquisition of power to survey them at any time, from the necessity of studying prominences during eclipses, were able to concentrate the whole of their attention on the corona. The first thing to be done was to ascertain the character of its spectrum. This was seen in 1868 only as a faintly continuous one, for Rayet, who seems to have perceived its distinctive bright line far from the summits of the flames, connected it nevertheless with those objects. On the other hand, Lieutenant Campbell ascertained on the same occasion the polarization of the coronal light in planes passing through the sun's centre, thereby showing that light to be, in whole or in part, reflected sunshine. But if reflected sunshine, it was objected, the chief at least of the dark Fraunhofer lines should be visible in it, as they are visible in moonbeams, sky illumination, and all other sun-derived light. The objection was well founded, but it was prematurely urged, as we shall see. On the 7th of August 1869, a track of total eclipse crossed the continent of North America diagonally, entering at Bering Straits and issuing on the coast of North Carolina. It was beset with observers, but the most effective work was done in Iowa. At Des Moines, Professor Harkness of the Naval Observatory, Washington, obtained from the corona an absolutely continuous spectrum, slightly less bright than that of a full moon, but traversed by a single green ray. The same green ray was seen at Burlington and its position measured by Professor Young of Dartmouth College. It appeared to coincide with that of a dark line of iron in the solar spectrum, numbered 1474 on Kirchhoff's scale. But in 1876 Young was able, by the use of a greatly increased dispersion, to resolve the Fraunhofer line 1474 into a pair, and the more refrangible member of which he considered to be the reversal of the green coronal ray. Scarcely called in question for over 20 years, the identification nevertheless broke down through the testimony of the eclipse photographs of 1898. Sir Norman Lockyer derived from them a position for the line in question notably higher up the spectrum than that previously assigned to it. Instead of 5317, its true wavelength proved to be 5303 10/millionths of a millimetre. Nor does it make any show by absorption in dispersed sunlight. The originating substance, designated coronium, of which nothing is known to terrestrial chemistry, continues luminous, at least 300,000 miles above the sun's surface, and is hence presumably much lighter even than hydrogen. A further trophy was carried off by American skill 16 months after the determination due to it of the distinctive spectrum of the corona. The eclipse of December 22nd, 1870, though lasting only 2 minutes and 10 seconds, drew observers from the New as well as from the Old World to the shores of the Mediterranean. Janssen issued from beleaguered Paris in a balloon, carrying with him the vital parts of a reflector specially constructed to collect evidence about the corona. But he reached Oran only to find himself shut behind a cloud curtain more impervious than the Prussian lines. Everywhere the sky was more or less overcast. Lockyer's journey from England to Sicily and shipwreck in the Psyche were recompensed with a glimpse of the solar aureola during 1 second and a half. 3 parties stationed at various heights on Mount Etna saw absolutely nothing. Nevertheless, important information was snatched in despite of the elements. The prominent event was Young's discovery of the reversing layer, As the surveying solar crescent narrowed before the encroaching moon, the dark lines of the spectrum, he tells us, and the spectrum itself gradually faded away until all at once, as suddenly as a bursting rocket shoots out its stars, the whole field of view was filled with bright lines more numerous than one could count. The phenomenon was so sudden, so unexpected, and so wonderfully beautiful as to force an involuntary exclamation. Its duration was about 2 seconds, and the impression produced was that of a complete reversal of the Fraunhofer spectrum, that is, the substitution of a bright for every dark line. Now, something of the kind was theoretically necessary to account for the dusky rays in sunlight which have taught us so much, and have yet much more to teach us, so that, although surprising from its transitory splendour, the appearance could not be strictly called unexpected. Moreover, its premonitory symptom in the fading out of these rays had been actually described by Secchi in 1868, and looked for by Young as the moon covered the sun in August 1869. But with the slit of his spectroscope placed normally to the sun's limb, the bright lines gave a flash too thin to catch the eye. In 1870 the position of the slit was tangential. It ran along the shallow bed of incandescent vapours instead of cutting across it. Hence his success. The same observation was made at Xeres de la Frontera by Mr. Pye, a member of Young's party, and although an exceedingly delicate one, has since frequently been repeated. The whole Fraunhofer series appeared bright, omitting other instances, to Maclear, Herschel and Fries in 1871, at the beginning or end of totality, to Pogson at the break-up of an annual eclipse, June 6, 1872, to Stone at Klipfontein, April 16, 1874, when he saw the field full of bright lines. But between the picture presented by the veritable Pluie de Lune Brillante, which descended into Monsieur Trépier's spectroscope for 3 seconds after the disappearance of the sun, May 17, 1882, and the familiar one of the dark line solar spectrum, certain differences were perceiving, showing their relation to be not simply that of a positive or negative impression. A reversing layer, or stratum of mixed vapours, glowing but at a lower temperature than that of the actual solar surface, was an integral part of Kirchhoff's theory of the production of the Fraunhofer lines. Here it was assumed that the missing rays were stopped, and here also it was assumed that the missing rays would be seen bright, could they be isolated from the overpowering splendour of their background. This isolation is effected by eclipses, with the result, beautiful confirmatory of theory, of reversing or turning from dark to bright the Fraunhofer spectrum. The completeness and precision of the reversal, however, could not be visually attested, and a quarter of a century elapsed before a successful snapshot provided photographic evidence on the subject. It was taken at Novaya Zemlya by Mr. Shackleton, a member of the late Sir George Baldwin-Power's expedition to observe the eclipse of August 9, 1896, and similar records in abundance were secured during the Indian eclipse of January 22, 1898, and the Spanish-American eclipse of May 28, 1900. The result of their leisurely examination has been to verify the existence of a reversing layer, in the literal sense of the term. It is true that no single flash photograph is an inverted transcript of the Fraunhofer spectrum. The lines are, indeed, in each case, speaking broadly, the same, but their relative intensities are widely different. Yet this need not occasion no surprise when we remember that Fraunhofer spectrum integrates the absorption of a multitudinous strata, various in density and composition, while only the upper section of the formation comes within view of the sensitive plates exposed at totalities. the lie-lowing vaporous beds being necessarily covered by the moon. The total depth of this glowing envelope may be estimated at 500 to 600 miles, and its normal state seems to be one of profound tranquility, judging from the imperturbable aspect of the array of dark lines due to its sifting action upon light. The last of the 5 eclipses, which we have grouped together for separate consideration, was visible in southern India and Australia, December 12, 1871. Some splendid photographs were secured by the English parties on the Malabar coast, showing for the first time the remarkable branching forms of the coronal emanations. But the most conspicuous result was Jansen's detection of some of the dark Fraunhofer lines, long vainly sought in the continuous spectrum of the corona. Chief among these was the D line of sodium, the original index, it might be said, to solar chemistry. No proof could be afforded more decisive than this faint echoing back of the distinctive notes of the Fraunhofer spectrum, that the polariscope had spoken the truth in asserting a large part of the coronal radiance to be reflected sunlight. But it is usually so drenched in original luminosity that its special features are almost obliterated. Jansen's success in seizing them was due in part to the extreme purity of the air at Shola in the Nilgiris, where he was stationed, in part to the use of an instrument adapted by its large aperture and short focus to give an image of the utmost brilliancy. His observation, repeated during the Caroline Island eclipse of 1883, was photographically verified 10 years later by Monsieur de la Bonne-Pluvinel in Senegal. An instrument of great value for particular purposes was introduced into eclipse work in 1871. The slitless spectroscope consists simply of a prism placed outside the object glass of a telescope or the lens of a camera, whereby the radiance encompassing the eclipsed sun is separated into as many differently tinted rings as it contains different kinds of light. These tinted rings were simultaneously viewed by Respighi at Poodacotta and by Lockyer at Baikal. Their photographic registration by the latter in 1875 initiated the transformation of the slitless spectroscope into the prismatic camera. Meanwhile, the use of an ordinary spectroscope by Herschel and Tennant at Dodder Beta showed the green ray coronium to be just as bright in a rift in the adjacent streamer. The visible structure of the corona was thus seen to be independent of the distribution of the gases which enter into its composition. By means, then, of the 5 great eclipses of 1860 to 1871, it was ascertained, first, that the prominences, and at least the lower part of the corona, are genuine solar appurtenances. Secondly, that the prominences are composed of hydrogen and other gases in a state of incandescence, and rise, as irregular outliers, from a continuous envelope of the same materials, some thousands of miles in thickness. And thirdly, that the corona is of a highly complex constitution, being made up in part of glowing vapours, in part of matter capable of reflecting sunlight. We may now proceed to consider the results of subsequent eclipses. These have raised, and have helped to solve, some very curious questions. Indeed, every carefully watched total eclipse of the sun stimulates as well as appeases curiosity, and leaves a legacy of outstanding doubt, continually, as time and inquiry go on, removed, but continually replaced. It cannot be denied that the corona is a perplexing phenomenon, and that it does not become less perplexing as we know more about it. It has presented itself under quite a new and strange aspect. on the occasion of the eclipse which visited the western states of North America on July 29, 1878. The conditions of observation were peculiarly favourable. The weather was superb. Above the Rocky Mountains, the sky was of such purity as to permit the detection of Jupiter's satellites with the naked eye on several successive nights. The opportunity for advancing knowledge was made the most of. Nearly 100 astronomers, including several Englishmen, occupied 12 separate posts and prepared for an attack in force. The question had often suggested itself, and was a natural one to ask, whether the corona sympathizes with the general condition of the sun, whether, either in shape or brilliancy, it varies with the progress of the sunspot period. A more propitious moment for getting this question answered could hardly have been chosen than that at which the eclipse occurred. Solar disturbance was just then at its lowest ebb. The development of spots for the month of July 1878 was represented on Wolf's system of relative numbers by the fraction 0.1, as against 135.4 for December 1870, an epoch of maximum activity. The chromosphere was, for the most part, shallow and quiescent. Its depth above the spot zones had sunk from about 6,000 to 2,000 miles. Prominences were few and faint. Obviously, if a type of corona corresponding to a minimum of sunspots existed, it should be seen then or never. It was seen, but while in some respects it agreed with anticipation, in others it completely set it at naught. The corona of 1878, as compared with those of 1869, 1870, and 1871, was generally admitted to be shrunken in its main outlines and much reduced in brilliancy. Locke here pronounced it 10 times fainter than 1871. Harkness estimated its light at less than 1/7 that derived from the mist-blotted aureola of 1870. In shape, too, it was markedly different. When the sunspots are numerous, the corona appears to be most fully developed above the spot zones, thus offering to our eyes a rudely quadrilateral contour. The 4 great luminous sheaves forming the corners of the square are made up of rays curving together from each side into a synclinal or ogival groups, each of which may be compared to the petal of a flower. To Janssen in 1871, the eclipsing moon seemed like the dark heart of a gigantic dahlia, painted in light on the sky, and the similitude to the ornament on the compass card used by Airy in 1851 well conveys the decorative effect of the beamy radiated kind of aureola. Never, it would appear, absent when solar activity is at a tolerably high pitch. In his splendid volume on eclipses, with which the systematic study of coronal structure may be said to have begun, Mr. Ranyard first generalized the synclinal peculiarity by a comparison of records. But the symmetry of the arrangement, though frequently striking, is liable to be confused by secondary formations. He further pointed out, with the help of careful drawings from the photographs of 1871 made by Mr. Wesley, the curved and branching shapes assumed by the component filaments of massive bundles of rays. Nothing of all this, however, was visible in 1878. Instead, there was seen, as the groundwork of the corona, a ring of pearly light, nebulous to the eye, but shown by telescopes and in photographs to have a fibrous texture, as if made up of the tufts of fine hair. North and south, a series of short, vivid, electrical-looking flame brushes diverged with conspicuous regularity from each of the solar poles. Their direction was not towards the centre of the sun, but towards each summit of his axis, so that the farther rays on each side started almost tangentially to the surface. By the leading and a truly amazing characteristic of the phenomenon was formed by 2 vast, faintly luminous wings of light expanded on either side of the sun in the direction of the ecliptic. These were missed by very few careful onlookers, but the extent assigned to them varied with skill in and facilities for seeing. By far the most striking observations were made by Newcomb at Separation, Wyoming, and by Cleveland Abbey on the shoulder of Pike's Peak, and by Langley at its summit, an elevation 14,100 feet above the sea. Never before had an eclipse been viewed from anything approaching that altitude, or under so translucent a sky. A proof of the great reduction in the atmospheric glare was afforded by the perceptibility of the corona 4 minutes after totality was over. For the 165 seconds of its duration, the remarkable streamers above alluded to continued, persistently visible, stretching away right and left of the sun to a distance of at least 10 million miles. One branch was traced over an apparent extent of fully 12 lunar diameters, without a sign of definite termination having been reached, and there was no grounds for supposing the other more restricted. The resemblance to the zodiacal light was striking, and a community of origin between that enigmatical member of our system and the corona was irresistibly suggested. We should indeed expect to see, under such exceptionally favourable atmospheric conditions as Professor Langley enjoyed on Pike's Peak, the roots of the zodiacal light presenting near the sun just such an appearance as he witnessed. But we can imagine no reason why their visibility should be associated with a low state of solar activity. Nevertheless, this seems to be the case with the streamers which astonished astronomers in 1878. For in 1867, when similar equatorial emanations, accompanied by similar symptoms of polar excitement, were described and depicted by Grosch of the Santiago Observatory, sunspots were at a minimum, while the corona of 1715, which appears from the record of it by Roger Coates to have been of the same type, preceded by 3 years the ensuing maximum. The eclipsed sun was seen by him at Cambridge, May 2nd, 1715, encompassed with a ring of light about 1/6 of the moon's diameter in breadth, upon which it was superposed a luminous cross formed of long bright branches lying very nearly in the plane of the ecliptic, and shorter polar arms so faint as to be only intermittently visible. The resemblance between his sketch and Cleveland Abbe's drawing of the corona of 1878 is extremely striking. It should nevertheless be noted that some conspicuous spots were visible on the sun's disk at the time of Coates' eclipse, and that the preceding minimum, according to Wolf, occurred in 1712. Thus the coincidence of the epochs is imperfect. Professor Cleveland Abbe was fully persuaded that the long rays carefully observed by him from Pike's Peak were nothing else than streams of meteorites rushing towards or from perihelion, and it is quite certain that the solar neighbourhood must be crowded with such bodies. But the peculiar structure at the base of the streamers displayed in the photographs, the curved rays meeting in pointed arches like Gothic windows, the visible upspringing tendency, the filamentous texture, speak unmistakably of the action of forces proceeding from the sun, not of extraneous matter circling round him. A further proof in the sympathetic change in the corona is afforded by analysis of its light. In 1878, the bright lines so conspicuous in the coronal spectrum in 1870 and 1871 had faded to the very limit of visibility. Several skilled observers failed to see it at all, but Young and Eastman succeeded in tracing the green coronium ray all around the sun, to a height estimated at 340,000 miles. The substance emitting it was thus present, though in a low state of incandescence. The continuous spectrum was relatively strong. Faint traces of the Fraunhofer lines attested for it an origin, in part by reflection, and polarization was undoubted, increasing towards the limb, whereas in 1870 it reached a maximum at considerable distance from it. Experiments with Edison's tassimeter seem to show that the corona radiates a sensible amount of heat. End of Part 1 of Chapter 3.
Part 2, Chapter 3 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. A Popular History of Astronomy During the 19th Century by Agnes Mary CLERKE. Chapter 3, Part 2. The next promising eclipse occurred May 17, 1882. The concourse of astronomers, which has become usual on such occasions, assembled this time at Sohag in Upper Egypt. Rarely have 74 seconds been turned to such account. To each observer a special task was assigned, and the advantages of a strict division of labor were visible in the variety and amount of the information gained. The year 1882 was one of numerous sunspots. On the eve of the eclipse, 23 separate maculae were counted. If there were any truth in the theory which connected coronal forms with fluctuations in solar activity, it might be anticipated that the vast equatorial expansions and polar brushes of 1878 would be found replaced by the star-like structure of 1871. This expectation was literally fulfilled. No lateral streamers were to be seen. The universal failure to perceive them, after express search in a sky of the most transparent purity, justifies the emphatic assertion that they were not there. Instead, the type of corona observed in India 11 years earlier was reproduced with its shining aigrettes, complex texture, and brilliant radiated aspect. Concordant testimony was given by the spectroscope. The reflected light derived from the corona was weaker than in 1878, while its original emissions were proportionately intensified. Nevertheless, most of the bright lines recorded as coronal were really due, there can be no doubt, to diffused chromospheric light. On this occasion, the first successful attempt was made to photograph the coronal spectrum, procured in the ordinary way with a slit and prisms. While the prismatic camera was also profitably employed, it served to bring out at least one important fact, that the uncommon strength in chromospheric regions of the twin violet beams of calcium, designated H and K, and prominence photography signalized its improvement by the registration, in the spectrum of one such object, of 29 rays, including many of the ultraviolet hydrogen series discovered by Sir William Huggins, in the emission of white stars. Dr. Schuster's photographs of the corona itself were the most extensive, as well as the most detailed of any yet secured. One rift imprinted itself on the plates to a distance of nearly a diameter and a half from the limb, and the transparency of the streamers was shown by the delineation through them of the delicate tracery beyond. The singular and picturesque feature was added of a bright comet, self-depicted in all the exquisite grace of swift movement, betrayed by the fine curve of its tail, hurrying away from one of its rare visits to our sun, and rendered momentarily visible by the withdrawal of the splendor in which it had been, and was again quickly veiled. From a careful study of these valuable records, Sir William Huggins derived the idea of a possible mode of photographing the corona without an eclipse. As already stated, its ordinary invisibility is entirely due to the glare, or reflected light diffused through our atmosphere. But Huggins found, on examining Schuster's negatives, that a large proportion of the light in the coronal spectrum, both continuous and interrupted, is collected in the violet region between the Fraunhofer lines G and H. There, then, he hoped that all other rays being excluded, it might prove strong enough to vanquish inimical glare, and stamp on prepared plates, through local superiority in illuminative power, the forms of the appendage by which it is emitted. His experiments were begun toward the end of May 1882, and by September 28th he had obtained a fair earnest of success. The exclusion of all other qualities of light, save that which he desired to operate, was accomplished by using chloride of silver as his sensitive material, that substance being chemically inert to all other but those precise rays in which the corona has the advantage. Plates thus sensitized received impressions which it was hardly possible to regard as spurious. Not only the general features, Captain Abney affirmed, are the same, but the details, such as rifts and streamers, have the same position and form. It was found, moreover, that the corona photographed during the total eclipse of May 6, 1883, was intermediate in shape between the coronas photographed by Sir William Huggins before and after that event, each picture taking its proper place in a series of progressive modifications, highly interesting in themselves, and full of promise for the value of the method employed to record them. But experiments on the subject were singularly interrupted. The volcanic explosion in the Straits of Sunda in August 1883 brought to astronomers a peculiarly unwelcome addition to their difficulties. The magnificent sunglows due to the diffractive effects on light of the vapors and fine dust flung in vast volumes into the air and rapidly diffused all around the globe betokened an atmospheric condition of all others the most prejudicial to delicate researches in the solar vicinity. The filmy coronal forms, accordingly, which had been hopefully traced on the Tulse Hill plates, ceased to appear there, nor were there any substantially better results obtained by Mr. C. Ray Woods in the purer air either of the Riffel or the Cape of Good Hope during the 3 ensuing years. Moreover, attempts to obtain coronal photographs during the partial phases of the eclipse of August 29, 1886, completely failed. No part of the lunar globe became visible in relief against circumfluous solar radiance on any of the plates exposed to Granada, and what vestiges of structure there were came out almost better upon the moon than beside her, thus stamping themselves at once as of atmospheric origin. That the effect sought is a perfectly possible one is proved by the distinct appearance of the moon projected on the corona in photographs of the partially eclipsed sun in 1858, 1889, and 1890, and very notably in 1898 and 1900. In the spring of 1893, Professor Hale attacked the problem of coronal daylight photography, employing the double-slit method so eminently serviceable for the delineation of prominences. But neither at Kenwood nor at the summit of Pike's Peak, whither in the course of the summer he removed his apparatus, was any action of the desired kind secured. Similar ill success attended his and Professor Rico's employment on Mount Etna in July 1894 of a specially designed coronagraph. Yet discouragement did not induce despair. The end in view is indeed too important to be readily abandoned, but it can be reached only when a more particular acquaintance with the nature of coronal light than we now possess indicates the appropriate device for giving it a preferential advantage in self-portraiture. Moreover, the effectiveness of this device may not improperly be enhanced through changes in the coronal spectrum at epochs of sun-spot maximum. The prosperous result of the Sohag observations stimulated the desire to repeat them on the first favorable opportunity. This offered itself 1 year later, May 6, 1883, yet not without the drawbacks incident to terrestrial conditions. The eclipse promise was of rare length, giving no less than 5 minutes and 23 seconds of total obscurity, but its path was almost exclusively a water track. It touched land only on the outskirts of the Marquesas group in the southern Pacific, and presented, as the one available foothold for observers, a coral reef named Caroline Island, 7.5 miles long by 1.5 wide, unknown previously to 1874, and visited only for the sake of its stores of guano. Seldom has a more striking proof been given to the vividness of human curiosity as to the condition of the worlds outside our own than in the assemblage of a group of distinguished men from the chief centers of civilization on a barren ridge, isolated in a vast and tempestuous ocean, at a distance in many cases of 11,000 miles, and upwards from the ordinary scene of their labors. And all these sacrifices, the cost and care of preparation, the transport and readjustment of delicate instruments, the contrivance of new and more subtle means of investigating phenomena, on the precarious chance of a clear sky during one particular 5 minutes. The event, though fortunate, emphasized the hazard of the venture. The observation of the eclipse was made possible only by the happy accident of a serene interval between two storms. The American expedition was led by Professor Edward S. Holden, and to it were courteously permitted to be attached Messrs. Lawrence and Woods, photographers, sent out by the Royal Society of London. Monsieur Johnson was chief of the French Academy mission. He was accompanied by Moudon, by Boulais, and joined from Vienna by Palisa, and from Rome by Tacchini. A large share of the work was directed to assuring or negativing previous results. The circumstances of an eclipse favor illusion. A single observation by a single observer, made under unfamiliar conditions and at a moment of peculiar excitement, can scarcely be regarded as offering more than a suggestion for future inquiry. But incredulity may be carried too far. Johnson, for instance, felt compelled by the survival of unwise doubts to devote some of the precious minutes of obscurity at Caroline Island to confirming what, in his own persuasion, needed no confirmation, that is, the presence of reflected Fraunhofer lines in the spectrum of the corona. Boulais and Palisa, on the other hand, instituted an exhausted but fruitless search for the spurious intramercurian planets announced by Swift and Watson in 1878. New information, however, was not deficient. The corona proved identical in type with that of 1882, agreeably to what was expected at an epoch of protracted solar activity. The characteristic aigrettes were of even greater brilliancy than in the preceding year, and the chemical effects of the coronal light proved unusually intense. Johnson's photographs, owing to the considerable apertures, 6 and 8 inches, of his object glasses, and the long exposures permitted by the duration of totality, were singularly perfect. They gave a greater extension to the coronal than could be traced with the telescope, and showed its forms as absolutely fixed and of remarkable complexity. The English pictures, taken with exposures up to 60 seconds, were likewise of great value. They exhibited details of structure from the limb to the tips of the streamers, which terminated definitely, and as it seemed, actually, where the impressions on the plates ceased. The coronal spectrum was also successfully photographed, and although the reversing layer in its entirety evaded record, a print was caught of some of its more prominent rays just before and after totality. The use of the prismatic camera was baffled by the anomalous scarcity of prominences. Using an ingenious apparatus for viewing simultaneously the spectrum from both sides of the sun, Professor Hastings noticed at Caroline Islands alternations with the advance of the moon in respective heights above the right and left solar limbs of the coronal green line, which were thought to imply that the corona, with its rifts and sheaves and tangled hanks of rays, is, after all, merely an elusive appearance, produced by the diffraction of sunlight at the moon's edge. But the observation was assuredly misleading or misinterpreted. Atmospheric diffusion may indeed, under favoring circumstances, be effective in deceptively enlarging solar appendages, but always to a very limited extent. The controversy is an old one as to the part played by our air in producing the radiance visible round the eclipsed sun. In its original form, it is true, it came to an end when Professor Harkness, in 1869, pointed out that the shadow of the moon falls equally over the air and on the earth, and that if the sun had no luminous appendages, a circular space of almost absolute darkness would consequently surround the apparent places of the superposed sun and moon. Mr. Proctor, with his usual ability, impressed this mathematically certain truth upon public attention, and Sir John Herschel calculated that the diameter of the negative halo thus produced would be in general no less than 23 degrees. But about the same time, a noteworthy circumstance relating to the state of things in the solar vicinity was brought into view. On February 11, 1869, Messrs. Franklin and Lockyer communicated to the Royal Society a series of experiments on gaseous spectra under varying conditions of heat and density, leading them to the conclusion that the higher solar prominences exist in a medium of excessive tenuity, and that even at the base of the chromosphere the pressure is far below that at the Earth's surface. This inference was fully borne out by the researches of Wüllner and Janssen, expressed the opinion that the chromospheric gases are rarefied almost to the degree of an air pump vacuum. Hence was derived a general and fully justified conviction that there could be outside and incumbent upon the chromosphere no such vast atmosphere as the corona appeared to represent, upon the strength of which conviction the glare theory entered, chiefly under the auspices of Sir Norman Lockyer, under the second stage of its existence. The genuineness of the inner corona, to the height of 5 feet or 6 feet from the limb, was admitted, but it was supposed that by the detailed reflection of its light in our air, the far more extensive outer corona was optically created, the irregularities of the moon's edge being called into account for the rays and rifts by which the structure was varied. This view received some countenance from Admiral Maclear's observation, during the eclipse of 1870, of bright lines everywhere, even at the center of the lunar disk. Here indeed was an undoubted case of atmospheric diffusion, but here also was a safe index to the extent of its occurrence. Light scatters equally in all directions, so that when the moon's face at the time of an eclipse shows, as is the common case, a blank in the spectroscope, it is quite certain that the corona is not noticeably enlarged by atmospheric causes. A sky drifted over with thin cirrus clouds and air changed with aqueous vapor amply accounted for the abnormal amount of scattering in 1870. But even in 1870, positive evidence was obtained of the substantial reality of the radiated outer corona, in the appearance on photographic plates exposed by Willard in Spain and by Brothers in Sicily, of identical dark rifts. The truth is that far from being developed by misty air, it is peculiarly liable to be affected by it. The purer the sky, the more extensive, brilliant, and intricate in the details of its structure the corona appears. Take as an example General Meyer's description of the eclipse of 1869, as seen from the summit of White Top Mountain, Virginia, at an elevation above the sea of 5,523 feet, in an atmosphere of peculiar clearness. To the unaided eye, he wrote, the eclipse presented, during the total obscuration, a vision magnificent beyond description, as a center stood the full and intensely black disk of the moon, surrounded by the aureola of a soft bright light, through which shot out, as if from the circumference of the moon, straight massive silvery rays, seeming distinct and separate from each other, to a distance of 2 or 3 diameters of the solar disk, the whole spectacle showing as on a background of diffused rose-colored light. On the same day at Des Moines, Newcomb could perceive, through somewhat hazy air, no long rays, and the 4-pointed outline of a corona reached at its farthest only a single semi-diameter of the moon from the limb. The plain fact that our atmosphere acts rather as a veil to hide the coronal radiance than as the medium through which it is visually formed emerges from further innumerable records. No observations of importance were made during the eclipse of September 9, 1885. The path of total obscurity touched land only on the shores of New Zealand, and 2 minutes was the outside limit of available time. Hence, local observers had the phenomenon to themselves, nor were they even favored by the weather in their efforts to make the most of it. One striking appearance was, however, disclosed. It was that of two white prominences of unusual brilliancy, shining like a pair of electric lamps, hung one at each end of a solar diameter, right above the places of two large spots. This coincidence of diametrically opposed disturbances is of too frequent occurrence to be accidental. Monsieur Trouvelot observed at Meudon in June 26, 1885, two active and evanescent prominences thus situated, each rising to an enormous height of 300,000 miles, and on August 16th, one scarcely less remarkable, balanced by an antipodal spot group. It towered upward, as if by a process of unrolling, to 250,000 miles, after which, in 2 minutes, the light died out of it. It had become completely extinct. The development, again from the ends of a diameter, of a pair of similar objects, was watched September 19th and 20th, 1893, by Father Figny, director of the Coloxa Observatory, and the phenomenon has been too often repeated to be accidental. The eclipse of August 29th, 1886, was total during about 4 minutes over tropical Atlantic regions, and an English expedition, led by Sir Norman Lockyer, was accordingly dispatched to Grenada in the West Indies for the purpose of using the opportunity it offered. But the rainy season was just then at its height. Clouds and squalls were the order of the day, and the elaborately planned program of observation could only in part be carried through. Some good work none the less was done. Professor Tacchini, who had been invited to accompany the party, ascertained, besides some significant facts about prominences, from a comparison of their forms and sizes during and after the eclipse, it appeared that only the growing vaporous cores of these objects were shown by the spectroscope under ordinary circumstances, their upper sections giving a faint continuous spectrum, and composed of presumably cooler materials, can only be seen when the veil of scattered light usually drawn over them is removed by an eclipse. Thus all modestly tall prominences have silvery summits, but all do not appear to possess the red heart of flame by which alone they can be rendered perceptible to daylight observation. Some prove to be ordinarily invisible, because silvery throughout, sheeted ghosts, as it were, met only in the dark. Specimens of the class had been noted as far back as 1842, but Tacchini first drew particular attention to them. The one observed by him in 1886 rose in a branching form to a height of 150,000 miles, and gave a brilliantly continuous spectrum, with bright lines at H and K, but no hydrogen lines. Hence the total invisibility of the object before and after the eclipse. During the eclipse it was seen framed, as it were, in a pointed arch of coronal light, the symmetrical arrangement of which, with regard to it, was obviously significant. Both its unspringing shape and the violet rays of calcium strongly emitted by it contradicted the supposition that white prominences represent a downrush of refrigerated materials. The corona of 1886, as photographed by Dr. Schuster and Mr. Maunder, showed neither the petals and plumes of 1871 nor the streamers of 1878. It might be called of a transition type. Wide polar rifts were filled in with tufted radiations, and bounded on either side by irregularly disposed compound luminous masses. In the southwestern quadrant, a triangular ray, conspicuous to the naked eye, represented, Mr. W. H. Pickering thought, the projection of a huge hollow cone. Branched and recurving jets were curiously associated with it. The intrinsic photographic brightness of the corona proved, from Pickering's measures, to be about 1/54th that of the average surface of the full moon. The Russian eclipse of August 19, 1887, can only be remembered as a disastrous failure. Much was expected of it. The shadow path ran from overland from Leipzig to the Japanese Sea, so that the solar appurtenances would, it was hoped, be disclosed to observers echeloned along a line of 6,000 miles. but the incalculable element of weather rendered all forecasts nugatory. The clouds never parted during the critical 3 minutes over central Russia, where many parties were stationed, and Professor D.P. Todd was equally unfortunate in Japan. Some good photographs were nevertheless secured by Professor Availle, director of the Tokyo Observatory, as well as by M.M. Belopolsky and Gleisnap at Petrovolsk and Jurjevich, respectively. They showed a corona of simpler form than that of the year before, but not yet of the pronounced type first associated by Mr. Regnard with the lowest stage of solar activity. The genuineness of the association was ratified by the duplicate spectacle of the next ensuing minimum year. 2 total eclipses of the sun distinguished 1889. The first took place on New Year's Day, when a narrow shadow path crossed California, allowing less than 2 minutes for the numerous experiments prompted by the varied nature of modern methods of research. American astronomers availed themselves of the occasion to the full. The heavens were propitious. Photographic records were obtained in unprecedented abundance and of unusual excellence. Their comparison and study placed it beyond reasonable doubt that the radiated corona belonging to periods of maximum sunspots gives place at periods of minimum to the winged type of 1878. Professor Holden perceived further that the equatorial extensions characterizing the latter tend to assume a trumpet shape. Their extremities diverge as if mutually repellent, instead of flowing together along a medial plane. The maximum actinic brilliancy of the corona, January 1st, 1889, was determined at Lick to be 21 times less than that of the full moon. Its color was described as of an intense luminous silver, with a bluish tinge, similar to the light of an electric arc. Its spectrum was comparatively simple. Very few bright lines, besides those of hydrogen and coronium, and apparently no dark ones, stood out from the prismatic background. The marked structural features of the corona, as presented by the negatives taken by Professors Neiffer and Sheropin, were the filaments and streamers. The filaments issued from polar calottes of 20-degree radius. The impression conveyed to the eye, Professor Pritchard wrote, is that the equatorial stream of denser coronal matter extends across and through the filaments, simply obscuring them by its greater brightness. The effect is just as if the equatorial belt were superposed upon or passed through the filamentary structure. There is nothing in the photographs to prove that the filaments do not exist all around the sun. The testimony from negatives of different lengths of exposure goes to show that the equatorial streamers are made up of numerous interlacing parts, inclined at various angles to the sun's equator. The coronal extensions, perceptible with the naked eye to a distance of more than 3 degrees from the sun, appeared barely 1/3 of that length on the best negatives. Little more could be seen of them either in Barnard's exquisite miniature pictures or in the photographs obtained by W. H. Pickering with a 13-inch refractor, the largest instrument so far used in eclipse photography. End of Chapter 2, Part 2. Recording by Lawrence Trask. InterfaceAudio.com, Mount Vernon, Ohio. Part 2, Chapter 3, of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. A Popular History of Astronomy During the 19th Century by Agnes Mary Clarke. Chapter 3. Recent Solar Eclipses. Part 3. The total eclipse of December 22, 1889, held out a prospect unfortunately not realized of removing some of the doubts and difficulties that impeded the progress of coronal photography. Messrs. Burnham and Scheiberle secured at Cayenne some excellent impressions, showing enough of the corona to prove its identical character, with that depicted in the beginning of the year, but not enough to convey additional information about its terminal forms or innermost structure. Any better result was indeed impossible, the moisture-laden air having cut down the actinic power of the coronal light to 1/4 its previous value. 2 English expeditions, organized by the Royal Astronomical Society, fared still worse. Mr. Taylor was stationed on the west coast of Africa, 100 miles south of Luanda. Father Perry chose as the scene of his operations the Salut Islands off French Guiana. Each was supplied with a reflector constructed by Dr. Common, endowed by its extremely short focal length of 45, combined with an aperture of 20 inches, with a light concentrating force capable, it was hoped, of compelling the very filmiest coronal branches to self-registration. Had things gone well, 2 sets of coronal pictures, absolutely comparable in every respect, and taken at an interval of 2 hours and a half, would have been at the disposal of astronomers. But things went very far from well. Clouds altogether obscured the sun in Africa. They only separated to allow of his shining through a saturated atmosphere in South America. Father Perry's observations were the last heroic effort of a dying man. Stricken with malaria, he crawled to the hospital as soon as the eclipse was over, and expired 5 days later, at sea, on board the Comus. He was buried at Barbados. And the sacrifice of his life had, after all, purchased no decisive success. Most of the plates exposed by him suffered deterioration from the climate, or from an inevitably delayed development. A drawing from the best of them by Miss Violet Common represented a corona differing from its predecessor of January 1st, chiefly through the oppositely unsymmetrical relations of its parts. Then the western wing had been broader at its base than the eastern. Now the inequality was conspicuously the other way. The next opportunity for retrieving the mischances of the past was offered April 16, 1893. The line of totality charted for that day ran from Chile to Senegambia. American parties appropriated the Andes. Both shores of the Atlantic were in English occupation. French expeditions, led by Delandres and Bijourdin, took up posts south of Cape Verde. A long totality of more than 4 minutes was favored by serene skies, hence an ample store of photographic data was obtained. Professor Scheiberle of the Lick Observatory took, almost without assistance, at Mina Bronces, a mining station 6,600 feet above the Pacific, 52 negatives, 8 of them with a 40-foot telescope, on a scale of 4.5 inches to the solar diameter. Not only the inner corona, but the array of prominences then conspicuous, appeared in them to be composed of fibrous jets and arches, held to be sections of elliptic orbits described by luminous particles about the sun's center. One plate received the impression of a curious object, entangled amidst coronal streamers, and the belief in its cometary nature was ratified by the bestowal of a comet medal in recognition of the discovery. Similar paraloidal forms had nevertheless occasionally been seen to make an integral part of earlier coronas, and it remains extremely doubtful whether Scheiberle's eclipse comet was justly entitled to the character claimed for it. The eclipse of 1893 disclosed a radiated corona such as a year of spot maximum was sure to bring. An unexpected fact about it was, however, ascertained. The coronal has been believed to have much in common with the chromospheric spectrum. It proved on investigation with a large prismatic camera, employed under Sir Norman Lockyer's directions by Mr. Fowler at Fundium, to be absolutely distinct from it. The fundamental green ray had on the West African plates 7 more refrangible associates, but all alike are of unknown origin. They may be due to many substances, or to one. Future research will perhaps decide. We can at present only say that the gaseous emissions of the corona include none from hydrogen, helium, calcium, or any other recognizable terrestrial element. Delandre's attempt to determine the rotation of the corona through opposite displacements, east and west of the interposed moon, of the violet calcium lines supposed to make part of the coronal spectrum, was thus rendered nugatory. Yet it gave an earnest of success by definitely introducing the subject into the constantly lengthened program of eclipse work. There is, however, little prospect of its being treated effectively until the green line is vivified by a fresh access of solar activity. The flight of the moon's shadow was on August 9, 1896, dogged by atrocious weather. It traversed, besides, some of the most inhospitable regions on the earth's surface, and afforded at the best but a brief interval of obscurity. At Novaya Zemlya, however, of all places, the conditions were tolerably favorable, and as we have seen, the trophy of a flash spectrograph was carried off. Some coronal photographs, moreover, taken by the late Sir George Baden-Powell and by M. Hansky, a member of a Russian party, were marked by features of considerable interest. They made apparent a close connection between coronal outflows and chromospheric jets, cone-shaped beams serving as the sheath or envelopes of prominences. M. Hansky indeed thought that every streamer had a chromospheric eruption at its base. Further, dark veinings of singular shapes unmistakably interrupted the coronal light and bordered brilliant prominences, reminding us of certain black lines traced by Swift across the anvil protuberance, August 7, 1869. In type, the corona of 1896 produced that of 1886, as befitted its intermediate position in the solar cycle. The eclipse track on January 22, 1898, crossed the Indian Peninsula from Viziadrug on the Malabar coast to Mount Everest in the Himalayas. Not a cloud obstructed the view anywhere, and an unprecedented harvest of photographic records was garnered. The flash spectrum, in its successive phases, appeared on plates taken by Sir Norman Lockyer, Mr. Evershed, Professor Campbell, and others. Professor Turner set on foot a novel mode of research by picturing the corona in the polarized ingredient of its light. Mrs. Maunder practically solved the problem of photographing the faint coronal extensions, one ray on her plates running out to nearly 6 diameters from the moon's limb. Yet she used a Dallmeyer lens of only 1½ inches aperture. Her success accorded perfectly with Professor Wadsworth's conclusion that effectiveness in delineation by slight contrasts of luminosity varies inversely with aperture. Triple-coated plates and a comparatively long exposure of 20 seconds contributed to a result unlikely for some time to be surpassed. The corona of 1898 presented a mixed aspect. The polar plumes due at minimum were combined in it with the quadrilateral ogives belonging to spot maxima. A slow course of transformation, in fact, seemed in progress, and it was found to be completed in 1900, when the eclipse of May 28th revealed the typical halo of a quiescent sun. The obscurity on this occasion was short, less than 100 seconds, but was well observed east and west of the Atlantic. No striking gain in knowledge, however, resulted. Important experiments were indeed made on the heat of the corona with Langley's bolometer, but their upshot can scarcely be admitted as decisive. They indicated a marked deficiency of thermal radiations, implying for coronal light, in Professor Langley's opinion, an origin analogous to that of the electric glow discharge, which at low pressures was found by K. Angstrom in 1893 to have no invisible heat spectrum. The corona was photographed by Professor Barnard at Wadesboro, North Carolina, with a 61.5-foot horizontal celiostat. In this instrument, of a type now much employed in eclipse operations and first recommended by Professor Turner, a 6-inch photographic objective preserved an invariable position, while a silvered plane mirror, revolving by clockwork once in 48 hours, since the angle of movement is doubled by reflection, supplied the light it brought to a focus. A temporary wooden tube connected the lens with the photographic house where the plates were exposed. Pictures thus obtained with exposures of from 1 to 14 seconds were described as remarkably sharp and perfectly defined, showing the prominences and inner corona very beautifully. The polar fans came out magnificently. The great Sumatra eclipse left behind it manifold memories of foiled expectations. A totality of above 6 minutes drew observers to the far east from several continents, each cherishing a plan of inquiry, which few were destined to execute. All along the line of shadow, which on May 18, 1901, crossed Réunion and Mauritius, and again met land at Sumatra and Borneo, the meteorological forecast was dubious, and the meteorological actuality in the main deplorable. Nevertheless, the corona was seen and fairly well photographed through drifting clouds, and proved to resemble in essentials the appendage viewed a year previously. Negatives taken by members of the Lick Observatory expedition led by Mr. Perrine disclosed the unique phenomenon of a violent coronal disturbance with a small compact prominence as its apparent focus, tumbling masses and irregular streamers radiating from a point subsequently shown by the Greenwich photographs to be the seat of a conspicuous spot, suggested the recent occurrence of an explosion, the far-reaching effects of which might be traced in the confused floccular luminosity of a vast surrounding region. Again, photographs in polarized light attested the radiance of the outer corona to be in large measure reflected, while that of the inner ring was original, and the inference was confirmed by spectrographs, recording many Fraunhofer lines when the slit lay far from the sun's limb, but none in its immediate vicinity. On plates exposed by Mr. Dyson and Dr. Humphreys with special apparatus, the coronal spectrum, continuous and linear, impressed itself more extensively in the ultraviolet than on any previous occasion, and Dr. Mitchell succeeded in photographing the reversing layer by means of a grating spectroscope. Finally, Mrs. Maunder, at Mauritius, despite mischievous atmospheric tremors, obtained with the Newbegin telescope an excellent series of coronal pictures. The principles of explanation applied to the corona may be briefly described as eruptive and electrical. The first was adopted by Professor Scheiberle in his mechanical theory, advanced in 1890. According to this view, the eclipse halo consists of streams of matter shot out with great velocity from the spot zones by forces acting perpendicularly to the sun's surface. The component particles return to the sun after describing sections of extremely elongated ellipses, unless their initial speed happen to equal or exceed the critical rate of 383 miles a second, in which case they are finally driven off into space. The perspective overlapping and interlacing of these incandescent outflows was supposed to occasion the intricacies of texture visible in the corona, and it should be recorded that a virtually identical conclusion was reached by Mr. Perrine in 1901, by a different train of reasoning, based upon a distinct set of facts. A theory on very much the same lines was, moreover, worked out by M. Bélopolsky in 1897. Scheiberle, however, had the merit of making the first adequate effort to deduce the real shape of the corona, as it exists in 3 dimensions, from its projection upon the surface of the sphere. A theory on very much the same lines was, moreover, worked out by M. Bélopolsky in 1897. Scheiberle, however, had the merit of making the first adequate effort to deduce the real shape of the corona, as it exists in 3 dimensions, from its projection upon the surface of the sphere. He failed indeed to account for the variation in coronal types by the changes in our situation with regard to the sun's equator. It is only necessary to remark that, if this were so, they should be subject to an annual periodicity, of which no trace can be discerned. Electromagnetic theories have the charm and the drawback of dealing largely with the unknown, but they are gradually losing the vague and intangible character which long clung to them, and the improved definition of their outlines has not, so far, brought them into disaccord with truth. The most promising hypothesis of this kind is due to Professor Bigelow of Washington. His able discussion of the eclipse photographs of January 1, 1889, showed a striking agreement between the observed coronal forms and the calculated effects of a repulsive influence obeying the laws of electric potential, also postulated by Huggins in 1885. Finally, subdivided matter, expelled from the sun along lines of force emanating from the neighborhood of his poles, thus tends to accumulate at equipotential surfaces. In deference, however, to a doubt more strongly felt then than now, whether the presence of free electricity is compatible with the solar temperature, he avoided any express assertion that the coronal structure is an electrical phenomenon, merely pointing out that, if it were, its details would be just what they are. Later, in 1892, Pupin in America and Ebert in Germany imitated the coronal streamers by means of electrical discharges in low vacua between small conducting bodies and strips of tinfoil placed on the outside of the containing glass receptacles. Finally, a critical experiment made by Ebert in 1895 served, as Bigelow justly said, to clear up the entire subject and put the theory on a working basis. Having obtained coronoidal effects in the manner described, he proceeded to subject them to the action of a strong magnetic field, with the result of marshalling the scattered rays into a methodical and highly suggestive array. They followed the direction of the magnetic lines of force, and, forsaking the polar collar of the magnetized sphere, surrounded it like a ruffle. The obvious analogy with the aurora polaris and the solar corona was insisted upon by Ebert himself, and has been further developed by Bigelow. According to a recent modification of his hypothesis, the latter appendage is controlled by 2 opposing systems of forces, the magnetic causing the rays to diverge from the poles toward the equator, and the electrostatic urging their spread, through the mutual repulsion of the particles accumulated in the wings, from the equator towards either pole. The cyclical change in the corona, he adds, is probably due to a variation in the balance of power thus established, the magnetic polar influence dominating at minima, the electrostatic at maxima, and he may feel well encouraged by the fortunate combination of many experimental details into one explanatory whole, no less than by the hopeful prospect of further developments, both practical and theoretical, along the same lines. What we really know about the corona can be summed up in a few words. It is certainly not a solar atmosphere. It does not gravitate upon the sun's surface and share his rotation, as our air gravitates upon and shares the rotation of the earth, and this for the simple reason that there is no visible growth of pressure downward, of which the spectroscope would infallibly give notice, in its gaseous constituents, whereas under the sole influence of the sun's attractive power, their density should be multiplied many million times in descent through a mere fraction of their actual depth. They are apparently in a perpetual state of efflux from and influx to our great luminary, under the stress of opposing forces. It is not unlikely that some part at least of the coronal materials are provided by eruptions from the body of the sun. It is almost certain that they are organized and arranged round it through electromagnetic action. This, however, would seem to be influential only upon their white-hot or reflective ingredients, out of which the streamers and aigrettes are composed, since the coronal gases appear, from observations during eclipses, to form a shapeless envelope, with condensations above the spot zones, or at the basis of equatorial extensions. The corona is undoubtedly affected both in shape and constitution by the periodic ebb and flow of solar activity, its low-tide form being winged, its high-tide form stellate, while the rays emitted by the gases contained in it fade, and the continuous spectrum brightens at times of minimum sunspots. The appendage as a whole must be of inconceivable tenuity, since comets cut their way through it without experiencing sensible retardation. Not even Sir William Crookes' vacua can give an idea of the rarefaction which this fact implies. Yet the observed luminous effects may not in reality bear witness contradictory of it. One solitary molecule in each cubic inch of space might, in Professor Young's opinion, produce them, while in the same volume of ordinary air at sea level, the molecules number, according to Dr. Johnstone Stoney, 20,000 trillions. The most important lesson, however, derived from eclipses is that of partial independence of them. Some of the fruits in the daily study of prominences the next chapter will collect, and the harvest has been rendered more abundant, as well as more valuable, since it has been found possible to enlist, in this department too, the versatile aid of the camera. End of Chapter 3. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com.
Part 2, Chapter 4 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clarke. Part 2, Chapter 4, Solar Spectroscopy, Part 1. The new way struck out by Janssen and Lockyer was at once and eagerly followed. In every part of Europe, as well as in North America, observers devoted themselves to the daily study of the chromosphere and prominences. Foremost among these were Lockyer in England, Zollner at Leipzig, Sporer at Anclam, Young at Hanover, New Hampshire, Secchi and Respighi at Rome. There were many others, but these names stood out conspicuously. The first point to be cleared up was that of chemical composition. Leisurely measurements verified the presence above the sun's surface of hydrogen in prodigious volumes, but showed that sodium had nothing to do with the orange-yellow ray identified with it in the haste of the eclipse. From its vicinity to the D pair, than which it is slightly more refrangible, the prominence line was, however, designated D3, and the unknown substance emitting it was named by Lockyer helium. Its terrestrial discovery ensued after 26 years. In March 1895, Professor Ramsay obtained from the rare mineral cleveite a volatile gas, the spectrum of which was found to include the yellow prominence ray. Helium was actually at hand and available for examination. The identification cleared up many obscurities in the chromospheric chemistry. Several bright lines, persistently seen at the edge of the sun and early suspected by Young to emanate from the same source as D3, were now derived from helium in the laboratory, and all the complex emissions of that exotic substance ranged themselves into 6 sets or series, the members of which are mutually connected by numerical relations of a definite and simple kind. Helium is of rather more than twice the density of hydrogen and has no chemical affinities. In almost evanescent quantities, it lurks in the Earth's crust and is diffused through the Earth's atmosphere. The importance of the part played in the prominence spectrum by the violet line of calcium was noted by Professor Young in 1872, but since H and K lie near the limit of the visible spectrum, photography was needed for a thorough investigation of their appearances. Aided by its resources, Professor George E. Hale, then at the beginning of his career, detected in 1889 their unfailing and conspicuous presence. The substance emitting them not only constitutes a fundamental ingredient of the chromosphere, but rises, in the fantastic jets thence issuing, to greater heights than hydrogen itself. The isolation of H and K in the solar prominences from any other of the lines usually distinctive of calcium was experimentally proved by Sir William and Lady Huggins in 1897 to be due to the extreme tenuity of the emitting vapor. Hydrogen, helium, and calcium form, then, the chief and unvarying materials of the solar Sierra and its peaks, but a number of metallic elements make their appearance spasmodically under the influence of disturbances in the layers beneath. In September 1871, Young drew up, at Dartmouth College, a list of 103 lines significant of injections into the chromosphere of iron, titanium, chromium, magnesium, and many other substances, during 2 months' observation in the pure air of Mount Sherman, 8,335 feet high, in the summer of 1872. These telltale lines mounted up to 273, and he believes their number might still be doubled by steady watching. Indeed, both Young and Lockyer have more than once seen the whole field of the spectroscope momentarily inundated with bright rays, as if the reversing layer had been suddenly thrust upwards in the chromosphere, and as quickly allowed to drop back again. The opinion would thus appear to be well grounded that the two form one continuous region, of which the lower parts are habitually occupied by the heaviest vapors, but where orderly arrangement is continually overturned by violent eruptive disturbances. The study of the forms of prominences practically began with Huggins' observation of one through an open slit, February 13, 1869. At first it had been thought possible to examine them only in sections, that is, by admitting mere narrow strips or lines of their various kinds of light, while the actual shape of the objects emitting those lines had been arrived at by such imperfect devices as that of giving to the slit of the spectroscope a vibratory moment rapid enough to enable the eye to retain the impression of one part, while others were successively presented to it. It was an immense gain to find that their rays had strength to bear so much of dilution with ordinary light as was involved in opening the spectroscopic shutter wide enough to exhibit the tree-like or horn-like or flame-shaped bodies rising over the sun's rim in their undivided proportions. Several diversely colored images of them are formed in the spectroscope. Each may be seen under a crimson, a yellow, a green, and a deep blue aspect. The crimson, however, built up out of the C-line of hydrogen, is the most intense, and is commonly used for purposes of observation and illustration. Friedrich Zollner was, by a few days, beforehand with Huggins in describing the open slit method, but was somewhat less prompt in applying it. His first survey of a complete prominence, pictured in, and not simply intersected by, the slit of his spectroscope, was obtained July 1, 1869. Shortly afterwards, the plan was successfully adopted by the whole band of investigators. A difference in kind was very soon perceived to separate these objects into two well-marked classes. Its natural and obvious character was shown by its having struck several observers independently. The distinction of cloud prominences from flame prominences was announced by Lockyer April 27th, by Zollner June 2nd, and by Respighi December 4th, 1870. The first description are tranquil and relatively permanent, sometimes enduring without striking change for many days. Certain of the included species mimic terrestrial cloud scenery, now appearing like fleecy cirrus transpenetrated with the red glow of sunset, now like prodigious masses of cumulostratus hanging heavily above the horizon. The solar clouds, however, have the peculiarity of possessing stems. Slender columns can ordinarily be seen to connect the surface of the chromosphere with its outlying portions. Hence the fantastic likeness to forest scenery presented by the long ranges of fiery trunks and foliage occasionally seeming to fringe the sun's limb. But while this mode of structure suggests an actual outpouring of incandescent material, certain facts require a different interpretation. At a distance, and quite apart from the chromosphere, prominences have been perceived, by both Secchi and Young, to form, just as clouds form in a clear sky, condensation being replaced by ignition. Filaments were then thrown out downward towards the chromosphere, and finally the usual appearance of a stemmed prominence was assumed. Still more remarkable was an observation made by Trouvelot at Harvard College Observatory, June 26, 1874. A gigantic comma-shaped prominence, 82,000 miles high, vanished from before his eyes by a withdrawal of light as sudden as the passage of a flash of lightning. The same observer has frequently witnessed a gradual illumination or gradual extinction of such objects, testifying to changes in the thermal or electrical condition of matter already in situ. The first photograph of a prominence, as shown by the spectroscope in daylight, was taken by Professor Young in 1870, but neither his method nor that described by Dr. Braun in 1872 had any practical success. This was reserved to reward the efforts toward the same end of Professor Hale. Begun at Harvard College in 1889, they were prosecuted soon afterwards at the Kenworth Observatory, Chicago. The great difficulty was to extricate the colored image of the gaseous structure, spectroscopically visible at the sun's limb, from the encompassing glare, a very little of which goes a long way in fogging sensitive plates. To counteract its mischievous effects, a second slit, besides the usual narrow one in front of the collimator, was placed on guard, as it were, behind the dispersing apparatus, so as to shut out from the sensitized surface all light save that of the required quality, the sun's image being allowed to drift across the outer slit, while the plate holder was kept moving at the same rate. The successive sectional impressions thus rapidly obtained finally built up a complete picture of the prominence. Another expedient was soon afterwards contrived. The H and K rays of calcium are always, as we have seen, bright in the spectrum of prominences. They are, besides, fine and sharp, while the corresponding absorption lines in the ordinary solar spectrum are wide and diffuse. Hence, prominences formed by the spectroscope out of these particular qualities of violet light can be photographed entire and at once, for the simple reason that they are projected upon a naturally darkened background. Atmospheric glare is abolished by local absorption. This beautiful method was first realized by Professor Hale in June 1891. A spectroheliograph, consisting of a spectroscopic and photographic apparatus of special type attached to the eye end of an equatorial 12 inches in aperture, was erected at Kenwood in March 1891, and with its aid, Professor Hale entered upon original researches of high promise for the advancement of solar physics. Noteworthy above all is his achievement of photographing both prominences and faculae on the very surface of the sun. The latter had, until then, been very imperfectly observed. They were only visible, in fact, when relieved by their brilliance against the dusky edge of the solar disk. Their convenient emission of calcium light, however, makes it possible to photograph them in all positions, and emphasizes their close relationship to prominences. The simultaneous picturing, moreover, of the entire chromospheric ring, with whatever trees or fountains of fire chance to be at the moment issuing from it, has been accomplished by a very simple device. The disk of the sun itself having been screened with a circular metallic diaphragm, it is only necessary to cause the slit to traverse the virtually eclipsed luminary, in order to get an impression of the whole round of its fringing appendages. And the record can be extended to the disk by removing the screen, and carrying the slit back at a quicker rate, when an image of the sun's surface, with the faculae and spots, is formed on the plate exactly within the image of the chromosphere formed during the first exposure. The whole operation, Professor Hale continues, is completed in less than a minute, and the resulting photographs give the first true pictures of the sun, showing all the various phenomena at its surface. Most of these novel researches were, by a remarkable coincidence, pursued independently and contemporaneously by M. Deslandres of the Paris Observatory. The ultraviolet prominence spectrum was photographed for the first time from an uneclipsed sun in June 1891 at Chicago. Besides H and K, 4 members of the Huggins series of hydrogen lines imprinted themselves on the plate. Meanwhile, M. Deslandres was enabled, by fitting quartz lenses to his spectroscope and substituting a reflecting for a refracting telescope, to get rid of the obstructive action of glass upon the shorter light waves, and thus to widen the scope of his inquiry into the peculiarities of those derived from prominences. As the result, not only all the 9 white star lines were photographed from a brilliant sun flame, but 5 additional ones were found to continue the series upward. The wavelengths of these last had, moreover, been calculated beforehand with singular exactness, from a simple formula known as Balmer's law. The new lines accordingly filled places in a manner already prepared for them, and were thus unmistakably associated with the hydrogen spectrum. This is now known to be represented in prominences by 27 lines, forming a kind of harmonic progression, only 4 of which are visibly darkened in the Fraunhofer spectrum of the sun. The chemistry of cloud prominences is simple. Hydrogen, helium, and calcium are their chief constituents. Flame prominences, on the other hand, show, in addition, the characteristic rays of a number of metals, among which iron, titanium, barium, strontium, sodium, and magnesium are conspicuous. They are intensely brilliant, sharply defined in their varying forms of jets, spikes, fountains, waterspouts, of rapid formation and speedy dissolution, seldom attaining to the vast dimensions of the more tranquil kind. Eruptive or explosive by origin, they occur in close connection with spots. Whether casually, the materials ejected as flames, settling and cooling down as dark, depressed patches of increased absorption, or consequently, as a reactive effect of falls of solidified substances from great heights in the solar atmosphere. The 2 classes of phenomena, at any rate, stand in a most intimate relation. They obey the same law of periodicity, and are confined to the same portions of the sun's surface, while quiescent prominences may be found right up to the poles and close to the equator. The general distribution of prominences, including both genera, follows that of faculae much more closely than that of spots. From Father Secchi's and Professor Respighi's observations, 1869–71, were derived the first clear ideas on the subject, which have been supplemented and modified by the later researches of Professors Tacchini and Rico at Rome and Palermo. The results are somewhat complicated, but may be stated broadly as follows. The district of greatest prominence frequency covers and overlaps by several degrees that of the greatest spot frequency. That is to say, it extends to about 40 degrees north and south of the equator. There is a visible tendency to a second pair of maxima nearer the poles. The poles themselves, as well as the equator, are regions of minimum occurrence. Distribution in time is governed by the spot cycle, but the maximum lasts longer for prominences than for spots. The structure of the chromosphere was investigated in 1869 and subsequent years by Professor Respighi, director of the Capitoline Observatory, as well as by Sporer and Bredikine of the Moscow Observatory. They found this supposed solar envelope to be of the same eruptive nature as the vast protrusions from it, and to be made up of a congeries of minute flames, set close together like blades of grass. The appearance, Professor Young writes, which probably indicates a fact, is as if countless jets of heated gas were issuing through vents and spiracles over the whole surface, thus clothing it with flame, which heaves and tosses like the blaze of a conflagration. The summits of these filaments of fire are commonly inclined, as if by a wind sweeping over them, when the sun's activity is near its height, but erect during his phase of tranquillity. Sporer, in 1871, inferred the influence of permanent polar currents, but Tacchini showed in 1876 that the deflections upon which this inference was based ceased to be visible as the spot minimum drew near. Another peculiarity of the chromosphere, denoting the remoteness of its character from that of a true atmosphere, is the irregularity of its distribution over the sun's surface. There are no signs of its bulging out at the equator, as the laws of fluid equilibrium in a rotating mass would require, but there are some that the fluctuations in its depth are connected with the phases of solar agitation. At times of minimum, it seems to accumulate and concentrate its activity at the poles, while the maxima probably bring a more equable general distribution, with local depressions at the base of great prominences and above spots. The low-lying stratum of carbon vapor was, in 1897, detected in the chromosphere by Professor Hale with a grating spectroscope attached to the 40-inch Yerkes refractor. The eclipse photographs of 1893 disclosed to Hartley's examination the presence of gallium, and those taken by Evershed in 1898 were found by Jewell to be crowded with ultraviolet lines of the equally rare metal scandium. The general rule had been laid down by Sir Norman Lockyer that the metallic radiations from the chromosphere were those enhanced in the electric spark. Hence the comparative study of conditions prevalent in the arc and the spark has acquired great importance in solar physics. The reality of the appearance of violent disturbance presented by the flaming kind of prominence can be tested in a very remarkable manner. Christian Doppler, professor of mathematics at Prague, enounced in 1842 the theorem that the color of a luminous body, like the pitch of a sonorous body, must be changed by movements of approach or recession. The reason is this: both color and pitch are physiological effects, depending not upon absolute wavelength, but upon the number of waves entering the eye or ear in a given interval of time, and this number, it is easy to see, must be increased if the source of light or sound is diminishing at distance, and diminished if it is decreasing it. In the one case, the vibrating body pursues and crowds together the waves emanating from it. In the other, it retreats from them, and so lengthens out the space covered by an identical number. The principle may be thus illustrated. Suppose shots to be fired at a target at fixed intervals of time. If the marksman advances, say 20 paces, between each discharge of his rifle, it is evident that the shots will fall faster on the target than if he stood still. If, on the contrary, he retires by the same amount, they will strike at correspondingly longer intervals. The result will of course be the same whether the target or the marksman be in movement. So far Doppler was altogether right. As regards sound, anyone can convince himself that the effect he predicted is a real one by listening to the alternate shrilling and sinking of the steam whistle when an express train rushes through a station. But in applying this principle to the colors of stars, he went widely astray, for he omitted from consideration the double range of invisible vibrations which partake of, and to the eye exactly compensate, changes of refrangibility in the visible rays. There is, then, no possibility of finding a criterion of velocity in the hue of bodies shining, like the sun and stars, with continuous light. The entire spectrum is slightly shifted up or down in the scale of refrangibility. Certain rays normally visible become exalted or degraded, as the case may be, into invisibility, and certain other rays at the opposite end undergo the converse process, but the sum total of impressions on the retina continues the same. We are not, however, without the means of measuring this subsensible transportation of the light gamut. Once more, the wonderful Fraunhofer lines came to the rescue. They are called by the earlier physicists fixed lines, but it is just because they are not fixed that in this instance we find them useful. They share, and in sharing betray, the general shift of the spectrum. This aspect of Doppler's principle was adverted to by Fizeau in 1848, and the first tangible results in the estimation of movements of approach and recession between the Earth and the stars were communicated by Sir William Huggins to the Royal Society, April 23, 1868. 18 months later, Zollner devised his reversion spectroscope for doubling the measurable effects of line displacements, aided by which ingenious instrument, and following a suggestion of its inventor, Professor H. C. Vogel, succeeded at Bothkamp, June 9, 1871, in detecting effects of that nature due to the solar rotation. This application constitutes at once the test and the triumph of the method. The eastern edge of the sun is continually moving towards us with an equatorial speed of about 1.25 miles per second, the western edge retreating at the same rate. The displacements, toward the violet on the east, towards the red on the west, corresponding to this velocity are very small, so small that it seems hardly credible that they should have been laid bare to perception. They amount to but 1/150th part of the interval between the two constituents of the D line of sodium, and the D line of sodium itself can be separated into a pair only by a powerful spectroscope. Nevertheless, Professor Young was able to show, quite satisfactorily, in 1876, not only deviations in the solar lines from their proper places indicating a velocity of rotation, 1.42 miles per second, slightly in excess of that given by observations of spots, but the exemption of terrestrial lines, those produced by absorption in the Earth's atmosphere, from the general push upwards or downwards. Shortly afterwards, Professor Langley, then director of the Allegheny Observatory, having devised a means of comparing with great accuracy light from different portions of the sun's disk, found while the obscure rays in two juxtaposed spectra derived from the solar poles were absolutely continuous, no sooner was the instrument rotated through 90 degrees, so as to bring its luminous supplies from opposite extremities of the equator, than the same rays became perceptibly notched. The telluric lines, meanwhile, remained unaffected, so as to become virtually mapped by the process. This rapid and unfailing mode of distinction was used by Cornu with perfect ease during his investigation of atmospheric absorption near Loiret in August and September 1883. A beautiful experiment of the same kind was performed by M. Thollon of M. Bischoffsheim's observatory at Nice in the summer of 1880. He confined his attention to one delicately defined group of 4 lines in the orange, of which the inner part are solar, that is iron, and the outer terrestrial. At the center of the sun, the intervals separating them were sensibly equal. But when the light was taken alternately from the right and left limbs, a relative shift in alternate directions of the solar, towards and from the stationary telluric rays, became apparent. A parallel observation was made at Dunnet, December 14, 1883, when it was noticed that a strong iron line in the yellow part of the solar spectrum is permanently double on the sun's eastern, but single on his western limb. Opposite motion displacements bringing about this curious effect of coincidence with and separation from an adjacent stationary line of our own atmosphere's production, according as the spectrum is derived from the retreating or advancing margin of the solar globe. Statements of fact so precise and authoritative amount to a demonstration that results of this kind are worthy of confidence, and they already occupy an important place among astronomical data. The subtle method of which they serve to assure the validity was employed in 1887–89 by M. Danner to test and extend Carrington's and Sporer's conclusions as to the anomalous nature of the sun's axial movement. His observations for the purpose, made with a fine diffraction spectroscope just then mounted at the Observatory of Uppsala, were published in 1891. Their upshot was to confirm and widen the law of retardation with increasing latitude derived from the progressive motions of spots. Determinations made within 15 degrees of the pole, consequently far beyond the region of spots, gave a rotation period of 38½ that of the equatorial belt being of 25½ days. Spots near the equator, indeed, complete their rounds in a period shorter by at least half a day, and the proportionate differences were found to exist elsewhere in corresponding latitudes. But Dunier's observations, it must be remembered, apply to a distinct part of the complex solar machine from the disturbed photospheric surface. It is amply possible that the absorptive strata producing the Fraunhofer lines, significant by their varying displacements at either limb of the inferred varying rates of rotation, may gyrate more slowly than the spot-generating level. Moreover, faculae appear to move at a quicker pace than either, so that we have, for 3 solar formations, 3 different periods of average rotation, the shortest of which belongs to the faculae, one of the intermediate length to the spots, and the most protracted to the reversing layer. All, however, agree in lengthening progressively from the equator towards the poles. Professor Holden aptly compared the sun to a vast whirlpool where the velocities of rotation depend not only on the situation of the rotating masses as to latitude, but also as to depth beneath the exterior surface. Sir Norman Lockyer promptly perceived the applicability of the surprising discovery of line shiftings through end-on motion to the study of prominences, the discontinuous light of which affords precisely the same means of detecting movement without seeming change of place, as do lines of absorption in a continuous spectrum. Indeed, his observations at the sun's edge almost compel recourse to an explanation made available just when the need of it began to be felt. He saw bright lines not merely pushed aside from their normal places by a barely perceptible amount, but bent, torn, broken, as if by the stress of some tremendous violence. These remarkable appearances were quite simply interpreted as the effects of movements varying in amount and direction in the different parts of the extensive mass of incandescent vapors falling within a single field of view. Very commonly they are of a cyclonic character. The opposite distortions of the same colored rays betray the fury of counter gales rushing along at the rate of 120 miles a second, while their undisturbed sections prove the persistence of a heart of peace in the midst of that unimaginable fiery whirlwind. Velocities up to 250 miles a second, or 15,000 times that of an express train at the top of its speed, were thus observed by Young during his trip to Mount Sherman, August 2, 1872, and these were actually doubled in an extraordinary outburst observed by Father Jules Fenny on June 17, 1891, at the Hainault Observatory in Hungary, as well as by M. Trouvelot at Meudon. Motions ascertainable in this way near the limb are, of course, horizontal as regards the sun's surface. The analogies they present might accordingly be styled meteorological rather than volcanic. But vertical displacements on a scale no less stupendous can also be shown to exist. Observations of the spectra of spots centrally situated, where motions in the line of sight are vertical, disclose the progress of violent uprushes and downrushes of ignited gases, for the most part in the penumbral or outlying districts. They appear to be occasioned by fitful and irregular disturbances, and have none of the systematic quality which would be required for the elucidation of sunspot theories. Indeed, they almost certainly take place at a great height above the actual openings in the photosphere. End of chapter 4, part 1. Part 2, chapter 4 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clarke. Part 2, Chapter 4, Solar Spectroscopy, Part 2. As to vertical motions above the limb, on the other hand, we have direct visual evidence of a truly amazing kind. The projected glowing matter has, by the aid of the spectroscope, been watched in its ascent. On September 7, 1871, Young examined at noon a vast hydrogen cloud 100,000 miles long, as it showed to the eye, and 54,000 high. It floated tranquilly above the chromosphere at an elevation of some 15,000 miles, and was connected with it by 3 or 4 upright columns, presenting the not uncommon aspect compared by Lockyer to a grove of banyans. Called away for a few minutes at 12:30, on returning at 12:55, the observer found that in the meantime the whole thing had been literally blown to shreds by some inconceivable uprush from beneath. In place of the quiet cloud I had left, the air, if I may use the expression, was filled with flying debris, a mass of detached, vertical, fusiform filaments, each from 10 feet to 30 feet by 2 or 3 feet wide, brighter and closer together where the pillars had formerly stood, and rapidly ascending. They rose, with a velocity estimated at 166 miles a second, to fully 200,000 miles above the sun's surface, then gradually faded away like a dissolving cloud, and at 1:15 only a few filmy wisps, with some brighter streamers low down near the photosphere, remained to mark the place. A velocity projection of at least 500 miles per second was, by Proctor's calculation, required to account for this extraordinary display, to which the earth immediately responded by a magnetic disturbance and a fine aurora. It has proved by no means an isolated occurrence. Young saw its main features repeated October 7, 1881, on a still vaster scale, for the exploded prominence attained this time an altitude of 350,000 miles, the highest yet chronicled. Lockyer, moreover, has seen a prominence 40,000 miles high shattered in 10 minutes, while uprushes have been witnessed by Respighi, of which the initial velocities were judged by him to be 400 or 500 miles a second. When it is remembered that a body starting from the sun's surface at the rate of 383 miles a second would, if it encountered no resistance, escape forever from his control, it is obvious that we have, in the enormous forces of eruption or repulsion, manifested in the outbursts just described, the means of accounting for the vast diffusion of matter in the solar neighborhood. Nor is it possible to explain them away, as Cornu, Faye, and others have sought to do, by substituting for the rush of matter in motion progressive illumination through electric discharges, chemical processes, or even through the mere reheating of gases cooled by expansion. All the appearances are against such evasions of the difficulty presented by velocities stigmatized as fabulous and improbable, but which, there is the strongest reason to believe, really exist. On the 12th of December, 1878, Sir Norman Lockyer formally expounded before the Royal Society his hypothesis of the compound nature of the chemical elements, a hypothesis, it is true, over and over again propounded from the simply terrestrial point of view. What was novel was the supra-terrestrial evidence adduced in its support, and even this had been, in a general and speculative way, anticipated by Professor F. W. Clarke of Washington. Lockyer had been led to his conclusion along several converging lines of research. In a letter to M. Dumas, dated December 3, 1873, he had sketched out the successive stages of celestial dissociation, which he conceived to be represented in the sun and stars. The absence from the solar spectrum of metalloidal absorption he explained by the separation, in the fierce solar furnace, of such substances as oxygen, nitrogen, sulfur, and chlorine into simpler constituents possessing unknown spectra, while metals were at that time still admitted to be capable of existing there in a state of integrity. 3 years later he shifted his position onward. He announced, as the result of a comparative study of the Fraunhofer and electric arc spectra of calcium, that the molecular grouping of that metal, which at low temperatures gives a spectrum with its chief line in the blue, is nearly broken up in the sun into another or others with lines in the violet. This came to be regarded by him as a truly typical case. During 4 years, 1875 to 78 inclusive, This diligent observer was engaged in mapping a section of the more refrangible part of the solar spectrum, wavelengths of 3,800 to 4,000, on a scale of magnitude such that, if completed down to the infrared, its length would have been about half a furlong. The attendant laborious investigation, by the aid of photography, of metallic spectra seemed to indicate the existence of what he called basic lines. These held their ground persistently in the spectra of two or more metals after all possible impurities had been eliminated, and were therefore held to attest the presence of a common substratum of matter in a simpler state of agitation than any with which we are ordinarily acquainted. Later inquiries have shown, however, that between the spectral lines of different substances there are probably no absolute coincidences. Basic lines are really formed of doublets or triplets, merged together by insufficient dispersion. Of Thalin's original list of 70 rays common to several spectra, very few resisted Thollon's and Young's powerful spectroscopes, and the process of resolution was completed by Rowland. Thus the argument from community of lines to community of substance has virtually collapsed. It was replaced by one founded on certain periodical changes on the spectra of sunspots. They emerged from a series of observations begun at South Kensington under Sir Norman Lockyer's direction in 1879 and continued for 15 years. The principle of the method employed is this: the whole range of Fraunhofer lines is visible when the light from a spot is examined with the spectroscope, but relatively few are widened. Now these widened lines alone constitute, presumably, the true spot spectrum. They and they alone tell what kinds of vapor are thrust down into the strange dusky pit of the nucleus, the unaffected lines taking their accustomed origin from the overlying strata of the normal solar atmosphere. Here, then, we have the criterion that was wanted, the means of distinguishing, spectroscopically and chemically, between the cavity and the absorbing layers piled up above it. By its persistent employment, some marked peculiarities have been brought out, such as the unfamiliar character of numerous lines in spot spectra, especially at epochs of disturbance, and the strange individuality in the behavior of every one of these darkened and distended rays. Each seems to act on its own account. It comports itself as if it were the sole representative of the substance emitting it. Its appearance is unconditioned by that of any of its terrestrial companions in the same spectrum. The most curious fact, however, elicited by these inquiries was that of the attendance of chemical vicissitudes upon the advance of the sunspot period. As the maximum approached, unknown replaced known components of the spot spectra in a most pronounced and unmistakable way. It seemed as if the vapors emitting lines of iron, titanium, nickel, etc., had ceased to exist as such, and their room been taken by others, total strangers in terrestrial laboratories. These were held by Lockyer to be simply the finer constituents of their predecessors, dissociation having been effected by the higher temperature ensuing upon increased solar activity. But Father Cordy's supplementary investigations at Stonyhurst modified, while they in the main substantiated, the South Kensington results. They showed that the substitution of unknown for known lines characterizes disturbed spots at all stages of the solar cycle, so that no systematic course of chemical change can be said to affect the sun as a whole. They showed further, from evidence independent of that obtained by Young in 1892, the remarkable conspicuousness in spot spectra of vanadium lines excessively faint in the Fraunhofer spectrum. Lockyer's unknown lines may probably thus be accounted for. They represent absorption, not by new, but by scarce elements, especially, Father Cordy thinks, those with atomic weights of about 50. The circumstance of their development in solar commotions, largely to the exclusion of iron, is none the less curious, but it cannot be explained by any process of dissociation. The theory has, however, to be considered under still another aspect. It frequently happens that the contortions or displacements due to motion are seen to affect a single line belonging to a particular substance, while the other lines of that same substance remain imperturbable. Now how is this most singular fact, which seems at first sight to imply that a body may be at rest and in motion at one and the same instant, to be accounted for. It is accounted for, on the present hypothesis, easily enough, by supposing that the rays, thus discrepant in their testimony, do not belong to one kind of matter, but to several, combined at ordinary temperatures, to form a body in appearance elementary. Of these different vapors, one or more may, of course, be rushing rapidly towards or from the observer, while the others remain still, and since the line of sight across the average prominence region penetrates at the sun's edge a depth of about 300,000 miles, all the incandescent materials separately occurring along which line are projected into a single flame or cloud, it will be perceived that there is ample room for diversities of behavior. The alternative mode of escape from the perplexity consists in assuming that the vapor in motion is rendered luminous under conditions which reduce its spectrum to a few rays, the unaffected lines being derived from a totally distinct mass of the same substance shining with its ordinary emissions. Thus calcium can be rendered virtually monochromatic by attenuation, and analogous cases are not rare. Sir Norman Lockyer only asks us to believe that effects which follow certain causes on the earth are carried a stage farther in the sun, while the same causes must be vastly intensified. We find that the bodies we call compound split asunder at fixed degrees of heat within the range of our resources. Why should we hesitate to admit that the bodies we call simple do likewise at degrees of heat without the range of our resources? The term element simply expresses terrestrial incapability of reduction. That in celestial laboratories, the means and their effect, here absent, should be present, would be an inference challenging in itself no expression of incredulity. There are indeed theoretical objections to which, though probably not insuperable, are unquestionably grave. Our 70 chemical elements, for instance, are placed by the law of specific heats on a separate footing from their known compounds. We are not, it is true, compelled by it to believe their atoms to be really and absolutely such, to contain, that is, the irreducible minimum of material substance, but we do certainly gather from it that they are composed on a different principle from the salts and oxides made and unmade at pleasure by chemists. Then the multiplication of the species of matter with which Lockyer's results menace us is at first sight startling. They may lead, we are told, to eventual unification, but the prospect appears remote. Their only obvious outcome is the disruption into several constituents of each terrestrial element. The components of iron alone should be counted by the dozen. And there are other metals, such as cerium, which, giving a still more complex spectrum, would doubtless be still more numerously resolved. Sir Norman Lockyer interprets the observed phenomena as indicating the success of combinations in varying proportions of a very few original ingredients, but no definite sign of their existence is perceptible. Protyle seems long to evade recognition, and the only intelligible underlying principle for the reasonings employed, that of one line, one element, implies a throng beyond counting of formative material units. Thus, added complexity is substituted for that fundamental unity of matter which has long formed the dream of speculators, and it is extremely remarkable that Sir William Crookes, working along totally different lines, has been led to analogous conclusions. To take only one example, as the outcome of extremely delicate operations of sifting and testing carried on for years, he finds that the metal yttrium splits up into 5, if not 8 constituents. Evidently, old notions are doomed, nor are any preconceived ones likely to take their place. It would seem, on the contrary, as if their complete reconstruction were at hand. Subversive facts are steadily accumulating. The revolutionary ideas springing from them tend, if we interpret them aright, towards the substitution of electrical for chemical theories of matter. Dissociation by the brute force of heat is already nearly superseded in the thoughts of physicists by the more delicate process of ionization. Precisely what this implies and involves we do not know, but the symptoms of its occurrence are probably altogether different from those gathered by Sir Norman Lockyer from the collation of celestial spectra. A.J. Ångström of Uppsala takes rank after Kirchhoff as a subordinate founder, so to speak, of solar spectroscopy. His great map of the normal solar spectrum was published in 1868, 2 years before he died. Robert Thalen was his coadjutor in its execution, and the immense labor which it cost was amply repaid by its eminent and lasting usefulness. For more than a score of years it held its ground as the universal standard of reference in all spectroscopic inquiries within the range of the visible emanations. Those that are invisible, by reason of the quickness of their vibrations, were mapped by Dr. Henry Draper of New York in 1873, and with superior accuracy by M. Cornu in 1881. The infrared part of the spectrum, investigated by Langley, Abney, and Knut Ångström, reaches perhaps no definite end, the radiations oscillating too slowly to affect the eye, as light may pass by insensible gradations by the long Hertzian waves of electricity. Professor Rowland's photographic map of the solar spectrum, published in 1886, and a second enlarged edition in 1889, opened fresh possibilities for its study, from far down in the red to high up in the ultraviolet, and the accompanying scale of absolute wave lengths has been, with trifling modifications, universally adopted. His new table of standard solar lines was published in 1893. Through his work, indeed, knowledge of the solar spectrum so far outstripped knowledge of terrestrial spectra that the recognition of their common constituents was hampered by intolerable uncertainties. Thousands of solar lines charted with minute precision remained unidentified for want of a corresponding precision in the registration of metallic lines. Rowland himself, however, undertook to provide a remedy. Aided by Louis E. Jewell, he redetermined at Johns Hopkins University the wavelengths of about 16,000 solar lines, photographing for comparison with them the spectra of all known chemical elements except gallium, of which he could procure no specimen. The labor of collation was well advanced when he died at the age of 52, April 16, 1901. Investigations of metallic arc spectra have also been carried out with signal success by Hasselberg, Kayser, and Runge, O. Lohse, and others. Another condition sine qua non of progress in this department is the separation of true solar lines from those produced by absorption in our own atmosphere, and here little remains to be done. Tholen's great atlas was designed for this purpose of discrimination. Each of its 33 maps exhibits, in quadruplet, a subdivision of the solar spectrum under varied conditions of weather and zenith distance. Telluric effects are thus made easily legible, and they account wholly for 866, partly for 246, out of a total of 3,200 lines. But the death of the artist, April 8, 1887, unfortunately interrupted the half-finished task of the last 7 years of his life. A most satisfactory record, meanwhile, of selective atmospheric action has been supplied by the experiments and determinations of Janssen, Cornu, and Egorov, by Dr. Becker's drawings, and Mr. McLean's photographs of the analyzed light of the sun at high, low, and medium altitudes, and the autographic pictures obtained by Mr. George Higgs of Liverpool of certain rhythmical groups in the red, emerging with surprising strength near sunset, excite general and well-deserved admiration. The main interest, however, of all these documents resides in the information afforded by them regarding the chemistry of the sun. The discovery that hydrogen exists in the atmosphere of the sun was made by Ångström in 1862. His list of solar elements published in that year, the result of an investigation separate from, though conducted on the same principle as Kirchhoff's, included the substance which we now know to be predominant among them. Dr. Plücker of Bonn had identified in 1859 the Fraunhofer line F with the green ray of hydrogen, but drew no inference from his observation. The agreement was verified by Ångström, 2 further coincidences were established, and in 1866 a fourth hydrogen line in the extreme violet, named h, was detected in the solar spectrum. With Thalen, he besides added manganese, titanium, and cobalt to the constituents of the sun enumerated by Kirchhoff, and raised the number of identical rays in the solar and terrestrial spectra of iron to no less than 460. Thus, when Sir Norman Lockyer entered on that branch of inquiry in 1872, 14 substances were recognized as common to the earth and sun. Early in 1878, he was able to increase the list provisionally to 33, all except hydrogen metals. This rapid success was due to his adoption of the test of length in lieu of that of strength in the comparison of lines. He measured their relative significance, in other words, rather by their persistence through a wide range of temperature than by their brilliance at any one temperature. The distinction was easily drawn. Photographs of the electric arc, in which any given metal had been volatilized, showed some of the rays emitted by its stretching across the axis of the light to a considerable distance on either side, while many others clung more or less closely to its central hottest core. The former long lines, regarded as certainly representative, were those primarily sought in the solar spectrum, while the attendant short lines, often in point of fact, due to foreign admixtures, were set aside as likely to be misleading. The criterion is a valuable one, and its employment has greatly helped to quicken the progress of solar chemistry. Carbon was the first non-metallic element discovered in the sun. Messrs. Trowbridge and Hutchins of Harvard College concluded in 1887, on the ground of certain spectral coincidences, that this protein substance is vaporized in the solar atmosphere at a temperature approximately that of the voltaic arc. Partial evidence to the same effect had earlier been alleged by Lockyer, as well as by Liveling and Dewar, and the case was rendered tolerably complete by photographs taken by Kayser and Runge in 1889. It was by Professor Rowland shown to be irresistible. 200 carbon lines were, through his comparisons, sifted out from sunlight, and it contained others significant of the presence of silicon, a related substance, and one as important to rock building on the earth as carbon is to the maintenance of life. The general result of Rowland's labors was the establishment among solar materials not only of these two out of the 14 metalloids, or non-metallic substances, but of 33 metals, including silver and tin. Gold, mercury, bismuth, antimony, and arsenic were discarded from the catalogue. Platinum and uranium, with 6 other metals, remained doubtful, while iron was recorded as crowding the spectrum with over 2,000 obscure rays. Gallium absorption was detected in it by Hartley and Ramage in 1889. Dr. Henry Draper announced in 1877 his imagined discovery in the solar spectrum of 18 especially brilliant spaces corresponding to oxygen emissions, but the agreement proved, when put to the test of very high dispersion, to be wholly illusory. Nor has it yet been found possible to identify in analyzed sunlight any significant bright beams. The book of solar chemistry must be read in characters exclusively of absorption. Nevertheless, the whole truth is unlikely to be written there. That a substance displays none of its distinctive beams in the spectrum of the sun or of a star affords scarcely a presumption against its presence, for it may be situated below the level where absorption occurs, or under a pressure such as to efface lines by widening and weakening them. It may be at a temperature so high that it gives off more light than it takes up, and yet its incandescence may be masked by the absorption of other bodies. Finally, it may just balance absorption by emission with the result of complete spectral neutrality. An instructive example is that of the chromospheric element helium. Father Secchi remarked in 1868 that there is no dark line in the solar spectrum matching its light, and his observation has been fully confirmed. Helium absorption is, however, occasionally noticed in the penumbrae of spots. Our terrestrial vital element might then easily subsist unrecognizably in the sun. The inner organization of the oxygen molecule is a considerably plastic one. It is readily modified by heat, and these modifications are reflected in its varying modes of radiating light. Dr. Schuster enumerated in 1879 4 distinct oxygen spectra, corresponding to various stages of temperature or phases of electrical excitement, and a fifth has been added by M. Egoreff's discovery in 1883 that certain well-known groups of dark lines in the red end of the solar spectrum, Fraunhofer's A and B, are due to absorption by the cool oxygen of our air. These persist down to the lowest temperatures and even survive a change of state. They are produced essentially the same by liquid as by aerial oxygen. It seemed, however, possible to M. Janssen that these bands owned a joint solar and terrestrial origin. Oxygen in a fit condition to produce them might, he considered, exist in the outer atmosphere of the sun, and he resolved to decide the point. No one could bring more skill and experience to bear upon it than he. By observations on the summit of the Faulhorn, as well as by direct experiment, he demonstrated, nearly 30 years ago, the leading part played by water vapor in generating the atmospheric spectrum, and he had recourse to similar means for appraising the share in it assignable to oxygen. An electric beam, transmitted from the Eiffel Tower to Meudon in the summer of 1888, having passed through a weight of oxygen about equal to that piled above the surface of the earth, showed that groups A and B, just as they appear in the high sun spectrum. Atmospheric action is then adequate to produce them. But M. Janssen desired to prove, in addition, that they diminish proportionately to its amount. His ascent of Mont Blanc in 1890 was undertaken with this object. It was perfectly successful. In the solar spectrum, examined from that eminence, oxygen absorption was so much enfeebled as to leave no possible doubt of its purely telluric origin. Under another form, nevertheless, it has been detected as indubitably solar. A triplet of dark lines, low down in the red, photographed from the sun by Higgs and McLean, was clearly identified by Runge and Paskin in 1896 with the fundamental group of an oxygen series, first seen by Piazzi Smyth in the spectrum of a vacuum tube in 1883. The pabulum vitae of our Earth is then to some slight extent effective in arresting transmitted sunlight, and oxygen must be classed as a solar element. The rays of the sun, besides being stopped selectively in our atmosphere, suffer also a marked general absorption. This tells chiefly upon the slowest wavelengths. The ultraviolet spectrum is in fact closed, if by the interposition of an opaque screen. Nor does the screen appear very sensibly less opaque from an elevation of 10,000 feet. Dr. Simony's spectral photographs, taken on the peak of Teneriffe, extended but slightly further up than M. Cornu's, taken in the valley of the Loire. Could the veil be withdrawn, some indications as to the originating temperature of the solar spectrum might be gathered from its range, since the proportion of quick vibrations given out by a glowing body grows with the intensity of its incandescence, and this brings us to the subject of our next chapter. End of chapter 4, part 2.
Part 2, Chapter 5 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clarke. Chapter 5, Temperature of the Sun. Newton was the first who attempted to measure the quantity of heat received by the earth from the sun. His object in making the experiment was to ascertain the temperature encountered by the comet of 1680 at its passage through perihelion. He found it by multiplying the observed heating effects of direct sunshine according to the familiar rule of the inverse squares of the distances to be about 2,000 times that of red-hot iron. Determinations of the sun's thermal power, made with some scientific exactness, date, however, from 1837. A few days previous to the beginning of that year, Herschel began observing at the Cape of Good Hope with an actinometer, and obtained results agreeing quite satisfactorily with those derived by Pouillet from experiments made in France some months later with a pyroheliometer. Pouillet found that the vertical rays of the sun falling on each square centimetre of the earth's surface are competent, apart from atmospheric absorption, to raise the temperature of 1.7633 grams of water 1 degree centigrade per minute. This number, 1.7633, he called the solar constant, and the unit of heat chosen is known as the calorie. Hence it was computed that the total amount of solar heat received during a year would suffice to melt a layer of ice covering the entire earth to a depth of 30.89 meters, or 100 feet, while the heat emitted would melt at the sun's surface a stratum 11.80 meters thick each minute. A careful series of observations showed that nearly half the heat incident upon our atmosphere is stopped in its passage through it. Herschel got somewhat larger figures, though he assigned only a third as the spoil of the air. Taking a mean between his own and Pouillet's, he calculated that the ordinary expenditure of the sun per minute would have power to melt a cylinder of ice 184 feet in diameter, reaching from his surface to that of A Centauri; or, putting it otherwise, that an ice rod 45.3 miles across, continually darted into the sun with the velocity of light, would scarcely consume, in dissolving, the thermal supplies now poured abroad into space. It is nearly certain that this estimate should be increased by about two-thirds in order to bring it up to the truth. Nothing would, at first sight, appear simpler than to pass from a knowledge of solar emission, a strictly measurable quantity, to a knowledge of the solar temperature, this being defined as the temperature to which a surface thickly coated with lamp-black, that is, of standard radiating power, should be raised to enable it to send us, from the sun's distance, the amount of heat actually received from the sun. Sir John Herschel showed that heat rays at the sun's surface must be 92,000 times as dense as when they reach the earth, but it by no means follows that either the surface emitting or a body absorbing those heat rays must be 92,000 times hotter than a body exposed here to the full power of the sun. The reason is that the rate of emission, consequently the rate of absorption, which is its correlative, increases very much faster than the temperature. In other words, a body radiates or cools at a continually accelerated pace as it becomes more and more intensely heated above its surroundings. Newton, however, took it for granted that radiation and temperature advance pari passu, that you have only to ascertain the quantity of heat received from and the distance of a remote body in order to know how hot it is; and the validity of this principle, known as Newton's law of cooling, was never questioned until De la Roche pointed out in 1812 that it was approximately true only over a low range of temperature, while 5 years later Dulong and Petit generalized experimental results into the rule that while temperature grows by arithmetical, radiation increases by geometrical progression. Adopting this formula, Pouillet derived from his observations on solar heat a solar temperature of somewhere between 1,461 degrees and 1,761 degrees centigrade. Now the higher of these points, which is nearly that of melting platinum, is undoubtedly surpassed at the focus of certain burning glasses which have been constructed of such power as virtually to bring objects placed there within 250,000 of miles of the photosphere. In the rays thus concentrated, platinum and diamond become rapidly vaporized, notwithstanding the great loss of heat by absorption, first in passing through the air, and again in traversing the lens. Pouillet's maximum is then manifestly too low, since it involves the absurdity of supposing a radiating mass capable of heating a distant body more than it is itself heated. Less demonstrably, but scarcely less surely, Mr. J. J. Waterston, who attacked the problem in 1860, erred in the opposite direction, working up on Newton's principle data collected by himself in India and at Edinburgh. He got for the potential temperature of the sun 12,880,000 degrees Fahrenheit, equivalent to 7,156,000 degrees centigrade. The phrase potential temperature, for which Viol substituted in 1876 effective temperature, was designed to express the accumulation in a single surface, postulated for the sake of simplicity, of the radiations not improbably received from a multitude of separate solar layers reinforcing each other, and might thus, it was explained, be considerably higher than the actual temperature of any one stratum. At Rome in 1861, Father Secchi repeated Waterston's experiments and reaffirmed his conclusion, while Soret's observations made on the summit of Mont Blanc in 1867 furnished him with materials for a fresh and even higher estimate of 10,000,000 degrees centigrade. Yet from the very same data, substituting Dulong and Petit's for Newton's law, Vicaire deduced in 1872 a provisional solar temperature of 1,398 degrees. This is below that at which iron melts, and we know that iron vapour exists high up in the sun's atmosphere. The matter was taken into consideration on the other side of the Atlantic by Ericsson in 1871. He attempted to re-establish the shaken credit of Newton's principle, and arrived by its means at a temperature of 4,000,000 degrees Fahrenheit. Subsequently, an underrated computation, based upon observation of the quantity of heat received by his sun motor, gave him 3,000,000 degrees. And the result, as he insisted, followed inevitably from the principle that the temperature produced by radiant heat is proportional to its density, or inversely as its diffusion. The principle, however, is demonstrably unsound. In 1876, the sun's temperature was proposed as the subject of a prize by the Paris Academy of Sciences, but although the essay of M. Jules Viol was crowned, the problem was declared to remain unsolved. Viol, who adhered to Dulong and Petit's formula, arrived at an effective temperature of 1,500 degrees centigrade, but considered that it might actually reach 2,500 degrees centigrade if the emissive power of the photospheric clouds fell far short, as seemed probable, of the lamp-black standard. Experiments made in April and May 1881 giving a somewhat higher result, he raised this figure to 3,000 degrees centigrade. Appraisements so outrageously discordant as those of Waterston, Secchi, and Ericsson on the one hand, and those of the French savants on the other, served only to show that all were based upon a vicious principle. Professor F. Rossetti, accordingly, of the Paduan University, at last perceived the necessity for getting out of the groove of laws, plainly in contradiction with facts. The temperature, for instance, of the oxyhydrogen flame was fixed by Bunsen at 2,800 degrees centigrade, an estimate certainly not very far from the truth. But if the two systems of measurement applied to the sun be used to determine the heat of a solid body rendered incandescent in this flame, it comes out by Newton's mode of calculation 45,000 degrees centigrade. By Dulong and Petit's 870 degrees centigrade. Both, then, are justly discarded, the first as convicted of exaggeration, the second of undervaluation. The formula substituted by Rossetti in 1878 was tested successfully up to 2,000 degrees centigrade. But since, like its predecessors, it was a purely empirical rule, guaranteed by no principle, and hence not to be trusted out of sight, it was, like them, liable to break down at still higher elevations. Radiation by this new prescription increases as the square of the absolute temperature, that is, of the number of degrees counted from the absolute zero of minus 273 degrees centigrade. Its employment gave for the sun's radiating surface an effective temperature of 20,380 degrees centigrade, including a supposed loss of one half in the solar atmosphere, and setting a probable deficiency in emission, as compared with lampblack, against a probable mutual reinforcement of superposed strata, Professor Rossetti considered effective as nearly equivalent to actual temperature. A law of cooling, proposed by M. Stefan at Vienna in 1879, was shown by Boltzmann many years later to have a certain theoretical validity. It is that emission grows as the fourth power of absolute temperature. Hence the temperature of the photosphere would be proportional to the square root of its heating effects at a distance, and appeared by Stefan's calculations from Biot's measures of solar radiative intensity to be just 6,000 degrees centigrade, while M. H. Le Chatelier derives 7,600 degrees from a formula conveying an intricate and unaccountable relation between the temperature of an incandescent body and the intensity of its red radiations. From a series of experiments carefully conducted at Daramona, Ireland, with a delicate thermal balance of the kind invented by Boulais and designated a radio micrometer, Messrs. Wilson and Gray arrived in 1893, with the aid of Stefan's law, at a photospheric temperature of 7,400 degrees centigrade, reduced by the first named investigator in 1901 to 6,590 degrees. Dr. Paschen of Hanover, on the other hand, ascribed to the sun a temperature of 5,000 degrees from comparisons between solar radiative intensity and that of glowing platinum; while F. W. Very showed in 1895 that a minimum value of 20,000 degrees centigrade for the same datum resulted from Paschen's formula connecting temperature with the position of maximum spectral energy. A new line of inquiry was struck out by Zollner in 1870. Instead of tracking the solar radiations backward with the dubious guide of empirical formulae, he investigated their intensity at their source. He showed that, taking prominences to be simple effects of the escape of powerfully compressed gases, it was possible, from the known mechanical laws of heat and gaseous constitution, to deduce minimum values for the temperatures prevailing in the area of their development. These came out 27,700 degrees centigrade for the strata lying immediately above, and 68,400 degrees centigrade for the strata lying immediately below the photosphere, the former being regarded as the region into which, and the latter as the region from which, the eruptions took place. In this calculation no prominences exceeding 40,000 miles (1.5 minutes) in height were included; but in 1884 G. A. Hearn of Colmar, having regard to the enormous velocities of projection observed in the interim, fixed 2,000,000 degrees centigrade as the lowest internal temperature by which they could be accounted for, although admitting the photospheric condensations to be incompatible with a higher external temperature than 50,000 degrees to 100,000 degrees centigrade. This method of going straight to the sun itself, observing what goes on there, and inferring conditions, has much to recommend it; but its profitable use demands knowledge we are still very far from possessing. We are quite ignorant, for instance, of the actual circumstances attending the birth of the solar flames. The assumption that they are nothing but phenomena of elasticity is a purely gratuitous one. Spectroscopic indications, again, give hope of eventually affording a fixed point of comparison with terrestrial heat sources, but their interpretation is still beset with uncertainties. nor can indeed the expression of transcendental temperatures in degrees of impossible thermometers be at the best other than a futile attempt to convey notions respecting a state of things altogether outside the range of our experience. A more tangible as well as a less disputable proof of solar radiative intensity than any mere estimates of temperature was provided in some experiments made by Professor Langley in 1878. Using means of unquestioned validity, he found the sun's disk to radiate 87 times as much heat and 5,300 times as much light as an equal area of metal in a Bessemer converter after the air blast had continued about 20 minutes. The brilliancy of the incandescent steel, nevertheless, was so blinding that melted iron flowing in a dazzling white-hot stream into the crucible showed deep brown by comparison, presenting a contrast like that of dark coffee poured into a white cup. Its temperature was estimated not quite securely at about 2,000 degrees centigrade, and no allowances were made in computing relative intensities for atmospheric ravages on sunlight, for the extra impediments to its passage presented by the smoke-laden air of Pittsburgh, or for the obliquity of its incidence. Thus a very large balance of advantage lay on the side of the metal. A further element of uncertainty in estimating the intrinsic strength of the sun's rays has still to be considered. From the time that his disk first began to be studied with the telescope, it was perceived to be less brilliant near the edges. Lucas Valerius of the Lyncæan Academy seems to have been the first to note this fact, which, strangely enough, was denied by Galileo in a letter to Prince Cesi of January 25, 1613. Father Scheiner, however, fully admitted it, and devoted some columns of his bulky tome to the attempt to find its appropriate explanation. In 1729, Bouguer measured with much accuracy the amount of this darkening, and from his data Laplace, adopting a principle of emission now known to be erroneous, concluded that the sun loses 11/12 of his light through absorption in his own atmosphere. The real existence of this atmosphere, which is totally distinct from the beds of ignited vapours producing the Fraunhofer lines, is not open to doubt, although its nature is still a matter of conjecture. The separate effects of its action on luminous, thermal, and chemical rays were carefully studied by Father Secchi, who in 1870 inferred the total absorption to be 88/100 of all radiations taken together, and added the important observation that the light from the limb is no longer white but reddish brown. Absorptive effects were thus seen to be unequally distributed, and they could evidently be studied to advantage only by taking the various rays of the spectrum separately, and finding out how much each had suffered in transmission. This was done by H. C. Vogel in 1877. Using a polarizing photometer, he found that only 13% of the violet rays escape at the edge of the solar disk, 16 of the blue and green, 25 of the yellow, and 30% of the red. Midway between center and limb, 88.7 of violet light and 96.7 of red penetrate the absorbing envelope, the abolition of which would increase the intensity of the sun's visible spectrum above 2½ times in the most, and 1½ times in the least refrangible parts. The nucleus of a small spot was ascertained to be of the same luminous intensity as a portion of the unbroken surface about 2½ minutes from the limb. These experiments having been made during a spot minimum, when there is reason to think that absorption is below its average strength, Vogel suggested their repetition at a time of greater activity. They were extended to the heat rays by Edwin B. Frost. Detailed inquiries made at Potsdam in 1892 went to show that, were the sun's atmosphere removed, his thermal power as regards ourselves would be increased 1.7 times. They established, too, the practical uniformity in radiation of all parts of his disk. A confirmatory result was obtained about the same time by Wilson and Rambaud, who found that the unveiled sun would be 1½ times hotter than the actual sun. Professor Langley, now of Washington, gave to measures of the kind a refinement previously undreamt of. Reliable determinations of the energy of the individual spectral rays were, for the first time, rendered possible by his invention of the bolometer in 1880. This exquisitely sensitive instrument affords the means of measuring heat, not directly like the thermopile, but in its effects upon the conduction of electricity. It represents, in the phrase of the inventor, the finger laid upon the throttle valve of a steam engine. A minute force becomes the modulator of a much greater force, and thus from imperceptible becomes conspicuous. By locally raising the temperature of an inconceivably fine strip of platinum, serving as the conducting wire in a circuit, the flow of electricity is impeded at that point, and the included galvanometer records a disturbance of the electrical flow. Amounts of heat were thus detected in less than 10 seconds, which, expended during 1,000 years on the melting of a kilogramme of ice, would leave a part of the work still undone; and further improvements rendered this marvellous instrument capable of thrilling to changes of temperature falling short of 1/10,000,000th of a degree centigrade. The heat contained in the diffraction spectrum is, with equal dispersions, barely 1/10th of that in the prismatic spectrum. It had accordingly never previously been found possible to measure it in detail, that is, ray by ray; but it is only from the diffraction or normal spectrum that any true idea can be gained as to the real distribution of energy among the various constituents, visible and invisible, of a sunbeam. The effective passage through a prism is to crowd together the red rays very much more than the blue. To this prismatic distortion was owing the establishment of a pseudo maximum of heat in the infra red, which disappeared when the natural arrangement by wave length was allowed free play. Langley's bolometer has shown that the hottest part of the normal spectrum virtually coincides with its most luminous part, both lying in the orange, close to the D line. Thus the last shred of evidence in favour of the threefold division of solar radiations vanished, and it became obvious that the varying effects, thermal, luminous, or chemical, produced by them are due not to any distinction of quality in themselves, but to the different properties of the substances they impinge upon. They are simply bearers of energy, conveyed in shorter or longer vibrations, the result in each separate case depending upon the capacity of the material particles meeting them for taking up those shorter or longer vibrations and turning them variously to account in their inner economy. A long series of experiments at Allegheny was completed in the summer of 1881 on the crest of Mount Whitney in the Sierra Nevada. Here, at an elevation of 14,887 feet, in the driest and purest air perhaps in the world, atmospheric absorptive inroads become less sensible, and the indications of the bolometer consequently surer and stronger. An enormous expansion was at once given to the invisible region in the solar spectrum below the red. Captain Abney had got chemical effects from undulations 12/10,000ths of a millimetre in length. These were the longest recognised as, or indeed believed on theoretical grounds to be capable of existing. Professor Langley now got heating effects from rays of above twice that wave length, his delicate thread of platinum groping its way down nearly to 30/10,000ths of a millimetre, or 3 microns. The known extent of the solar spectrum was thus at once more than doubled. Its visible portion covers a range of about 1 octave, Bolometric indications already in 1884 comprised between 3 and 4. The great importance of the newly explored region appears from the fact that 3/4 of the entire energy of sunlight reside in the infrared, while scarcely more than 1/100th part of that amount is found in the better known ultraviolet space. These curious facts were reinforced in 1886 by further particulars learned with the help of rock salt lenses and prisms, glass being impervious to very slow as to very rapid vibrations. Traces were thus detected of solar heat distributed into bands of transmission alternating with bands of atmospheric absorption far beyond the measurable limit of 5.3 microns. In 1894, Langley described at the Oxford meeting of the British Association his new bolographic researches, in which the sensitive plate was substituted for the eye in recording deflections of the galvanometer responding to variations of invisible heat. Finally, in 1901, he embodied in a splendid map of the infrared spectrum 740 absorption lines of determinate wavelengths ranging from 0.76 to 5.3 microns. Their chemical origin, indeed, remains almost entirely unknown, no extensive investigations having yet been undertaken of the slower vibrations distinctive of particular substances; but there is evidence that 7 of the 9 great bands crossing the new spectrum, as Langley calls it, are telluric and subject to seasonal change. Here, then, he thought, might eventually be found a sure standing ground for vitally important previsions of famines, droughts, and bonanza crops. Atmospheric absorption had never before been studied with such precision as it was by Langley on Mount Whitney. Aided by simultaneous observations from Lone Pine at the foot of the Sierra, he was able to calculate the intensity belonging to each ray before entering the earth's gaseous envelope; in other words, to construct an extra-atmospheric curve of energy in the spectrum. The result showed that the blue end suffered far more than the red, absorption varying inversely as wave-length. This property of stopping predominantly the quicker vibrations is shared, as both Vogel and Langley have conclusively shown, by the solar atmosphere. The effect of this double absorption is as if 2 plates of reddish glass were interposed between us and the sun, the withdrawal of which would leave his orb not only 3 or 4 times more brilliant, but in colour distinctly greenish blue. The fact of the uncovered sun being blue has an important bearing upon the question of his temperature, to afford a somewhat more secure answer to which was the ultimate object of Professor Langley's persevering researches; for it is well known that as bodies grow hotter, the proportionate representation in their spectra of the more refrangible rays becomes greater. The lowest stage of incandescence is the familiar one of red heat. As it gains intensity, the quicker vibrations come in, and an optical balance of sensation is established at white heat. The final term of blue heat, as we now know, is attained by the photosphere. On this ground alone, then, of the large original preponderance of blue light, we must raise our estimate of solar heat, and actual measurements show the same upward tendency. Until quite lately, Pouillet's figure of 1.7 calories per minute per square centimetre of terrestrial surface was the received value for the solar constant. Forbes had, it is true, got 2.85 from observations on the Fall Horn in 1842, but they failed to obtain the confidence they merited. Pouillet's result was not definitely superseded until Violle, from actinometrical measures at the summit and base of Mont Blanc in 1875, computed the intensity of solar radiation at 2.54, and Crova, about the same time, at Montpellier, showed it to be above 2 calories. Langley went still higher. Working out the results of the Mount Whitney expedition, he was led to conclude atmospheric absorption to be fully twice as effective as had hitherto been supposed. Scarcely 60%, in fact, of those solar radiations which strike perpendicularly through a seemingly translucent sky were estimated to attain the sea level. The rest are reflected, dispersed, or absorbed. This discovery involved a large addition to the original supply so mercilessly cut down in transmission, and the solar constant rose at once to 3 calories. Nor did the rise stop there. M. Saveliev deduced for it a value of 3.47 from actinometrical observations made at Kiev in 1890, and Knut Ångström, taking account of the arrestive power of carbonic acid, inferred enormous atmospheric absorption and a solar constant of 4 calories. In other words, the sun's heat, reaching the outskirts of our atmosphere, is capable of doing, without cessation, the work of an engine of 4 horsepower for each square yard of the earth's surface. Thus modern inquiries tend to render more and more evident the vastness of the thermal stores contained in the great central reservoir of our system, while bringing into fair agreement the estimates of its probable temperature. This is in great measure due to the acquisition of a workable formula by which to connect temperature with radiation. Stephan's rule of a fourth power relation, if not actually a law of nature, is a colorable imitation of one, and its employment has afforded a practical certainty that the sun's temperature, so far as it is definable, neither exceeds 12,000 degrees centigrade nor falls short of 6,500 degrees centigrade. End of chapter 5. Part 2, Chapter 6 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clarke. Chapter 6, The Sun's Distance. The question of the sun's distance arises naturally from the consideration of his temperature, since the intensity of the radiations emitted, as compared with those received and measured, depends upon it. But the knowledge of that distance has a value quite apart from its connection with solar physics. The semi-diameter of the earth's orbit is our standard measure for the universe. It is the great fundamental datum of astronomy, the unit of space, any error in the estimation of which is multiplied and repeated in 1,000 different ways, both in the planetary and sidereal systems. Hence its determination was called by Airy the noblest problem in astronomy. It is also one of the most difficult. The quantities dealt with are so minute that their sure grasp tasks all the resources of modern science. An observational inaccuracy which would set the moon nearer to or farther from us than she really is by 100 miles would vitiate an estimate of the sun's distance to the extent of 16 million. What is needed in order to attain knowledge of the desired exactness is no less than this: to measure an angle about equal to that subtended by a halfpenny 2,000 feet from the eye, within a little more than 1,000th part of its value. The angle thus represented is what is called the horizontal parallax of the sun. By this amount, the breadth of a halfpenny at 2,000 feet, he is to a spectator on the rotating earth, removed at rising and setting from his meridian place in the heavens. Such, in other terms, would be the magnitude of the terrestrial radius as viewed from the sun. If we knew this magnitude with certainty and precision, we should also know with certainty and precision the dimensions of the earth being, as they are well ascertained, the distance of the sun. In fact, the one quantity commonly stands for the other in works treating professedly of astronomy. But this angle of parallax, or apparent displacement, cannot be directly measured, cannot even be perceived with the finest instruments. Not from its smallness. The parallactic shift of the nearest of the stars, as seen from opposite sides of the earth's orbit, is many times smaller. But at the sun's limb and close to the horizon, where the visual angle in question opens out to its full extent, atmospheric troubles become overwhelming, and altogether swamp the far more minute effects of parallax. There remain indirect methods. Astronomers are well acquainted with the proportions which the various planetary orbits bear to each other. They are so connected in the manner expressed by Kepler's third law that, the periods being known, it only needs to find the interval between any two of them in order to infer at once the distances separating them all from one another and from the sun. The plan is given. What we want to discover is the scale upon which it is drawn, so that if we can get a reliable measure of the distance of a single planet from the earth, our problem is solved. Now, some of our fellow travellers in our unending journey round the sun come at times well within the scope of celestial trigonometry. The orbit of Mars lies at one point not more than 35 million miles outside that of the Earth, and when the two bodies happen to arrive together in or near the favourable spot, a conjuncture which occurs every 15 years, the desired opportunity is granted. Mars is then in opposition, or on the opposite side of us from the sun, crossing the meridian consequently at midnight. It was from an opposition of Mars, observed in 1672 by Richer at Cayenne in concert with Cassini in Paris, that the first scientific estimate of the sun's distance was derived. It appeared to be nearly 87 millions of miles, parallax 9.5 minutes, while Flamsteed deduced 81,700,000, parallax 10 minutes, from his independent observations of the same occurrence, a difference quite insignificant at that stage of the inquiry. But Picard's result was just half Flamsteed's, parallax 20 minutes, distance 41 million miles, and La Hire considered that we must be separated from the hearth of our system by an interval of at least 136 million miles, so that uncertainty continued to have an enormous range. Venus, on the other hand, comes closest to the Earth when she passes between it and the sun. At such times of inferior conjunction, she is, however, still 26 million miles, or in round numbers 109 times as distant as the moon. Moreover, she is so immersed in the sun's rays that it is only when her path lies across his disk that the requisite facilities for measurement are afforded. These partial eclipses of the sun by Venus, as Encke termed them, are coupled together in pairs, of which the components are separated by 8 years, recurring at intervals alternately of 105½ and 121½ years. Thus the first calculated transit took place in December 1631, and its companion, observed by Horrocks in the same month, in S. 1639. Then, after the lapse of 121½ years, came the June couple of 1761 and 1769, and again after 105½, the two last observed December 8, 1874, and December 6, 1882. Throughout the 20th century there will be no transit of Venus, but the astronomers of the 21st will only have to wait 4 years for the first of a June pair. The rarity of these events is due to the fact that the orbits of the Earth and Venus do not lie in the same plane. If they did, there would be a transit each time that our twin planet overtakes us in her more rapid circling, that is, on an average every 584 days. As things are actually arranged, she passes above or below the Sun, except when she happens to be very near the line of intersection of the two tracks. Such an occurrence as a transit of Venus seems at first sight full of promise for solving the problem of the Sun's distance, for nothing would appear easier than to determine exactly either the duration of the passage of a small dark orb across a large brilliant disk, or the instant of its entry upon or exit from it. And the differences in these times, which, owing to the comparative nearness of Venus, are quite considerable, as observed from remote parts of the earth, can be translated into differences of space, that is, into apparent or parallactic displacements, whereby the distance of Venus becomes known, and thence, by a simple sum in proportion, the distance of the Sun. But in that word exactly what snares and pitfalls lie hid. It is so easy to think and to say, so indefinitely hard to realize. The astronomers of the 18th century were full of hope and zeal. They confidently expected to attain, through the double opportunity offered them, to something like a permanent settlement of the statistics of our system. They were grievously disappointed. The uncertainty as to the Sun's distance, which they had counted upon reducing to a few 100,000 miles, remained at many millions. In 1822, however, Encke, then director of the Seeberg Observatory near Gotha, undertook to bring order out of the confusion of discordant and discordantly interpreted observations. His combined result for both transits, 1761 and 1769, was published in 1824 and met universal acquiescence. The parallax of the Sun thereby established was 8.5776 minutes, corresponding to a mean distance of 95 1/4 million miles. Yet this abolition of doubt was far from being so satisfactory as it seemed. Serenity on the point lasted exactly 30 years. It was disturbed in 1854 by Hansen's announcement that the observed motions of the moon could be drawn into accord with theory only on the terms of bringing the Sun considerably nearer to us than he was supposed to be. Dr. Matthew Stewart, professor of mathematics in the University of Edinburgh, had made a futile attempt in 1763 to deduce the Sun's distance from his disturbing power over our satellite. Tobias Mayer of Göttingen, however, whose short career was fruitful of suggestions, struck out the right way to the same end, and Laplace, in the seventh book of the Mécanique Céleste, gave a solar parallax derived from the lunar parallactic inequality, substantially identical with that issuing from Encke's subsequent discussion of the 18th century transits. Thus, two wholly independent methods, the trigonometrical, or method by survey, and the gravitational, or method by perturbation, seem to corroborate each, the upshot of the use of the other, until the 19th century was well past its meridian. It is singular how often errors conspire to lead conviction astray. Hansen's note of alarm in 1854 was echoed by Leverrier in 1858. He found that an apparent monthly oscillation of the Sun, which reflects a real monthly movement of the earth round its common centre of gravity with the moon, and which depends for its amount solely on the mass of the moon and the distance of the Sun, required a diminution in the admitted value of that distance by fully 4 million miles. 3 years later, he pointed out that certain perplexing discrepancies between the observed and computed places, both of Venus and Mars, would vanish on the adoption of a similar measure. Moreover, a favorable opposition of Mars gave the opportunity in 1862 for fresh observations, which, separately worked out by Stone and Winecki, agreed with all the newer investigations in fixing the great unit at slightly over 91 million miles. In Newcomb's hands they gave 92.5 million. The accumulating evidence in favor of a large reduction in the sun's distance was just then reinforced by an auxiliary result of a totally different and unexpected kind. The discovery that light does not travel instantaneously from point to point, but takes some short time in transmission, was made by Olaus Roemer in 1675 through observing that the eclipses of Jupiter's satellites invariably occurred later, when the Earth was on the far side, than when it was on the near side of its orbit. Half the difference, or the time spent by a luminous vibration in crossing the mean radius of the Earth's orbit, is called the light equation, and the determination of its precise value has claimed the minute care distinctive of modern astronomy. Delambre in 1792 made it 493 seconds. Glasenapp, a Russian astronomer, raised the estimate in 1874 to 501. Professor Harkness adopts a safe medium value of 498 seconds. Hence, if we had any independent means of ascertaining how fast light travels, we could tell at once how far off the sun is. There is yet another way by which knowledge of the swiftness of light would lead us straight to the goal. The heavenly bodies are perceived, when carefully watched and measured, to be pushed forward out of their true places in the direction of the earth's motion by a very minute quantity. This effect, already adverted to, has been known since Bradley's time as aberration. It arises from a combination of the two movements of the earth round the sun and of the light waves through the ether. If the earth stood still, or if light spent no time on the road from the stars, such an effect would not exist. Its amount represents the proportion between the velocities with which the earth and the light rays pursue their respective journeys. This proportion is, roughly, 1 to 10,000. So that here again, if we knew the rate per second of luminous transmission, we should also know the rate per second of the Earth's movement, consequently the size of its orbit and the distance of the sun. But until lately, instead of finding the distance of the sun from the velocity of light, there has been no means of ascertaining the velocity of light except through the imperfect knowledge possessed as to the distance of the sun. The first successful terrestrial experiments on the point date from 1849, and it is certainly no slight triumph of human ingenuity to have taken rigorous account of the delay of a sunbeam in flashing from one mirror to another. Fizeau led the way, and he was succeeded after a few months by Léon Foucault, who in 1862 had so far perfected Wheatstone's method of revolving mirrors as to be able to announce with authority that light travels slower, and that the sun was in consequence nearer than had been supposed. Thus a third line of separate research was found to converge to the same point with the two others. Such a conspiracy of proof was not to be resisted, and at the anniversary meeting of the Royal Astronomical Society in February 1864, the correction of the solar distance took the foremost place in the annals of the year. Lest, however, a sudden bound of 4 million miles nearer to the centre of our system should shake public faith in astronomical accuracy, it was explained that the change in the solar parallax corresponding to that huge leap amounted to no more than the breadth of a human hair, 125 feet from the eye. The Nautical Almanac gave from 1870 the altered value of 8.95 minutes, for which Newcomb's result of 8.85 minutes, adopted in 1869 in the Berlin Ephemeris, was substituted some 10 years later. In astronomical literature, the change was initiated by Sir Edmund Beckett in the first edition, 1865, of his Astronomy without Mathematics. If any doubt remained as to the misleading character of Encke's deduction, so long implicitly trusted in, it was removed by Powalke's and Stone's rediscussions in 1864 and 1868, respectively, of the transit observations of 1769. Using improved determinations of the longitude of the various stations and a selective judgment in dealing with their materials, which, however indispensable, did not escape adverse criticism, they brought out results confirmatory of the no longer disputed necessity for largely increasing the solar parallax and proportionately diminishing the solar distance. Once more in 1890, and this time with better success, the 18th century transits were investigated by Professor Newcomb. Turning to account the experience gained in the interim regarding the optical phenomena accompanying such events, he elicited from the mass of somewhat discordant observations at his command a parallax 8.79 minutes, in close agreement with the value given by sundry modes of recent research. Conclusions on the subject, however, were still regarded as purely provisional. A transit of Venus was fast approaching, and to its arbitrament, as to that of a court of final appeal, the pending question was to be referred. It is true that the verdict in the same case by the same tribunal a century earlier had proved of so indecisive a character as to form only a starting point for fresh litigation. But that century had not passed in vain, and it was confidently anticipated that observational difficulties, then equally unexpected and insuperable, would yield to the elaborate care and skill of forewarned modern preparation. The conditions of the transit of December 8, 1874, were sketched out by Sir George Airy, then Astronomer Royal, in 1857, and formed the subject of eager discussion in this and other countries down to the very eve of the occurrence. In these Mr. Proctor took a leading part, and it was due to his urgent representations that provision was made for the employment of the method identified with the name of Halley, which had been too hastily assumed inapplicable to the first of each transit pair. It depends upon the difference in the length of time taken by the planet to cross the sun's disk, as seen from various points of the terrestrial surface, and requires accordingly the visibility of both entrance and exit at the same station. Since these were, in 1874, separated by about 3½ hours, and the interval may be much longer, the choice of posts for the successful use of the method of durations is a matter of some difficulty. The system described by Delisle in 1760, on the other hand, involves merely noting the instant of ingress or egress, according to situation, from opposite extremities of a terrestrial diameter, the disparity in time giving a measure of the planet's apparent displacement, hence of its actual rate of travel in miles per minute, from which its distances severally from earth and sun are immediately deducible. Its chief attendant difficulty is the necessity for accurately fixing the longitudes of the points of observation, but this was much more sensibly felt a century ago than it is now, the improved facility and certainty of modern determinations tending to give the Delislean plan a decided superiority over its rival. These two traditional methods were supplemented in 1874 by the camera and the heliometer. From photography, above all, much was expected. Observations made by its means would have the advantages of impartiality, multitude, and permanence. peculiarities of vision and bias of judgment would be eliminated, the slow progress of the phenomenon would permit an indefinite number of pictures to be taken, their epochs fixed to a fraction of a second, while subsequent leisurely comparison and measurement could hardly fail, it was thought, to educe approximate truth from the mass of accumulated evidence. The use of the heliometer, much relied on by German observers, was so far similar to that of the camera that the object aimed at by both was the determination of the relative positions of the centres of the Sun and Venus viewed at the same absolute instant from opposite sides of the globe, so that the principle of the two older methods was to ascertain the exact times of meeting between the solar and planetary limbs; that of the two modern to determine the position of the dark body already thrown into complete relief by its shining background. The former are methods by contact, the latter methods by projection. Every country which had a reputation to keep or to gain for scientific zeal was forward to cooperate in the great cosmopolitan enterprise of the transit. France and Germany each sent out 6 expeditions. 26 stations were in Russian, 12 in English, 8 in American, 3 in Italian, 1 in Dutch occupation. In all, at a cost of nearly $250,000, some 80 distinct posts of observation were provided, among them such inhospitable and all but inaccessible rocks in the bleak southern ocean as St. Paul's and Campbell's Islands, swept by hurricanes and fitted only for the habitation of seabirds, where the daring votaries of science, in the wise prevision of a long leaguer by the elements, were supplied with stores for many months or even a whole year. Siberia and the Sandwich Islands were thickly beset with observers. Parties of 3 nationalities encamped within the mists of Kerguelen Island, expressly termed the Land of Desolation, in the sanguine though not wholly frustrated hope of a glimpse of the sun at the right moment. M. Janssen narrowly escaped destruction from a typhoon in the China Seas on his way to Nagasaki. Lord Lindsay, now Earl of Crawford, and Balcarres equipped at his private expense an expedition to Mauritius, which was in itself an epitome of modern resource and ingenuity. During several years, the practical methods best suited to ensure success for the impending enterprise formed a subject of European debate. Official commissions were appointed to receive and decide upon evidence, and experiments were in progress for the purpose of defining the actual circumstances of contacts, the precise determination of which constituted the only tried, though by no means an assuredly safe road to the end in view. In England, America, France, and Germany, artificial transits were mounted, and the members of the various expeditions were carefully trained to unanimity in estimating the phases of junction and separation between a moving dark circular body and a broad illuminated disk. In the previous century, a formidable and prevalent phenomenon, which acquired notoriety as the black drop or black ligament, had swamped all pretensions to rigid accuracy. It may be described as substituting adhesion for contact, the limbs of the sun and planet, instead of meeting and parting with the desirable clean definiteness, clinging together as if made of some glutinous material, and prolonging their connection by means of a dark band or dark threads stretched between them. Some astronomers ascribed this baffling appearance entirely to instrumental imperfections, others to atmospheric agitation, others again to the optical encroachment of light upon darkness known as irradiation. It is probable that all these causes conspired in various measure to produce it, and it is certain that its conspicuous appearance may, by suitable precautions, be obviated. The organization of the British forces reflected the utmost credit on the energy and ability of Lieutenant Colonel Tupman, who was responsible for the whole. No useful measure was neglected. Each observer went out ticketed with his personal equation, his senses drilled into a species of martial discipline, his powers absorbed so far as possible in the action of a cosmopolitan observing machine. Instrumental uniformity and uniformity of method were obtainable and were attained, but diversity of judgment unhappily survived the best directed efforts for its extirpation. The eventful day had no sooner passed than telegrams began to pour in, announcing an outcome of considerable, though not unqualified success. The weather had proved generally favorable. The manifold arrangements had worked well, contacts had been plentifully observed, photographs in lavish abundance had been secured. A store of materials, in short, had been laid up, of which it would take years to work out the full results by calculation. Gradually, nevertheless, it came to be known that the hope of a definitive issue must be abandoned. Unanimity was found to be as remote as ever. The dreaded black ligament gave indeed less trouble than was expected, but another appearance supervened which took most observers by surprise. This was the illumination due to the atmosphere of Venus. Astronomers, it is true, were not ignorant that the planet had, on previous occasions, been seen girdled with a lucid ring. But its power to mar observations by the distorting effect of refraction had scarcely been reckoned with. It proved, however, to be very great. Such was the difficulty of determining the critical instant of internal contact that, in Colonel Tupman's words, observers side by side with adequate optical means differed as much as 20 or 30 seconds in the times they recorded for phenomena which they have described in almost identical language. Such uncertainties in the data admitted of a corresponding variety in the results. From the British observations of ingress and egress, Sir George Airy derived in 1877 a solar parallax of 8.76 minutes, corrected to 8.754 minutes, indicating a mean distance of 93,375,000 miles. Mr. Stone obtained a value of 92 millions, parallax 8.88 minutes, and held any parallax less than 8.84 minutes or more than 8.93 minutes to be absolutely negatived by the documents available. Yet from the same, Colonel Tupman deduced 8.81 minutes, implying a distance 700,000 miles greater than Stone had obtained. The best French observations of contacts gave a parallax of about 8.88 minutes. French micrometric measures the obviously exaggerated one of 9.05 minutes. Photography, as practiced by most of the European parties, was a total failure. Utterly discrepant values of the microscopic displacements designed to serve as sounding lines for the solar system issued from attempts to measure even the most promising pictures. You might as well try to measure the zodiacal light, it was remarked to Sir George Airy. Those taken on the American plan of using telescopes of so great focal length as to afford, without further enlargement, an image of the requisite size, gave notably better results. From an elaborate comparison of those dating from Vladivostok, Nagasaki, and Peking, with others from Kerguelen and Chatham Islands, Professor D. P. Todd of Amherst College deduced a solar distance of about 92 million miles, parallax 8.883 minutes, plus or minus 0.034 minutes, and the value was much favored by concurrent evidence. On the whole, estimates of the great spatial unit cannot be said to have gained any security from the combined effort of 1874. A few months before the transit, Mr. Proctor considered that the uncertainty then amounted to 1,448,000 miles. 5 years after the transit, Professor Harkness judged it to be still 1,575,950 miles, yet it had been hoped that it would have been brought down to 100,000. As regards the end for which it had been undertaken, the grand campaign had come to nothing. Nevertheless, no sign of discouragement was apparent. There was a change of view, but no relaxation of purpose. The problem, it was seen, could be solved by no single heroic effort, but by the patient approximation of gradual improvements. Astronomers accordingly looked round for fresh means or more refined expedients for applying those already known. A new phase of exertion was entered upon. On September 5, 1877, Mars came into opposition near the part of his orbit which lies nearest to that of the earth, and Dr. Gill, now Sir David, took advantage of the circumstance to appeal once more to him for a decision on the quaestio vexata of the sun's distance. He chose as the scene of his labours the island of Ascension, and for their plan a method recommended by Airy in 1857, but never before fairly tried. This is known as the diurnal method of parallaxes. Its principle consists in substituting successive morning and evening observations from the same spot for simultaneous observations from remote spots, the rotation of the earth supplying the necessary difference in the points of view. Its great advantage is that of unity in performance. A single mind looking through the same pair of eyes, reinforced with the same optical appliances, is employed throughout, and the errors inseparable from the combination of data collected under different conditions are avoided. There are many cases in which one man can do the work of two better than two men can do the work of one. The result of Gill's skilful determinations made with Lord Lindsay's heliometer was a solar parallax of 8.78 minutes, corresponding to a distance of 93,080,000 miles. The bestowal of the Royal Astronomical Society's gold medal stamped the merit of this distinguished service. But there are other subjects for this kind of inquiry besides Mars and Venus. Professor Gall of Breslau suggested in 1872 that some of the minor planets might be got to repay astronomers for much disinterested toil spent in unravelling their motions by lending aid to their efforts towards a correct celestial survey. 10 or 12 come near enough and are bright enough for the purpose. In fact, the absence of sensible magnitude is one of their chief recommendations, since a point of light offers far greater facilities for exact measurement than a disk. The first attempt to work this new vein was made at the opposition of Phocea in 1872, and from observations of Flora in the following year at 12 observatories in the northern and southern hemispheres, Gall deduced a solar parallax of 8.87 minutes. At Mauritius in 1874, Lord Lindsay and Sir David Gill applied the diurnal method to Juno, then conveniently situated for the purpose, and the continued use of similar occasions affords an unexceptionable means for improving knowledge of the sun's distance. They frequently recur, they need no elaborate preparation. A single astronomer armed with a heliometer can do all the requisite work. Dr. Gill, however, organized a more complex plan of operations upon Iris in 1888 and upon Victoria and Sappho in 1889. A novel method was adopted. Its object was to secure simultaneous observations made from opposite sides of the globe just when the planet lay in the plane passing through the centre of the earth, and the two observers, the same pair of reference stars being used on each occasion. The displacements caused by parallax were thus in a sense doubled, since the star to which the planet seemed approximated in the northern hemisphere showed as if slightly removed from it in the southern, and vice versa. As the planet pursued its course, fresh star couples came into play during the weeks that the favourable period lasted. In these determinations only heliometers were employed. Dr. Elkin of Yale College cooperated throughout, and the heliometers of Dresden, Göttingen, Bamberg, and Leipzig shared in the work, while Dr. Auwers of Berlin was Sir David Gill's personal coadjutor at the Cape. Voluminous data were collected. Meridian observations of the stars of reference for Victoria occupied 21 establishments during 4 months. The direct work of triangulation kept 4 heliometers in almost exclusive use for the best part of a year, and the ensuing toilsome computations, carried out during 3 years at the Cape Observatory, filled 2 bulky tomes with their details. Gill's final result, published in 1897, was a parallax of 8.802 minutes, equivalent to a solar distance of 92,874,000, and it was qualified by a probable error so small that the value might well have been accepted as definitive but for an unlooked-for discovery. The minor planet Eros, detected August 14, 1898, was found to pursue a course rendering it an almost ideal intermediary in solar parallax determinations. Once in 30 years it comes within 15 million miles of the Earth, and although the next of these choice epochs must be awaited for some decades, an opposition too favourable to be neglected occurred in 1900. At an international conference, accordingly, held at Paris in July of that year, a plan of photographic operations was concerted between the representatives of no less than 58 observatories. Its primary object was to secure a large stock of negatives showing the planet with the comparison stars along the route traversed by it from October 1900 to March 1901. And this at least was successfully attained. Their measurement will in due time educe the apparent displacements of the moving object as viewed simultaneously from remote parts of the earth, and the upshot should be a solar parallax adequate in accuracy to the exigent demands of the 20th century. The second of the 19th century pair of Venus transits was looked forward to with much abated enthusiasm. Russia refused her active cooperation in observing it, on the ground that oppositions of the minor planets were trigonometrically more useful and financially far less costly, and her example was followed by Austria, while Italian astronomers limited their sphere of action to their own peninsula. Nevertheless, it was generally held that a phenomenon which the world could not again witness until it was 4 generations older should, at the price of any effort, not be allowed to pass in neglect. The persuasion of its importance justified the summoning of an international conference at Paris in 1881, from which, however, America, preferring independent action, held aloof. It was decided to give Delisle's method another trial, and the ambiguities attending and marring its use were sought to be obviated by careful regulations for ensuring agreement in the estimation of the critical moments of ingress and egress. But in fact, as M. Puiseux had shown, contacts between the limbs of the sun and planet, so far from possessing the geometrical simplicity attributed to them, are really made up of a prolonged succession of various and varying phases, impossible either to predict or identify with anything like rigid exactitude. Sir Robert Ball compared the task of determining the precise instant of their meeting or parting to that of telling the hour with accuracy on a watch without a minute hand, and the comparison is admittedly inadequate, For not only is the apparent movement of Venus across the sun extremely slow, being but the excess of her real motion over that of the earth, but three distinct atmospheres, the solar, terrestrial, and Cytherean, combine to deform outlines and mask the geometrical relations which it is desired to connect with a strict count of time. The result was very much what had been expected. The arrangements were excellent, and were only in a few cases disconcerted by bad weather. The British parties, under the experienced guidance of Mr. Stone, the late Radcliffe observer, took up positions scattered over the globe from Queensland to Bermuda. The Americans collected a whole library of photographs. The Germans and Belgians trusted to the heliometer. The French used the camera as an adjunct to the method of contacts. Yet little or no approach was made to solving the problem. Thus, from 606 measures of Venus on the sun, taken with a new kind of heliometer at Santiago in Chile, M. Houzeau of the Brussels Observatory derived a solar parallax of 8.907 minutes, and a distance of 91,727,000 miles. But the probable errors of this determination amounted to 0.084 minutes either way. It was subject to a more or less of 900,000, or to a total uncertainty of 1,800,000 miles. The probable error of the English result, published in 1887, was less formidable, yet the details of the discussion showed that no great confidence could be placed in it. The sun's distance came out 92,560,000 miles, while 92,360,000 was given by Professor Harkness's investigation of 1,475 American photographs. Finally, Dr. Auwers deduced from the German heliometric measures the unsatisfactorily small value of 92 million miles. The transit of 1882 had not then brought about the desired unanimity. The state and progress of knowledge on this important topic were summed up by Faye and Harkness in 1881. The methods employed in its investigation fall, as we have seen, into three separate classes: the trigonometrical, the gravitational, and the phototachymetrical, an ungainly adjective used to describe the method by the velocity of light. Each has its special difficulties and sources of error. Each has counterbalancing advantages. The only trustworthy result from celestial surveys was at that time furnished by Gill's observations of Mars in 1877. But the method by lunar and planetary disturbances is unlike all the others in having time on its side. It is this which Leverrier declared with emphasis must inevitably prevail, because its accuracy is continually growing. The scarcely perceptible errors which still impede its application are of such a nature as to accumulate year by year. Eventually, then, they will challenge, and must receive a more and more perfect correction. The light velocity method, however, claimed, and for some years justified, M. Faye's preference. By a beautiful series of experiments on Foucault's principle, Michelson fixed in 1879 the rate of luminous transmission at 299,930, corrected later to 299,910 kilometers a second. This determination was held by Professor Todd to be entitled to 4 times as much confidence as any previous one, and if the solar parallax of 8.758 minutes deduced from it by Professor Harkness errs somewhat by defect, it is doubtless because Glasenapp's light equation, with which it was combined, errs slightly by excess. But all earlier efforts of the kind were thrown into the shade by Professor Newcomb's arduous operations at Washington in 1880 to 1882. The scale upon which they were conducted was in itself impressive. Foucault's entire apparatus in 1862 had been enclosed in a single room. Newcomb's revolving and fixed mirrors, between which the rays of light were to run their timed course, were set up on opposite shores of the Potomac at a distance of nearly 4 kilometers. This advantage was turned to the utmost account by ingenuity and skill in contrivance and execution, and the deduced velocity of 299,860 kilometers equals 186,328 miles a second, had an estimated error, 30 kilometers, only 1/10 that ascribed by Cornu to his own result in 1874. Just as these experiments were concluded in 1882, M. Magnus Néron of St. Petersburg published an elaborate investigation of the small annular displacements of the stars due to the successive transmission of light, involving an increase of Struve's constant of aberration from 20.445 minutes to 20.492 minutes. And from the new value, combined with Newcomb's light velocity, was derived a valuable approximation to the sun's distance, concluded at 92,905,021 miles. Parallax equals 8.794 minutes. Yet it is not quite certain that Néron's correction was an improvement. A differential method of determining the amount of aberration struck out by M. Lowery of Paris avoids most of the objections to the absolute method previously in vogue, and the upshot of its application in 1891 was to show that Struve's constant might better be retained than altered, Lowery's of 20.447 minutes varying from it only to an insignificant extent. Professor Hall had moreover deduced nearly the same value, 20.454 minutes, from the Washington observations since 1862 of Alpha Lyrae Vega, whence, in conjunction with Newcomb's rate of light transmission, he arrived at a solar parallax of 8.81 minutes. Inverting the process, Sir David Gill in 1897 derived the constant from the parallax. If the Earth's orbit have a mean radius, as found by him, of 92,874,000 miles, then he calculated the aberration of light. Newcomb's measures of its velocity being supposed exact, amounts to 20.467 minutes. This figure can need very slight correction. Professor Harkness surveyed in 1891, from an eclectic point of view, the general situation as regarded the sun's parallax. Convinced that no single method deserved an exclusive preference, he reached a plausible result through the combination, on the principle of least squares, that is, by the mathematical rules of probability, of all the various quantities upon which the great datum depends. It thus summed up and harmonized the whole of the multifarious evidence bearing upon the point, and as modified in 1894, falls very satisfactorily into line with the Cape determination. We may then at least provisionally accept 92,870,000 miles as the length of our measuring rod for space, nor do we hazard much in fixing 100,000 miles as the outside limit of its future correction. End of chapter 6.
Chapter 7 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary CLERKE. Chapter 7, Part 1. Planets and Satellites. Johann Hieronymus Schröter was the Herschel of Germany. He did not, it is true, possess the more brilliant gifts of his rival. Herschel's piercing discernment, comprehensive intelligence, and inventive splendor were wanting to him. He was nevertheless the founder of descriptive astronomy in Germany, as Herschel was in England. Born in Erfurt in 1745, he prosecuted legal studies at Göttingen, and there imbibed from Kastner a lifelong devotion to science. From the law, however, he got the means of living, and what was to the full as precious to him, the means of observing. Entering the sphere of Hanoverian officialism in 1788, he settled a few years later at Lilienthal, near Bremen, as Oberamtmann, or chief magistrate. Here he built a small observatory, enriched in 1785 with a 7-foot reflector by Herschel, then one of the most powerful instruments to be found anywhere out of England. It was soon surpassed, through his exertions, by the first fruits of native industry in that branch. Schrader of Kiel transferred his workshops to Lilienthal in 1792, and constructed there, under the superintendence and at the cost of the astronomical Oberamtmann, a 13-foot reflector, declared by Lalande to be the finest telescope in existence, and one 27 feet in focal length, probably as inferior to its predecessor in real efficiency as it was superior in size. Thus, with the instruments of gradually increasing power, Schrader studied during 34 years the topography of the moon and planets. The field was then almost untrodden. He had but few and casual predecessors, and has since had no equal in the sustained and concentrated patience of his hourly watchings. Both their prolixity and their enthusiasm are faithfully reflected in his various treatises, yet the one may be pardoned for the sake of the other, especially when it is remembered that he struck out a substantially new line, and that one of the main lines of future advance. Moreover, his infectious zeal communicated itself. He set the example of observing when there was scarcely an observer in Germany, and under his roof Harding and Bessel received their training as practical astronomers. But he was reserved to see evil days. Early in 1813, the French under Vandamme occupied Bremen. On the night of April 20, the Vale of Lilies was, by their wanton destructiveness, laid waste with fire. The government offices were destroyed, and with them the chief part of Schroeder's property, including the whole stock of his books and writings. There was worse behind. A few days later, his observatory, which had escaped the conflagration, was broken into, pillaged, and ruined. His life was wrecked with it. He survived the catastrophe 3 years without the means to repair, or the power to forget it, and gradually sank from disappointment into decay, terminated by death August 29, 1816. He had, indeed, done all the work he was capable of, and though not of the first quality, it was far from contemptible. He laid the foundation of the new comparative study of the moon's surface, and the descriptive particulars of the planets laboriously collected by him constituted a store of more or less reliable information, hardly added to during the ensuing half-century. They rested, it is true, under some shadow of doubt, but the most recent observations have tended on several points to rehabilitate the discredited authority of the Lilienthal astronomer. We may now briefly resume and pursue in its further progress the course of his studies, taking the planets in the order of their distances from the sun. In April 1792, Schroeder saw reason to conclude, from the gradual degradation of light on its partially illuminated disk, that Mercury possesses a tolerably dense atmosphere. During the transit of May 7, 1799, he was moreover struck with the appearance of a ring of softened luminosity encircling the planet to an apparent height of 3 seconds, or about a quarter of its own diameter. Although a mere thought in texture, it remained persistently visible, both with the 7-foot and the 13-foot reflectors armed with powers up to 288. It had a well-marked grayish boundary, and reminded him, though indefinitely fainter, of the penumbra of a sunspot. A similar appendage had been noticed by Duplantier at Montpellier, November 11, 1736, and again in 1786 and 1789 by Prosperin and Fleugergus. But Herschel, on November 9, 1802, saw the preceding limb of the planet projected on the sun cut the luminous solar clouds with the most perfect sharpness. The presence, however, of a halo was unmistakable in 1832, when Professor Moll of Utrecht described it as a nebulous ring of a darker tinge approaching to the violet color. Again, to Huygens and Stone, November 5, 1868, it showed as lucid and most distinct. No change in the color of the glasses used or the powers applied could get rid of it, and it lasted throughout the transit. It was next seen by Christie and Duncan at Greenwich, May 6, 1878, and with much precision of detail by Trouvelot at Cambridge, U.S. Professor Holden, on the other hand, noted at Hastings-on-Hudson the total absence of all anomalous appearances. Nor could any vestige of them be perceived by Barnard at Lick on November 10, 1894. Various effects of irradiation and diffraction were, however, observed by Lowell and W. H. Pickering at Flagstaff, and Davidson was favored at San Francisco with glimpses of the historic aureola, as well as of a central whitish spot, which often accompanies it. That both are somehow of optical production can scarcely be doubted. Nothing can be learned from them regarding the planet's physical condition. Airy showed that refraction in a Mercurian atmosphere could not possibly originate the noted aureola, which must accordingly be set down as strictly an ocular nervous phenomenon. It is less easy to escape from this conclusion that we find the virtually airless moon capable of exhibiting a like appendage. Professor Stephen Alexander of the United States Survey, with two other observers, perceived during the eclipse of the sun of July 18, 1860, the advancing lunar limb to be bordered with a bright band, and photographic effects of the same kind appear in pictures of transits of Venus and partial solar eclipses. The spectroscope affords little information as to the constitution of Mercury. Its light is, of course, that of the sun reflected, and its spectrum is consequently a faint echo of the Fraunhofer spectrum. Dr. H. C. Vogel, who first examined it in April 1871, suspected traces of the action of an atmosphere like ours, but it would seem on slight grounds. It is, however, certainly very poor in blue rays. More definite conclusions were, in 1874, derived by Zollner from photometric observations of Mercurian phases. A similar study of the waxing and waning moon had afforded him the curious discovery that light changes dependent upon phase vary with the nature of the reflecting surface, following a totally different law on a smooth, homogeneous globe and on a rugged and mountainous one. Now, the phases of Mercury, so far as could be determined from only two sets of observations, correspond with the latter kind of structure. Strictly analogous to those of the moon, they seem to indicate an analogous mode of surface formation. This conclusion was fully borne out by Müller's more extended observations at Potsdam during the years 1885 to 1893. Practical assurance was gained from them that the innermost planet has a rough rind of dusky rock, absorbing all but 17% of the light poured upon it by the fierce adjacent sun. Its albedo, in other words, is 0.17, which is precisely that ascribed to the moon. The absence of any appreciable Mercurian atmosphere followed almost necessarily from these results. On March 26, 1800, Schroeter, observing with his 13-foot reflector in a peculiarly clear sky, perceived the southern horn of Mercury's crescent to be quite distinctly blunted. Interception of sunlight by a Mercurian mountain, rather more than 11 English miles high, explained the effect to his satisfaction. By carefully timing its recurrence, he concluded rotation on an axis in a period of 24 hours 4 minutes. The first determination of the kind rewarded 20 years of unceasing vigilance. It received ostensible confirmation from the successive appearances of a dusky streak and blotch in May and June 1801. These, however, were inferred to be no permanent markings on the body of the planet, but atmospheric formations, the streak at times drifting forwards, it was thought, under the fluctuating influence of Mercurian breezes. From a rediscussion of these somewhat doubtful observations, Bessel inferred that Mercury rotates on an axis inclined 70 degrees to the plane of its orbit in 24 hours 53 seconds. The rounded appearance of the southern horn seen by Schröter was more or less doubtfully caught by Noble 1864, Burton and Franks 1877, but was obvious to Mr. W. F. Denning at Bristol on the morning of November 5, 1882. That the southern polar regions are usually less bright than the northern is well ascertained, but the cause of the deficiency remains dubious. If inequalities of surface are in question, they must be on a considerable scale, and a similar explanation might be given of the deformations of the terminator, or dividing line between darkness and light in the planet's phases, first remarked by Schröter, and again clearly seen by Trouvelot in 1878 and 1881. The displacement during 4 days of certain brilliant and dusky spaces on the disk indicated to Mr. Denning in 1882 rotation in about 25 hours, while the general aspect of the planet reminded him of that of Mars. But the difficulties in the way of its observation are enormously enhanced by its constant close attendance on the sun. In his sustained study of the features of Mercury, Schröter had no imitator until Schiaparelli took up the task at Milan in 1882. His observations were made in daylight. It was found that much more could be seen, and higher magnifying powers used, high up in the sky near the sun than at low altitudes through the agitated air of morning or evening twilight. A notable discovery ensued. Following the planet hour by hour, instead of making necessarily brief inspections at intervals of about a day, as previous observers had done, it was found that the markings faintly visible remained sensibly fixed, hence that there was no rotation in a period at all comparable with that of the earth, and after long and patient watching, the conclusion was at last reached that Mercury turns on his axis in the same time needed to complete a revolution in his orbit. One of his hemispheres, then, is always averted from the sun, as one of the moon's hemispheres from the earth, while the other never shifts from beneath his torrid rays. The librations, however, of Mercury are on a larger scale than those of the moon, because he travels in a more eccentric path. The temporary inequalities arising between his even pacing on an axis and his alternately accelerated and retarded elliptical movement occasion, in fact, an oscillation to and fro of the boundaries of light and darkness on his globe over an arc of 47 degrees 22 minutes in the course of his year over 88 days. Thus, the regions of perpetual day and perpetual night are separated by 2 segments, amounting to 1/4 of the entire surface, where the sun rises and sets once in 88 days. Else there is no variation from the intense glare on one side of the globe, and the nocturnal blackness on the other. To Schiaparelli's scrutiny, Mercury appeared as a spotty globe, enveloped in a tolerably dense atmosphere. The brownish stripes and streaks discerned on his rose-tinged disk, and judged to be permanent, were made the basis of a chart. They were not, indeed, always equally well seen. They disappeared regularly near the limb, and were at times veiled even when centrally situated. Some of them had been clearly perceived by de Ball at Bothkamp in 1882. Mr. Lowell followed Schiaparelli's example by observing Mercury in the full glare of noon. "The best time to study him," he remarked, "is when planetary almanacs state Mercury invisible." A remarkable series of drawings executed, some at Flagstaff in 1896, the remainder at Mexico in 1897, supplied grounds for the following, among other conclusions. Mercury rotates synchronously with its revolution, that is, once in 88 days, on an axis sensibly perpendicular to its orbital plane. No certain signs of a Mercurian atmosphere are visible. The globe is seamed and furrowed with long narrow markings, explicable as cracks in cooling. It is and always was a dead world. From micrometrical measures, moreover, the inferences were drawn that the planet's mass had a probable value about 1/20th that of the Earth, while its mean density falls considerably short of the terrestrial standard. The theory of Mercury's movements has always given trouble. In Lalande's as in Maslin's time, the planet seemed to exist for no other purpose than to throw discredit on astronomers, and even to Leverrier's powerful analysis it long proved recalcitrant. On the 12th of September, 1869, however, he was able to announce before the Academy of Sciences the terms of a compromise between observation and calculation. They involved the addition of a new member to the solar system, the hitherto unrecognized presence of a body about the size of Mercury itself, revolving at somewhat less than half its mean distance from the sun, or if farther, then of less mass, and vice versa, would, it was pointed out, produce exactly the effect required, of displacing the perihelion of the former planet 38 minutes, a century more than could otherwise be accounted for. The planes of the two orbits, however, should not lie far apart, as otherwise a nodal disturbance would arise not perceived to exist. It was added that a ring of asteroids similarly placed would answer the purpose equally well, and it was more likely to have escaped notice. Upon the heels of this forecast followed promptly a seeming verification. Dr. Lescarbault, a physician residing at Orgères, whose slender opportunities had not blunted his hopes of achievement, had, ever since 1845, when he witnessed the transit of Mercury, cherished the idea that an unknown planet might be caught thus projected on the solar background. Unable to observe continuously until 1858, he, on March 26, 1859, saw what he had expected, a small, perfectly round object slowly traversing the sun's disk. The fruitless expectation of re-observing the phenomena, however, kept him silent, and it was not until December 22nd, after the news of Leverrier's prediction had reached him, that he wrote to acquaint him with his supposed discovery. The imperial astronomer thereupon hurried down to Orgères, and by his personal inspection of the simple apparatus used, by searching cross-examination and local inquiry, convinced himself of the genuine character and substantial accuracy of the reported observation. He named the new planet Vulcan, and computed elements, giving it a period of revolution slightly under 20 days. But it has never since been seen. M. Lais, director of the Brazilian Coast Survey, thought himself justified in asserting that it never had been seen. Observing the sun for 12 minutes after the supposed ingress recorded at Orgères, he noted those particular regions of its surface as très uniformes d'intensité. He subsequently, however, admitted Lescarbault's good faith, at first rashly questioned. The planet-seeking doctor was, in truth, only one among many victims of similar illusions. Waning interest in the subject was revived by a fresh announcement of a transit witnessed, it was asserted, by Weber at Pecolo, April 4th, 1876. The pseudo-planet, indeed, was detected shortly afterwards on the Greenwich photographs, and was found to have been seen by M. Ventosa at Madrid in its true character of a sunspot without penumbra. But Leverrier had meantime undertaken the investigation of a list of 20 similar dubious appearances collected by Haas and published by Wolf in 1872. From these, 5 were picked out as referring in all likelihood to the same body, the reality of whose existence was now confidently asserted, and of which more or less probable transits were fixed for March 22, 1877 and October 15, 1882. But, widespread watchfulness notwithstanding, no suspicious object came into view at either epoch. The next announcement of the discovery of Vulcan was on the occasion of the total solar eclipse of July 29, 1878. This time it was stated to have been seen at some distance southwest of the obscured sun as a ruddy star with a minute planetary disk, and its simultaneous detection by 2 observers, the late Professor James C. Watson, stationed at Rawlins, Wyoming Territory, and Professor Lewis Swift at Denver, Colorado, was at first readily admitted. But their separate observations could, on a closer examination, by no possibility be brought into harmony, and if valid, certainly referred to 2 distinct objects, if not to 4, each astronomer eventually claiming a pair of planets. Nor could any one of the 4 be identified with Lescarbault's and Leverrier's Vulcan, which, if substantial body revolving round the sun, must then have been found on the east side of that luminary. The most feasible explanation of the puzzle seems to be that Watson and Swift merely saw each the same 2 stars in Cancer, haste and excitement doing the rest. Nevertheless, they strenuously maintained their opposite conviction. Intra-Mercurian planets have since been diligently searched for when the opportunity of a total eclipse offered, especially during the long obscuration at Caroline Island. Not only did Professor Holden sweep in the solar vicinity, but Palisa and Trouvelot agreed to divide the field of exploration and thus make sure of whatever planetary prey there might be within reach, yet with only negative results. Photographic explorations during recent eclipses have been equally fruitless. Belief in the presence of any considerable body or bodies within the orbit of Mercury is accordingly at a low ebb. Yet the existence of the anomaly in the Mercurian movements indicated by Leverrier has been made only surer by further research. Its elucidation constitutes one of the pending problems of astronomy. End of Chapter 7, Part 1. Chapter 7 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary CLERKE. Chapter 7, Part 2, Planets and Satellites. From the observation at Bologna in 1666 through 67 of some very faint spots, Domenico Cassini concluded a rotation or libration of Venus, he was not sure which, in about 23 hours. By Bianchini in 1726, the period was augmented to 24 days, 8 hours. J. Cassini, however, in 1740 showed that the data collected by both observers were consistent with rotation in 23 hours, 20 minutes. So the matter rested until Schroeder's time. After watching 9 years in vain, he at last, February 28, 1788, perceived the ordinarily uniform brightness of the planet's disk to be marbled with a filmy streak, which returned periodically to the same position in about 23 hours, 28 minutes. This approximate estimate was corrected by the application of a more definite criterion. On December 28, 1789, the southern horn of the crescent Venus was seen truncated, an outlying lucid point interrupting the darkness beyond. Precisely the same appearance recurred 2 years later, giving for the planet's rotation a period of 23 hours 21 minutes. To this, only 22 seconds were added by de Vico as a result of over 10,000 observations made with the Cauchois refractor of the Collegio Romano, 1839 to 41. The axis of rotation was found to be much more bowed towards the orbital plane than that of the Earth, the equator making with it an angle of 53 degrees 11 minutes. These conclusions inspired, it is true, much distrust. Consequently, there were no received ideas on the subject to be subverted. Nevertheless, a shock of surprise was felt at Schiaparelli's announcement early in 1890 that Venus most probably rotates after the fashion just previously ascribed to Mercury. A continuous series of observations from November 1877 to February 1878, with their records in above 100 drawings, supplied the chief part of the data upon which he rested his conclusions. They certainly appeared exceptionally well grounded, and the doubts at first qualifying them were removed by a fresh set of determinations in July 1895. Most observers had depended, in their attempts to ascertain the rotation period of Venus, upon evanescent shadings, most likely of atmospheric origin and scarcely recognizable from day to day. Schiaparelli fixed his attention upon round, defined, lustrously white spots, the presence of which near the cusps of the illuminated crescent has been attested for close upon 2 centuries. His steady watch over them showed the invariability of their position with regard to the terminator, and this is as much as to say that the regions of day and night do not shift on the surface of the planet. In other words, she keeps the same face always turned towards the sun. Moreover, since her orbit is nearly circular, libratory effects are very small. They amount, in fact, to only just 1/30th of those serving to modify the severe contrasts of climate in Mercury. Confirmatory evidence of Schiaparelli's result for Venus is not wanting. Thus, observations irreconcilable with a swift rate of rotation were made at Bothkamp in 1871 by Vogel and Losig, and a drawing executed by Professor Holden with the great Washington reflector, December 15, 1877, showed the same markings in the positions recorded at Milan to have been occupied by them 8 hours previously. Further, a series of observations carried out by Mr. Perrotin at Nice, May 15 to October 4, 1890, and from Mount Mounier in 1895-6, with the special aim of testing the inference of synchronous rotation and revolution, proved strongly corroborative of it. A remarkable collection of drawings made by Mr. Lowell in 1896 appeared decisive in its favor. Ticini at Rome, Mascari at Catania and Etna, Cerulli at Tirano obtained in 1892-6 evidence similar in purport. On the other hand, Neaston of Brussels found reason to revert de Vico's discarded elements for the planet's rotation, and Trouvelot, Stanley Williams, Villager, and Leo Brenner so far agreed with him as to adopt a period of approximately 24 hours. Finally, E. von Oppolzer suggested an appeal to the spectroscope, and Belopolsky secured in 1900 spectrograms apparently marked by the minute displacements corresponding to a rapid rate of axial movement, but they were avowedly taken only as an experiment with unsuitable apparatus, and the desirable verification of their supposed import is not yet forthcoming. Until it is, Schiaparelli's period of 225 days must be allowed to hold the field. Effects attributed to great differences of level in the surface of Venus have struck many observers. Francesco Fontana at Naples in 1643 noticed irregularities along the inner edge of the crescent. Lahire in 1700 considered them. Regard being had to difference of distance to be much more strongly marked than those visible in the moon. Schroeter's assertions to the same effect, though scouted with some unnecessary vehemence by Herschel, have since been repeatedly confirmed, amongst others by Madler, de Vico, Langdon, who in 1873 saw the broken line of the terminator with peculiar distinctness through a veil of auroral cloud, by Denning, March 30, 1881, despite preliminary impressions to the contrary, as well as by C.V. Zenger at Prague, January 8, 1883. The great mountain mass, presumed to occasion the periodical blunting of the southern horn, was precariously estimated by the Lilienthal observer to rise to the prodigious height of nearly 27 miles, or just 5 times the elevation of Mount Everest. Yet the phenomenon persists, whatever may be thought of the explanation. Moreover, the speck of light beyond, interpreted as the visible sign of a detached peak rising high enough above the encircling shadow to catch the first and last rays of the sun, was frequently discerned by Baron von Erdborn in 1876, while an object near the northern horn of the crescent, strongly resembling a lunar ring mountain, was delineated both by de Vico in 1841 and by Denning 40 years later. We are almost equally sure that Venus, as that the Earth, is encompassed with an atmosphere. Yet notwithstanding luminous appearances plainly due to refraction during the transits both of 1761 and 1769, Schroeter in 1792 took the initiative in coming to a definite conclusion on the subject. It was founded first on the rapid diminution of brilliancy towards the terminator, attributed to atmospheric absorption. Next, on the extension beyond a semicircle of the horns of the crescent. Lastly, on the presence of a bluish gleam illuminating the early hours of the Cytherean night with what was taken to be genuine twilight. Even Herschel admitted that sunlight, by the same effect through which the heavenly bodies show visibly above our horizons, while still geometrically below them, appeared to be bent round the shoulder of the globe of Venus. Ample confirmation of the fact has since been afforded. At Dorpat in May 1849, the planet being within 3 degrees 26 minutes of inferior conjunction, Madler found the arms of waning light upon the disk to embrace no less than 240 degrees of its extent. And in December 1842, Mr. Guthrie of Burvey, New Brunswick, actually observed, under similar conditions, the whole circumference to be lit up with a faint nebulous glow. The same curious phenomenon was intermittently seen by Mr. Leeson Prince at Uckfield in September 1861, but with more satisfactory distinctness by Mr. C.S. Lyman of Yale College before and after the conjunction of December 11, 1866, and during nearly 5 hours previous to the transit of 1874, when the yellowish ring of refracted light showed at one point an approach to interruption, possibly through the intervention of a bank of clouds. Again, on December 2, 1898, Venus being 1 degrees 45 minutes from the sun's center, Mr. H. N. Russell of the Halstead Observatory descried the coalescence of the cusps and founded on the observation a valuable discussion of such effects. Taking account of certain features in the case left unnoticed by Neison and Proctor, he inferred from them the presence of a Cytherean atmosphere, considerably less refractive than our own, although possibly, in its lower strata, encumbered with dust or haze. Similar appearances are conspicuous during transits, but while the Mercurian halo is characteristically seen on the sun, the silver thread round the limb of Venus commonly shows on the part off the sun. There are, however, instances of each description in both cases. Mr. Grant, in collecting the records of physical phenomena accompanying the transits of 1761 and 1769, remarks that no one person saw both kinds of annulus, and argues a dissimilarity in their respective modes of production. Such a dissimilarity probably exists, in the sense that the inner section of the ring is illusory, the outer a genuine result of the bending of light in a gaseous envelope. But the distinction of separate visibility has not been borne out by recent experience. Several of the Australian observers during the transit of 1874 witnessed the complete phenomenon. Mr. J. McDonnell at Eden saw a shadowy nebulous ring surround the whole disk, when ingress was 2/3 accomplished. Mr. Tornaghi at Goulburn perceived a halo entire and unmistakable at half egress. Similar observations were made at Sydney, and were renewed in 1882 by Lescarbault at Augeries, by Metzger in Java, and by Barnard at Vanderbilt University. Spectroscopic indications of aqueous vapor, as present in the atmosphere of Venus, were obtained in 1874 and 1882 by Ticini and Rico in Italy, and by Young in New Jersey. Janssen, however, who made a special study of the point subsequently to the transit of 1882, found them much less certain than he had anticipated, and Vogel, by repeated examinations, 1871 through 73, could detect only the very slightest variations from the pattern of the solar spectrum. Some additions there indeed seem to be in the thickening of a few water and oxygen lines, but so nearly evanescent as to induce the persuasion that most of the light we receive from Venus has traversed only the tenuous upper portion of its atmosphere. It is reflected at any rate with comparatively slight diminution. On the 26th and 27th of September 1878, a close conjunction gave Mr. James Nasmyth the rare opportunity of watching Venus and Mercury for several hours side by side in the field of his reflector, when the former appeared to him like clean silver, the latter as dull as lead or zinc. Yet the light incident upon Mercury is on average 3.5 times as strong as the light reaching Venus. Thus the reflective power of Venus must be singularly strong, and we find accordingly from a combination of Zollner's with Muller's results that its albedo is but little inferior to that of new fallen snow. In other words, it gives back 77% of the luminous rays impinging upon it. This extraordinary brilliancy would be intelligible were it permissible to suppose that we see nothing of the planet but a dense canopy of clouds. But the hypothesis is discountenanced by the Flagstaff observations, and is irreconcilable with the visibility of mountainous elevations and permanent surface markings. To Mr. Lowell, these were so distinct and unchanging as to furnish data for a chart of the Cytherean globe, and the peculiar arrangement of divergent shading exhibited in it cannot offhand be set down as unreal, in view of Perrotin's earlier discernment of analogous linear traces. Gruithuisen's snowcaps, however, it is safe to say, do not exist as such, although shining regions near the poles form a well-attested trait of the strange Cytherean landscape. The secondary or ashen light of Venus was first noticed by Riccioli in 1643. It was seen by Derham about 1715, by Kirch in 1721, by Schroeter and Harding in 1806, and the reality of the appearance has since been authenticated by numerous and trustworthy observations. It is precisely similar to that of the old moon in the new moon's arms, and Zenger, who witnessed it with unusual distinctness January 8, 1883, supposes it due to the same cause, namely, to the faint gleam of reflected Earth light from the night side of the planet. When we remember, however, that full Earth light on Venus at its nearest has little more than 1/12,000th its intensity on the Moon, we see at once that the explanation is inadequate. Nor can Professor Safaric's, by phosphorescence of the warm and teeming oceans with which Zollner regarded the globe of Venus as mainly covered, be seriously entertained. Vogel's suggestion is more plausible. He and O. Lohse at Bothkamp, November 3–11, 1871, saw the dark hemisphere partially illuminated by secondary light, extending 30 degrees from the terminator, and thought the effect might be produced by a very extensive twilight. Others have had recourse to the analogy of our aurorae, and J. Lamp suggested that the grayish gleam visible to him at Bothkamp October 21 and 26, 1887, might be an accompaniment of electrical processes connected with the planet's meteorology. Whatever the origin of the phenomenon, it may serve, on a night-enwrapped hemisphere, to dissipate some of the thick darkness otherwise encroached upon only by the pale light of stars. Venus was once supposed to possess a satellite, but belief in its existence has died out. No one indeed has caught even a deceptive glimpse of such an object during the last 125 years. Yet it was repeatedly, and one might have thought, well observed in the 17th and 18th centuries. Fontana discovered it in 1645. Cassini, an adept in the art of seeing, recognized it in 1672 and again in 1686. Short watched it for a full hour in 1740 with varied instrumental means. Tobias Mayer in 1759, Montaigne in 1761, several astronomers at Copenhagen in March 1764 noted what they considered its unmistakable presence, as did Horrebow in 1768. But Paul Struban, who in 1887 submitted all the available data on the subject to a searching examination, identified Horrebow's satellite with Libra, a fifth magnitude star, and a few other apparitions were by his industry similarly explained away. Nevertheless, several withstood all efforts to account for them, and together form a most curious case of illusion, for it is quite certain that Venus has no such conspicuous attendant. The third planet encountered in traveling outward from the sun is the abode of man. He has in consequence opportunities for studying its physical habitudes altogether different from the baffling glimpse afforded to him of the other members of the solar family. Regarding the earth, then, a mass of knowledge so varied and comprehensive has been accumulated as to form a science, or rather several sciences apart. But underneath all lie astronomical relations, the recognition and investigation of which constitute one of the most significant intellectual events of the present century. It is indeed far from easy to draw a line of logical distinction between items of knowledge which have their proper place here and those which should be left to the historian of geology. There are some, however, of which the cosmical connections are so close that it is impossible to overlook them. Among these is the ascertainment of the solidity of the globe. At first sight, it seems difficult to conceive what the apparent positions of the stars can have to do with subterranean conditions. Yet it was from star measurements alone that Hopkins, in 1839, concluded the earth to be solid to a depth of at least 800 or 1,000 miles. His argument was that if it were a mere shell filled with liquid, precession and nutation would be much larger than they are observed to be, for the shell alone would follow the pull of the sun and moon on its equatorial girdle, leaving the liquid behind, and being thus so much the lighter, would move the more readily. There is, it is true, grave reason to doubt whether this reasoning corresponds with the actual facts of the case, but the conclusion to which it led has been otherwise affirmed and extended. Indications of an identical purport have been derived from another kind of external disturbance affecting our globe through the same agencies. Lord Kelvin, then Sir William Thomson, pointed out in 1862 that tidal influences are brought to bear on land as well as on water, although obedience to them is perceptible only in the mobile element. Some bodily distortion of the Earth's figure must, however, take place, unless we suppose it is of absolute or preternatural rigidity, and the amount of such distortion can be determined from its effect in diminishing oceanic tides below their calculated value. For if the Earth were perfectly plastic to the stresses of solar and lunar gravity, tides, in the ordinary sense, would not exist. Continents and oceans would swell and subside together. It is to the difference in the behavior of solid and liquid terrestrial constituents that the ebb and flow of the waters are due. 6 years later, the distinguished Glasgow professor suggested that this criterion might, by the aid of a prolonged series of exact tidal observations, be practically applied to test the interior condition of our planet. In 1882, accordingly, suitable data extending over 33 years having at length become available, Mr. G. H. Darwin performed the laborious task of their analysis, with the general result that the effective rigidity of the Earth's mass must be at least as great as that of steel. Ratification from an unexpected quarter has lately been brought to this conclusion. The question of a possible mobility in the Earth's axis of rotation has often been mooted. Now at last it has received an affirmative reply. Dr. Kustner detected, in his observations of 1884 through 85, effects apparently springing from a minute variation in the latitude of Berlin. The matter having been brought before the International Geodetic Association in 1888, special observations were set on foot at Berlin, Potsdam, Prague, Strasbourg, the upshot of which was to bring plainly to view synchronous and seemingly periodic fluctuations of latitude to the extent of half a second of arc. The reality of these was verified by an expedition to Honolulu in 1891 through 92, the variations there corresponding inversely to those simultaneously determined in Europe. Their character was completely defined by Mr. S. C. Chandler's discussion in October of 1891. He showed that they could be explained by supposing the pole of the Earth to describe a circle with a radius of 30 feet in a period of 14 months. Confirmation of this hypothesis was found by Dr. B. A. Gould in the Cordoba observations, and it was provided with a physical basis through the able cooperation of Professor Newcomb. The Earth, owing to its ellipsoidal shape, should, apart from disturbance, rotate upon its axis of figure, or shortest diameter, since thus alone can the centrifugal forces generated by its spinning balance each other. Temporary causes, however, such as heavy falls of snow or rain, limited to one continental area, the shifting of ice masses, even the movements of winds, may render the globe slightly lopsided, and thus oblige it to forsake its normal axis and rotate on one somewhat divergent from it. This instantaneous axis, for it is incessantly changing, must, by mathematical theory, revolve round the axis of figure in a period of 306 days. Provided, that is to say, the Earth were a perfectly rigid body. But it is far from being so. It yields sensibly to every strain put upon it, and this yielding tends to protract the time of circulation of the displaced pole. The length of its period, then, serves as a kind of measure of the plasticity of the globe, which, according to Newcomb's and S.S. Howe's independent calculations, seems to be a little less than that of steel. In an earth compacted of steel, the instantaneous axis would revolve in 441 days. In the actual Earth, the process is accomplished in 428 days. By this new path, accordingly, astronomers have been led to an identical estimate of the consistence of our globe with that derived from tidal investigations. Variations of latitude are intrinsically complex. To produce them, an incalculable interplay of causes must be at work, with each its proper period and law of action. All the elements of the phenomenon are then in a perpetual state of flux, and absorb for their continual redetermination the arduous and combined labors of many astronomers. Nor is this trouble superfluous. Minute in extent though they be, the shiftings of the pole menace the very foundations of exact celestial science. Their neglect would leave the entire fabric insecure. Just at the beginning of the present century, they reached a predicted minimum, but are expected again to augment their range after the year 1902. The interesting suggestion has been made by Mr. J. Halm that such fluctuations are in some obscure way affected by changes in solar activity and conform like them to an 11-year cycle. In a paper read before the Geological Society, December 15, 1830, Sir John Herschel threw out the idea that the perplexing changes of climate revealed by the geological record might be explained through certain slow fluctuations in the eccentricity of the Earth's orbit, produced by the disturbing action of the other planets. Shortly afterwards, however, he abandoned the position as untenable, and it was left to the late Dr. James Croll in 1864 and subsequent years to reoccupy and fortify it. Within restricted limits, as Lagrange and more certainly and definitively Leverrier proved, the path pursued by our planet round the sun alternately contracts in the course of ages into a moderate ellipse and expands almost to a circle. The major axis and consequently the mean distance remaining invariable. Even at present, when the eccentricity approaches a minimum, the sun is nearer to us in January than in July by above 3 million miles, and some 850,000 years ago this difference was more than 4 times as great. Dr. Croll brought together a mass of evidence to support the view that at epochs of considerable eccentricity, the hemisphere of which the winter, occurring at aphelion, was both intensified and prolonged, must have undergone extensive glaciation, while the opposite hemisphere, with a short mild winter and long cool summer, enjoyed an approach to perennial spring. These conditions were exactly reversed at the end of 10,500 years, through the shifting of the perihelion combined with the precession of the equinoxes. The frozen hemisphere blooming into a luxuriant garden, as its seasons came round to occur at the opposite sites of the terrestrial orbit, and the vernal hemisphere subsiding simultaneously into ice-bound rigor. Thus a plausible explanation was offered of the anomalous alternations of glacial and semi-tropical periods, attested on incontrovertible geological evidence as having succeeded each other in times past over what are now temperate regions. They succeeded each other, it is true, with much less frequency and regularity than the theory demanded, but the discrepancy was overlooked or smoothed away. The most recent glacial epoch was placed by Dr. Croll about 200,000 years ago, when the eccentricity of the Earth's orbit was 3.4 times as great as it is now. At present, a faint representation of such a state of things is afforded by the southern hemisphere. One condition of glaciation in the coincidence of winter, with the maximum of remoteness from the sun, is present. The other, a high eccentricity, is deficient. Yet the ring of ice-bound territory hemming in the southern pole is well known to be far more extensive than the corresponding region in the north. The verification of this ingenious hypothesis depends upon a variety of intricate meteorological conditions, some of which have been adversely interpreted by competent authorities. What is still more serious, its acceptance seems precluded by time relations of a simple kind. Dr. Wright has established with some approach to certainty that glacial conditions ceased in Canada and the United States about 10 or 12,000 years ago. The erosive action of the Falls of Niagara qualifies them to serve as a clepsydra, or water clock, on a grand scale, and their chronological indications have been amply corroborated elsewhere and otherwise on the same continent. The astronomical ice age, however, should have been enormously more antique. No reconciliation of the facts with the theory appears possible. The first attempt at an experimental estimate of the mean density of the Earth was Maskelyne's observation in 1774 of the deflection of a plumb line through the attraction of Schehallien. The conclusion thence derived that our globe weighs 4.5 times as much as an equal bulk of water was not very exact. It was considerably improved upon by Cavendish, who in 1798 brought into use the torsion balance constructed for the same purpose by John Michel. The resulting estimate of 5.48 was raised to 5.66 by Francis Bailey's elaborate repetition of the process in 1838 through 42. From experiments on the subject made in 1872 to 73 by Cornu and Bayle, the slightly inferior value of 5.56 was derived, and it was further shown that the data collected by Bailey, when corrected for a systematic error, gave practically the same result, 5.55. Mr. Wilsing's of 5.58, obtained at Potsdam in 1889, nearly agreed with it, while Professor Poynting, by means of a common balance, arrived at a terrestrial mean density of 5.49. Professor Boys next entered the field with an exquisite apparatus in which a quartz fiber performed the functions of a torsion rod, and the figure 5.53 determined by him and exactly confirmed by Dr. Brown's research at Mariaschein, Bohemia in 1896 may be called the standard value of the required datum. Newton's guess at the average weight of the Earth as 5 or 6 times that of water has thus been curiously verified. Operations for determining the figure of the Earth were carried out during the last century on an unprecedented scale. The Russo-Scandinavian arc, of which the measurement was completed under the direction of the elder Struve in 1855, reached from Hammerfest to Asmalia on the Danube, a length of 25 degrees 20 minutes. But little inferior to it was the Indian arc, begun by Lambton in the first years of the century, continued by Everest, revised and extended by Walker. Both were surpassed in compass by the Anglo-French arc, which embraced 28 degrees, and considerable segments of meridians near the Atlantic and Pacific shores of North America were measured under the auspices of the United States Coast Survey. But these operations shrink into insignificance by comparison with Sir David Gill's grandiose scheme for uniting two hemispheres by a continuous network of triangulation. The history of geodesy in South Africa began with Lassaielle's measurements in 1752. They were repeated and enlarged in scope by Sir Thomas Maclear in 1841 through 48. His determinations prepared the way for a complete survey of Cape Colony and Natal, executed during the 10 years of 1883 through 92 by Colonel Morris, R.E., under the direction of Sir David Gill. Bechuanaland and Rhodesia were subsequently included in the work, and the Royal Astronomer obtained in 1900 the support of the International Geodetic Association for its extension to the mouth of the Nile. Nor was this the limit of his design. By carrying the survey along the Levantine coast, connection can be established with Struve's system, and the magnificent amplitude of 105 degrees will be given to the conjoined African and European arcs. Meantime, the French have undertaken the remeasurement of Bouguer's Peruvian arc, and a corresponding Russo-Swedish enterprise is progressing in Spitzenbergen, so that abundant materials will ere long be provided for fresh investigations of the shape and size of our planet. The smallness of the outstanding uncertainty can be judged by comparing J.B. Listing's with General Clarke's results, published in the same year, 1878. Listing stated the dimensions of the terrestrial spheroid as follows. Equatorial radius is 3,960 miles. The polar radius is 3,947 miles. Ellipticity is 1/288.5. Clarke's corresponding figures were 3,963 and 3,950 miles, giving an ellipticity of 1/293.5. The value of the latter fraction at present generally adopted is 1/292. That is to say, the thickness of the protuberant equatorial ring is held to be 1/292 of the equatorial radius. From astronomical considerations, it is true, Newcomb estimated the ratio at 1/308, but for obtaining this particular datum, geodetical methods are unquestionably to be preferred. End of Chapter 7, Part 2. Chapter 7 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary CLERKE. Chapter 7, Part 3. Planets and Satellites. The Moon possesses for us a unique interest. She in all probability shared the origin of the earth. She perhaps prefigures its decay. She is at present its minister and companion. Her existence, so far as we can see, serves no other purpose than to illuminate the darkness of terrestrial nights, and to measure, by swiftly recurring and conspicuous changes of aspect, the long span of terrestrial time. Inquiries stimulated by visible dependence and aided by relatively close vicinity have resulted in a wonderfully minute acquaintance with the features of the single lunar hemisphere open to our inspection. Selenography, in the modern sense, is little more than 100 years old. It originated with the publication in 1791 of Schröter's Selenotopographische Fragmente. Not but that the lunar surface had already been diligently studied, chiefly by Hevelius, Cassini, Riccioli, and Tobias Mayer. The idea, however, of investigating the moon's physical condition and detecting symptoms of the activity there of natural forces through minute topographical inquiry first obtained effect at Lilienthal. Schröter's delineations, accordingly, imperfect though they were, afforded a starting point for a comparative study of the superficial features of our satellite. The first of the curious objects, which he named Rills, was noted by him in 1787. Before 1801, he had found 11. Lohrmann added 75, Madler 55. Schmidt published, in 1866, a catalogue of 425, of which 278 had been detected by himself, and he eventually brought the number up to nearly 1,000. They are then a very persistent lunar feature, though wholly without terrestrial analog. There is no difference of opinion as to their nature. They are quite obviously clefts in a rocky surface 100 to 500 yards deep, usually a couple of miles across, and pursuing straight, curved, or branching tracks up to 150 miles in length. As regards their origin, the most probable view is that they are fissures produced in cooling, but Neison inclines to consider them rather as dried watercourses. On February 24, 1792, Schröter perceived what he took to be distinct traces of a lunar twilight, and continued to observe them during 9 consecutive years. They indicated, he thought, the presence of a shallow atmosphere, about 29 times more tenuous than our own. Bessel, on the other hand, considered that the only way of saving a lunar atmosphere was to deny it any refractive power, the sharpness and suddenness of star occultations, negativing the possibility of gaseous surroundings of greater density, admitting an extreme supposition, than 1 of 500 that of terrestrial air. Newcomb places the maximum at 1 of 400. Sir John Herschel concluded, the non-existence of any atmosphere at the moon's edge having a 1 in 1,980 part of the density of the Earth's atmosphere. This decision was fully borne out by Sir William Huygens' spectroscopic observation of the disappearance behind the moon's limb of the small star E Piscium, January 4, 1865. Not the slightest sign of selective absorption or unequal refraction was discernible. The entire spectrum went out at once, as if a slide had suddenly dropped over it. The spectroscope has uniformly told the same tale, for M. Toland's observation during the total solar eclipse at Sohag of a supposed thickening at the moon's rim of certain dark lines in the solar spectrum is now acknowledged to have been illusory. Moonlight, analyzed with the prism, is found to be pure reflected sunlight, diminished in quantity, owing to the low reflective capability of the lunar surface, to less than 1/5 its incident intensity, but wholly unmodified in quality. Nevertheless, the diameter of the moon appeared from the Greenwich observations discussed by Airy in 1865 to be 4 minutes smaller than when directly measured, and the effect would be explicable by refraction in a lunar atmosphere 2,000 times thinner than our own at the sea level. But the difference was probably illusory. It resulted in part, if not wholly, from the visual enlargement by irradiation of the bright disk of the moon. Professor Comstock, employing the 16-inch Clarke equatorial of the Washburn Observatory, found in 1897 the refractive displacements of occulted stars so trifling as to preclude the existence of a permanent lunar atmosphere of much more than 1 in 5,000 the density of the terrestrial envelope. The possibility, however, was admitted that on the illuminated side of the moon temporary exhalations of aqueous vapor might arise from ice strata evaporated by sun heat. Meantime, some renewed evidence of actual crepuscular gleams on the moon had been gathered by Messrs. Paul and Prosper Henry of the Paris Observatory, as well as by Mr. W. H. Pickering in the pure air of Arequipa at an altitude of 8,000 feet above the sea. An occultation of Jupiter, too, observed by him August 12, 1892, was attended with a slight flattening of the planet's disk through the effect, it was supposed, of lunar refraction, but of refraction in an atmosphere possessing at most 1 of 4,000 the density at the sea level of terrestrial air, and capable of holding in equilibrium no more than 1/250th of an inch of mercury. Yet this small barometric value corresponds, Mr. Pickering remarks, to a pressure of hundreds of tons per square mile of the lunar surface. The compression downward of gaseous strata on the moon should in any case proceed very gradually, owing to the slight power of lunar gravity, and they might hence play an important part in the economy of our satellite while evading spectroscopic and other tests. Thus, as Mr. Raynard remarked, the cliffs and pinnacles of the moon bear witness, by their unworn condition, to the efficiency of atmospheric protection against meteoric bombardment, and Mr. Pickering shows that it could be afforded by such a tenuous envelope as that postulated by him. The first to emulate Schröter's selenographical zeal was Wilhelm Gotthelf Lohrmann, a land surveyor of Dresden, who in 1824 published 4 out of 25 sections of the first scientifically executed lunar chart on a scale of 37½ inches to a lunar diameter. His sight, however, began to fail 3 years later, and he died in 1840, leaving materials from which the work was completed and published in 1878 by Dr. Julius Schmidt, late director of the Athens Observatory. Much had been done in the interim. Beer and Madler began at Berlin in 1830, their great trigonometrical survey of the lunar surface, as yet neither revised nor superseded. A map issued in 4 parts, 1834 through 36, on nearly the same scale as Lohrmann's, but more detailed and authoritative, embodied the results. It was succeeded in 1837 by a descriptive volume bearing the imposing title Der Mond oder allgemeine vergleichende Selenographie. This summation of knowledge in that branch, though in truth leaving many questions open, had an air of finality which tended to discourage further inquiry. It gave form to a reaction against the sanguine views entertained by Hevelius, Schröter, Herschel, and Gruithuisen as to the possibilities of agreeable residence on the moon, and relegated the Selenites, one of whose cities Schröter thought he had discovered, and of whose festal processions Gruithuisen had not despaired of becoming a spectator, to the shadowy land of the Ivory Gate. All examples of change in lunar formations were, moreover, dismissed as illusory. The light contained in the work was, in short, a dry light, not stimulating to the imagination. A mixture of lie, Bacon shrewdly remarks, doth ever add pleasure. For many years, accordingly, Schmidt had the field of selenography almost to himself. Reviving interest in the subject was at once excited and displayed by the appointment in 1864 of a lunar committee of the British Association. The indirect were of greater value than the direct fruits of its labors. The English school of selenography rose into importance. Popularity was gained for the subject by the diffusion of works conspicuous for ingenuity and research. Nasmyth's and Carpenter's beautiful illustrated volume, 1874, was succeeded after 2 years by a still more weighty contribution to lunar science in Mr. Nison's well-known book, accompanied by a map based on the survey of Beer and Madler, but adding some 500 measures of positions, beside the representation of several thousand new objects. With Schmidt's Charta Der Gebirge des Mondes, Germany once more took the lead. This splendid delineation, built upon Lohrmann's foundation, embraced the detail contained in upwards of 3,000 original drawings representing the labor of 34 years. No less than 32,856 craters are represented in it, on a scale of 75 inches to a diameter. An additional help to lunar inquiries was provided at the same time in this country by the establishment, through the initiative of the late Mr. W.R. Baird, of the Selenographical Society. But the strongest incentive to diligence in studying the rugged features of our celestial helpmeet has been the idea of probable or actual variation in them. A change always seems to the inquisitive intellect of man like a breach in the defenses of nature's secrets, through which it may hope to make its way to the citadel. What is desirable easily becomes credible, and thus statements and rumors of lunar convulsions have successively, during the last 100 years, obtained credence, and successively, on closer investigation, been rejected. The subject is one as to which illusion is peculiarly easy. Our view of the moon's surface is a bird's eye view. Its conformation reveals itself indirectly, through irregularities in the distribution of light and darkness. The forms of its elevations and depressions can be inferred only from the shapes of the black, unmitigated shadows cast by them. But these shapes are in a state of perpetual and bewildering fluctuation, partly through changes in the angle of illumination, partly through changes in our point of view caused by what are called the moon's librations. The result is that no single observation can be exactly repeated by the same observer, since identical conditions recur only after the lapse of a great number of years. Local peculiarities of surface, besides, are liable to produce perplexing effects. The reflection of earth light at a particular angle from certain bright summits completely, though temporarily, deceived Herschel in the belief that he had witnessed in 1783 and 1787 volcanic outbursts on the dark side of the moon. The persistent recurrence, indeed, of similar appearances under circumstances less amenable to explanation inclined Webb to the view that effusions of native light actually occur. More cogent proofs must, however, be adduced before a fact so intrinsically improbable can be admitted as true. But from the publication of Beer and Mädler's work until 1866, the received opinion was that no genuine sign of activity had ever been seen, or was likely to be seen, on our satellite; that her face was a stereotyped page, a fixed and irreversible record of the past. A profound sensation, accordingly, was produced by Schmidt's announcement, in October 1866, that the crater Linné in the Mare Serenitatis had disappeared, effaced, as it was supposed, by an igneous outflow. The case seemed undeniable, and is still dubious. Linné had been known to Lohrmann and Mädler, 1822-32, as a deep crater, 5 or 6 miles in diameter, the third largest in the dusky plain known as the Mare Serenitatis, and Schmidt had observed and drawn it, 1840-43, under a practically identical aspect. Now it appears under high light as a whitish spot, in the center of which, as the rays begin to fall obliquely, a pit, scarcely 2 miles across, emerges into view. The crateral character of the comparatively minute depression was detected by Father Secchi, February 11, 1867. This is not all. Schröter's description of Linné, as seen by him November 5, 1788, tallies quite closely with modern observation, while its inconspicuous in 1797 is shown by its omission from Russell's lunar globe and maps. We are thus driven to adopt one of two suppositions. Either Lohrmann, Mädler, and Schmidt were entirely mistaken in the size and importance of Linnae, or a real change in its outward semblance supervened during the first half of the century and has since passed away, perhaps again to recur. The latter hypothesis seems the more probable, and its probability is strengthened by much evidence of actual obscuration or variation of tint in other parts of the lunar surface, more especially on the floor of the great walled plain named Plato. From a re-examination with a 13-inch refractor at Arequipa in 1891-92 of this region and of the mare Serenitatis, Mr. W. H. Pickering inclines to the belief that lunar volcanic action, once apparently so potent, is not yet wholly extinct. An instance of the opposite kind of change was alleged by Dr. Hermann J. Klein of Köln in March 1878. In Linnae, the obliteration of an old crater had been assumed. In Hyginus N, the formation of a new crater was asserted. Yet quite possibly the same cause may have produced the effects thought to be apparent in both. It is, however, far from certain that any real change has affected the neighborhood of Hyginus. The novelty of Klein's observation of May 19, 1877, may have consisted simply in the detection of a hitherto unrecognized feature. The region is one of complex formation, consequently of more than ordinary liability to deceptive variations in aspect under rapid and entangled fluctuations of light and shade. Moreover, it seems to be certain, from Messrs. Pret and Capron's attentive study, that Hyginus N is no true crater, but a shallow, saucer-like depression, difficult of clear discernment. Under suitable illumination, nevertheless, it contains and is marked by an ample shadow. In both these controverted instances of change, lunar photography was invoked as a witness, but notwithstanding the great advances made in the art by De la Rue in this country, by Draper, and above all by Rutherford in America, without decisive results. Investigations of the kind began to assume a new aspect in 1890, when Professor Holden organized them at the Lick Observatory. Autographic moon pictures were no longer taken casually, but on system, and Dr. Weinek's elaborate study and skillful reproductions of them at Prague gave them universal value. They were designed to provide materials for an atlas on the scale of Beer and Madler's, of which some beautiful specimen plates have been issued. At Paris in 1894, with the aid of a large equatorial code, a work of similar character was set on foot by Messrs. Louvy and Puiseux. Its progress has been marked by the successive publication of 5 installments of a splendid atlas on a scale of about 8 feet to the lunar diameter, accompanied by theoretical dissertations designed to establish a science of selenology. The moon's formations are thus not only delineated under every variety of light incidence, but their meaning is sought to be elicited and their history and mutual relations interpreted. Henceforth, at any rate, the lunar volcanoes can scarcely, without notice taken, breathe hard in their age-long sleep. Melanie was the first to get undeniable heating effects from moonlight. His experiments, made on Mount Vesuvius early in 1846, were repeated with like result by Zantedeschi at Venice 4 years later. A rough measure of the intensity of those effects was arrived at by Piazzi Smith at Guajara, on the peak of Teneriffe, in 1856. At a distance of 15 feet from the thermal multiplier, a Price's candle was found to radiate just twice as much heat as the full moon. Then, after 13 years, in 1869 to 72, an exact and extensive series of observations on the subject were made by the present Earl of Rosse. The lunar radiations from the first to the last quarter displayed when concentrated with the Parsonstown 3-foot mirror, appreciable thermal energy, increasing with the phase, and largely due to dark heat, distinguished from the quicker vibrating sort by inability to traverse a plate of glass. This was supposed to indicate an actual heating of the surface during the long lunar day of 300 hours to about 500 degrees Fahrenheit, corrected later to 197 degrees, the moon thus acting as a direct radiator no less than as a reflector of heat. But the conclusion was very imperfectly borne out by Dr. Bourdica's observations with the same instrument and apparatus during the total lunar eclipse of October 4, 1884. This initial opportunity of measuring the heat phases of an eclipsed moon was used with the remarkable result of showing that the heat disappeared almost completely, though not quite simultaneously, with the light. Confirmatory evidence of the extraordinary promptitude with which our satellite parts with heat, already to some extent appropriated, was afforded by Professor Langley's bolometric observations at Allegheny of the partial eclipse of September 23, 1885. Yet it is certain that the moon sends us a perceptible quantity of heat on its own account, besides simply throwing back solar radiations. For in February 1885, Professor Langley succeeded, after many fruitless attempts, in getting measures of a lunar heat spectrum. The incredible delicacy of the operation may be judged of from the statement that the sum total of the thermal energy dispersed by his rock salt prisms was insufficient to raise a thermometer fully exposed to it 1/1000th of a degree centigrade. The singular fact was, however, elicited that this almost evanescent spectrum is made up of two superposed spectra, one due to reflection, the other, with a maximum far down in the infrared, to radiation. The corresponding temperature of the moon's sunlit surface Professor Langley considers to be about that of freezing water. Repeated experiments have failed to get any thermal effects from the dark part of the moon. It was inferred that our satellite has no internal heat sensible at the surface, so that the radiations from the lunar soil, giving the low maximum in the heat spectrum, must be due purely to solar heat which has been absorbed and almost immediately re-radiated. Professor Langley's explorations of the terra incognita of immensely long wavelengths, where lie the unseen heat emissions from the Earth into space, led him to the discovery that these, contrary to the received opinion, are in good part transmissible by our atmosphere, although they are completely intercepted by glass. Another important result of the Allegheny work was the abolition of the anomalous notion of the temperature of space, fixed by Boulais at -140 degrees centigrade. For space itself can have no temperature, and stellar radiation is a negligible quantity. Thus, it is safe to assume that a perfect thermometer suspended in space at the distance of the Earth or Moon from the Sun, but shielded from its rays, would sensibly indicate the absolute zero, ordinarily placed at -273 degrees centigrade. A prize essay on the distribution of the Moon's heat, The Hague, 1891, by Mr. Frank W. Very, who had taken an active part in Professor Langley's long-sustained inquiry, embodies the fruits of its continuation. They show the lunar disk to be tolerably uniform in thermal power. The brighter parts are also indeed hotter, but not much. The traces perceived of a slight retention of heat by the substances forming the lunar surface agreed well with the Parsonstown observations of the total eclipse of the moon, January 28, 1888, for they brought out an unmistakable divergence between the heat and light phases. A curious decrease of heat, previous to the first touch of the Earth's shadow upon the lunar globe, remains unexplained, unless it be admissible to suppose the terrestrial atmosphere capable of absorbing heat at an elevation of 190 miles. The probable range of temperature on the moon was discussed by Professor Very in 1898. He concluded it to be very wide. Hotter than boiling water under the sun's vertical rays, the arid surface of our dependent globe must, he found, cool in the 14-day lunar night to about the temperature of liquid air. Although that fundamental part of astronomy known as celestial mechanics lies outside the scope of this work, and we therefore pass over in silence the immense labors of Plana, de Mousseau, Hansen, Delaunay, G.W. Hill, and Airy in reconciling the observed and calculated motions of the moon, there is one slight but significant discrepancy, which is of such importance to the physical history of the solar system that some brief mention must be made of it. Halley discovered in 1693, by examining the records of ancient eclipses, that the moon was going faster then than 2,000 years previously, so much faster as to have got ahead of the place in the sky she would otherwise have occupied, by about 2 of her own diameters. It was one of Laplace's highest triumphs to have found an explanation of this puzzling fact. He showed in 1787 that it was due to a very slow change in the ovalness of the Earth's orbit, tending, during the present age of the world, to render it more nearly circular. The pull of the sun upon the moon is thereby lessened, the counterpull of the Earth gets the upper hand, and our satellite, drawn nearer to us by something less than an inch per year, proportionately quickens her pace. Many thousands of years hence, the process will be reversed. The terrestrial orbit will close in at the sides. The lunar orbit will open out under the growing stress of solar gravity, and our celestial chronometer will lose instead of gaining time. This is all quite true as Laplace put it, but it is not enough. Adams, the virtual discoverer of Neptune, found with surprise in 1853 that the received account of the matter was essentially incomplete, and explained, when the requisite correction was introduced, only half the observed acceleration. What was to be done with the remaining half? Here Delaunay, the eminent French mathematical astronomer, unhappily drowned at Cherbourg in 1872 by the capsizing of a pleasure boat, came to the rescue. It is obvious to anyone who considers the subject a little attentively that the tides must act to some extent as a friction brake upon the rotating Earth. In other words, they must bring about an almost infinitely slow lengthening of the day, for the two masses of water piled up by lunar influence on the hither and farther sides of our globe strive, as it were, to detach themselves from the unity of the terrestrial spheroid and to follow the movements of the moon. The moon, accordingly, holds them against the whirling Earth, which revolves like a shaft in a fixed collar, slowly losing motion and gaining heat, eventually dissipated through space. This must go on, so far as we can see, until the periods of the Earth's rotation and of the moon's revolution coincide. Nay, the process will be continued, should our oceans survive so long, by the feebler tide-raising power of the sun, ceasing only when day and night cease to alternate, when one side of our planet is plunged in perpetual darkness and the other seared by unchanging light. Here then we have the secret of the moon's turning always the same face towards the Earth. It is that in primeval times, when the moon was liquid or plastic, an Earth-raised tidal wave rapidly and forcibly reduced her rotation to its present exact agreement with her period of revolution. This was divined by Kant nearly a century before the necessity for such a mode of action presented itself to any other thinker. In a weekly paper published at Königsberg in 1754, the modern doctrine of tidal friction was clearly outlined by him, both as regards its effects actually in progress on the rotation of the earth and as regards its effects already consummated on the rotation of the moon, the whole forming a preliminary attempt at what he called a natural history of the heavens. His sagacious suggestion, however, remained entirely unnoticed until revived, it would seem independently, by Julius Robert Mayer in 1848, while similar and probably original conclusions were reached by William Ferrel of Allensville, Kentucky in 1858. Delaunay was not then the inventor or discoverer of tidal friction. He merely displayed it as an effective cause of change. He showed reason for believing that its action in checking the earth's rotation, far from being, as Ferrel had supposed, completely neutralized by the contraction of the globe through cooling, was a fact to be reckoned with in computing the movements as well as in speculating on the history of the heavenly bodies. The outstanding acceleration of the moon was thus at once explained. It was explained as apparent only, the reflection of a real lengthening by 1 second in 100,000 years of the day. But on this point the last word has not yet been spoken. Professor Newcomb undertook in 1870 the onerous task of investigating the errors of Hansen's lunar tables as compared with observations prior to 1750. The results, published in 1878, proved somewhat perplexing. They tend, in general, to reduce the amount of acceleration left unaccounted for by Laplace's gravitational theory, and proportionately to diminish the importance of the part played by tidal friction. But in order to bring about this diminution, and at the same time conciliate Alexandrian and Arabian observations, it is necessary to reject as total the ancient solar eclipses known as those of Thales and Larissa. This may be necessary, but it must be admitted to be a hazardous expedient. Its upshot was to indicate a possibility that the observed and calculated values of the moon's acceleration might, after all, prove to be identical, and the small outstanding discrepancy was still further diminished by Tisserand's investigation, differently conducted on the same Arabian eclipses discussed by Newcomb. The necessity of having recourse to a lengthening day is then less pressing than it seemed some time ago, and the effect, if perceptible in the moon's motion, should, M. Tisserand remarked, be proportionately so in the motions of all the other heavenly bodies. The presence of the apparent general acceleration that should ensue can be tested with most promise of success, according to the same authority, by delicate comparisons of past and future transits of Mercury. Newcomb further showed that small residual irregularities are still found in the movements of our satellite, inexplicable either by any known gravitational influence or by any uniform value that could be assigned to secular acceleration. If set down to the account of imperfections in the timekeeping of the earth, it could only be on the arbitrary supposition of fluctuations in its rate of going, themselves needing explanation. This, it is true, might be found in very slight changes of figure, not altogether unlikely to occur. But into this cloudy and speculative region astronomers for the present decline to penetrate. They prefer, if possible, to deal only with calculable causes, and thus to preserve for their most perfect of sciences its special prerogative of assured prediction. End of Chapter 7, Part 3.